unlocking unprecedented computational power and setting the stage for revolutionary technological advancements. To begin this momentous occasion, let us invoke the blessings of Lord Ganesha, the remover of obstacles and the deity of wisdom and intellect. I now invite our esteemed dignitaries to kindly join us for the lighting of the ceremonial lamp, followed by the Ganesh Vandana.
गणपति सूरनिरागसमो शुभनयना करुणामय गौरी हरश्री वरद विनायक ओंकार गणपति ओंकार गणपति अधिपति सुखपति छंदपति गंधापति निरंतर लीन निरंतर हो सूर निरागस हो सूर निरागस हो गणपति सूर निरागस हो. Thank you.
Thank you, everyone. We will now proceed with the felicitation of our esteemed guests. I would like to invite our dignitaries on the stage to honor them with a small token of our appreciation. I would request Dr. Ketan Kotecha, Professor and Director, SIT Pune, to felicitate Dr. U.B. Desai, Sir, Chancellor, Anurag University. I request Ms. Lakshmi Kanat Ma'am, Program Director and Scientist C-DAC Pune, to felicitate Colonel Retired P. Sai Shankar Sir, BSN, National Contribution, PhD. I request Dr. Shruti Patil Ma'am, Head of the Department of AI and Machine Learning, SIT Pune, to felicitate Mr. Aditya Sinha, Director, C-DAC Patna. I request Dr. Shilpa Geeti Ma'am, Professor, Department of AI and Machine Learning, SIT Pune, to felicitate Ms. Lakshmi Kanat Ma'am, Program Director and Scientist, C-DAC Pune. Thank you all. We will now move forward with a warm welcome from the organizers. To deliver the welcome address, I kindly invite Ms. Lakshmi Kanat Ma'am from C-DAC Pune to the stage. Lakshmi Kanat Ma'am is a key contributor at the C-DAC Pune, specializing in the design and development of information technology solutions across diverse fields such as AI in oncology, IoT systems, public health, and finance. Her work involves creating ICT systems that utilize mobile platforms, AI, and high-performance computing to deliver advanced analytics and solutions. In addition to her technical expertise, Ms. Lakshmi leads capacity building programs for IT professionals in the Ayush sector, helping integrate technology into traditional healthcare practices.
Thank you so much. The voice of Ganesh Vandana was really good, and we have a very nice beginning to this nice quantum workshop as well as symposium today. A very, very warm welcome to all the speakers, to all the delegates, as well as the heads of institutions who have taken time to attend this important meeting and event today with us. I would like to begin with saying from Rigveda, which says that Ano Bhadra Kratavo Yantu Vishwataha, which means let good thoughts, noble thoughts come to us from all around us. So we have a very good tradition of sharing knowledge amongst ourselves, and this is a guiding principle we can use. So this quantum accelerated workshop, as we know that this whole world is full of complex problems and we need new ways to solve those problems. And quantum is one of the ways forward along with AI. So I'm very happy that the HOD of AI and the director of the institute have given a lot of thrust to this area of AI and finding applications in several domains. So we will all benefit from these applications and understanding the ways forward through this workshop. What are the areas we can look forward to? Some of the areas are drug discovery, secure communications, and of course the financial modeling. So these are some representative areas, but our country is huge and the number of problems we face as a country and as a globe are many. So only sky is the limit for us to define problems and solve it the quantum way. And then another important aspect which we intend to solve or which we intend to bring forth through this symposium is the idea of collaboration or development of an ecosystem. So don't just look at it as a set of technologies, but also as a forum or as an opportunity, a very big opportunity to network. So if we network with the right people, then this the idea of this symposium, one of the ideas of the symposium will be successful because we need to be able to form good collaborations and large teams to solve big problems. So let us keep this as one of the areas in our mind while we immerse ourselves in quantum technology. Then in this accelerated computing workshop, we intend to cover the fundamentals of quantum mechanics, quantum hardware innovations, quantum software ecosystems, HPC-based quantum accelerators. So as you know, C-DAC specializes in the area of supercomputing as well as development of quantum accelerators. And now with AI, these three together will help us solve a lot of problems. The other area covered today will be quantum algorithm design as well as hands-on simulations with the QSim simulator. Going forward, we have already looked at the important role that collaborations are going to play and the immense promise that the quantum technologies hold. One mantra that I think all of us can also look at, this area of quantum computing is not easy. So we need to have the lot of patience to learn this new paradigm completely. And the mantra that we can carry for today, from today, is the mantra of Charai Beti, which means we need to keep walking. So we need to keep walking with technology, we need to keep walking with each other. And now not just walking, but we also need to march. So thank you very much. And again, a very warm and hearty welcome to each one of you.
Thank you, Ms. Pandit. Now I would like to introduce our charismatic leader, Dr. Kotecha. Dr. Kotecha has been a strong advocate for research and innovation in AI and emerging technologies, and his leadership has been integral to the collaboration that has made this symposium possible. Dr. Kotecha is a world-renowned expert in AI and deep learning with over 30 years of experience at the forefront of the field. He has recently achieved global recognition as one of the top 2% scientists worldwide, a distinction conferred by the Stanford University. I request Kotecha sir to kindly deliver the welcome address.
Good morning, all of you. First of all, I welcome
my own mentor and teacher, Dr. U.B. Desai. I always tell, and I like to tell to audience as well, that first course in AI in 1998, I studied under him at IIT Bombay. Lakshmi Madam, Mr. Sai Sankar from DST, Aditya Sinha sir from C-DAC Pune, other delegates, other speakers, um, uh, faculty members, and the research scholars. I welcome all of you to the inaugural function here, which is on a very, very important topic, which is, as I understand, is quantum. I would like to give a couple of analogies and also introduce the institution. When I finished my BTech in 95, I was too much inclined to do my master's and PhD from IIT Mumbai. I waited a couple of years because I could not clear the test. The reason I was willing to do that is I was fascinated by some words in newspapers, which is AI plus robotics at that time. So I wanted to do masters in that. When I joined and I chose a supervisor and I started working, I realized it's not my cup of tea, particularly robotics. And I changed the supervisor, dropped the idea of project halfway. So what I'm trying to tell here is the quantum is similar right now. Everyone talks about quantum, and if you see newspaper, 6,000 crore India is going to give. So any researcher would like to grab the low-hanging fruits, but it's too tough. As Madam also rightly mentioned, that is very, very tough. So of course, it's a challenging for a researcher. Similar, I just recall 20 years back, I read in news that you will have a cloth, will not get wet in rain because of nanotechnology. Still, I'm waiting for that. So this will take time, So some of the things are glamorous, nothing wrong in that. It gives us excitement, but one has to put a very hard and tough efforts in there for next 5 to 10 years. It's not like that today you attend 2 days workshop and tomorrow you'll publish or get 10% of 6,000 crore from him, right? So that's the first thing, and I'm sure that today the crowd, I have seen the profile of many of you, including the speakers from IIT and others. Very, very thorough researchers. I'm sure today's will be really useful. A lot of deliberations in terms of research, futuristic goals, and what is required to set and become leader in quantum will be discussed. Second, I wanted to tell something about my institution. This institution is a very, very young institution in the Symbiosis family. We are more than 52 years young now as a university, having an extraordinary rank of 31 NIRF out of 1,100 universities across the country. And this is the flagship engineering institution, this entire building, G+6, where we house, to be exact, 2,997 students, right? So almost 3,000 students and 250 faculty and staff here, plus almost 300 PhD students. Believe me, out of 300, if you meet anyone on the road, they out of that 90% will tell that we are working in AI. Okay, maybe I have infused AI in their blood. If you go to any, and that's one of the reason why, because the AI is a tool. You cannot tell that you are master in AI means you conquer the world. AI is just a tool like Microsoft Word where you need to apply. And particularly if you are only knowing AI, hardly there is use because you need to have a problem, right? And that's what I think I have tried to give that tool to all departments, and they are using it effectively. But I'm telling this because of that, it has emerged, the institute has emerged as a very important research institution. You will not believe, which I also could not once I checked the Scopus. Last year, 23, we published 800 Scopus index papers out of these 150 faculty members, and most of them were Q1, Q2 papers as well. So I think that's one of the reasons, because we are applying AI to civil, mechanical, predictive maintenance, maybe in particular physics as well, a lot of different places. And that's what I think today also is to be done, that AI badly need now computation power and the speed to go to the next level. And I think the quantum is one of the important solution, apart from a lot of other optimizations and all. So I think that will be discussed here. This institution research at all, but at the same time, it achieves 100% placement of the students. No wonders, because like IITs next to that, we get best of the best students here. And then now the trend is, since last 2 years, the students are getting internship, and internship is getting converted to placement, and internships are also paid. So students get 40,000, 50,000 rupees per month for almost last entire year, and then they get extra with the same companies. Why it is getting done? Because I wanted to tell and thank my faculty member. They not only publish, but they nurture the students well. They help them in placement. They help them in all kinds of activities. And of course, without sacrificing anything, a single lecture can't be missed in this institution. So very tough, of course, to be in the institution, but we have extraordinary support in terms of infrastructure from the management, in terms of very high salaries, and a lot of incentives for research. If you publish a Q1 paper, any faculty member who joins yesterday and publish a Q1 paper gets 50,000 rupees extra, right? So you can publish 12, you can get 6 lakhs extra per year. That is the limit right now they have placed, because some of us are getting more than 6 lakhs, and that was the limit that's certainly set by the management, right? So these are some of the highlights. The last thing is, we have, because of this, and we are in Pune, we got noticed by a lot of industries. And believe me, Bajaj Auto, they have, under their CSR, donated 30 crore to us. And we created 18 state-of-the-art laboratories on the second floor here. And this is not a one-time investment. They are continue doing so, continuing uplifting the equipment. When I met Mr. Rajiv Bajaj first time in the inaugural, he told, these are the equipments which I told them that they should be available in 24, but you should be ahead, even because I'm alumnus of IIT Bombay. But then also he told that you should be having equipments better than IIT Bombay. Okay, so in next 5 years, any equipments, anything which you feel obsolete, tell me, I'll give it. Right? So that's a commitment from Bajaj. The goal from given to us is, we need to select the students from tier 2, tier 3 institutions where infrastructure is in bottleneck. The students come here, they get trained for 6 months, and we need to place them. Believe me, the center was inaugurated last year. The first batch started from January 22nd, and this 22nd of June, they got finished that particular certificate program, and all 118 students got placed from this institution, right? So that's a kind of commitment they expected and we could fulfill, and that's because of my dedicated faculty members here. So I really take extreme pride in my all-rounders, because they are everywhere. Unlike the teachers in previous days, I know they do only teaching. Now the teachers do maximum work compared to any other industry. This is the profession which demands 101 activity. If I write 101, I'm sure some of you will add more than that. So that many activities. So thanks to my teachers, and congratulations to Dr. Shruti for organizing this particular event, even though it's credit given to a director, but ultimately she is the one who, along with the faculty members of AI department, has organized this particular program. Best wishes.
Thank you so much, sir. Now it's my great honor to introduce Colonel Retired P. Sai Shankar, a VSM National Quantum Mission, DST. Colonel Sai Shankar is a seasoned ICT and cybersecurity expert with over 2 decades of leadership in information security, cybersecurity, governance, risk and compliance, and ICT project management. A distinguished alumnus of the Indian Military Academy, IME, and IIT Delhi, Mr. Sai is currently pursuing a PhD in post-quantum algorithms at IIT Kharagpur. His expertise has been honed through commanding ICT units and managing large-scale projects worth over 900 crores. He has also implemented risk management strategies to ensure safety during dynamic situations, including the COVID-19 pandemic. Colonel Sai has contributed extensively as an instructor in cryptology and cybersecurity at premier military institutions. He is the founder and director of Transcend Surya, a consultancy firm specializing in quantum technologies and cybersecurity. Additionally, Colonel Sai plays a pivotal role as the lead technical manager for the National Quantum Mission under the Department of Science and Technology, Government of India. His leadership and achievements have earned him prestigious honors such as the Vishist Seva Mandal and a Certificate of Merit by the Chief of the Army Staff. I request sir to please come and deliver this address.
Jai Hind everyone, and thanks ma'am for speaking such high words. I don't know how much it is applicable, but as I'm a soldier and I'm still a soldier, so I'm very less in words. I'm not a great orator. I mean action. So I will not be able to speak long, but definitely in the session which I will be covering, I will explain what I wanted to convey. But one thing I want to highlight is that quantum technologies which we are talking to is an application or outcome of quantum science. And quantum science is a separate vertical of science. It has to be seen from that lens. Whatever we are seeing working today, this TV or fridges or all this computer, they work on classical physics. People have a misunderstanding, okay, now the entire world is moving in quantum, let all also jump into the quantum. It's not so like that. It is not an upgradation like it from 1G to 2G or 2G to the 5G. So when we have to be a separate branch of science and we have to deal with that angle. Second point I want to highlight is that as a nation, we have missed many buses. Semiconductor bus was missed by us. Many buses were missed, and most of the places we have been just followers. We have never been a leader, or we are not allowing other person to lead us. And when we go for government to government interaction or dealing, most of the time we keep silence because we don't know if we have an speak with an aggressive tone with the other nation, whether the other nation will impose sanction to us. That high level confidence will come only when as a nation we have our own IPs, when we have a strong stand on our own technologies. And nature gives chance to everyone. So entire world is moving in the quantum. We have started a little bit late, but not the way. But we have immense capability. And the second point I want to highlight is that most of the time we have been working like outsourced labor to the other nations. So now it is a high time that the mission which is coming as sir has brought out at the National Quantum Mission, that nation is also giving importance. The people and the environment, the academics should take interest and make the students pursue it and take things ahead. Jai, thank you.
Yes. Thank you, sir. Now it gives me immense pleasure to introduce our next guest, Mr. Shri Aditya Sinha, Director, C-DAC Patna. Shri Aditya Kumar Sinha is a seasoned leader and visionary in the field of advanced computing, serving as the director at C-DAC Patna and C-DAC Kolkata. With over 2 decades of experience, he has been instrumental in driving high-performance teams specializing in digital transformation, health tech, agri-tech, education and training, unmanned aerial vehicles, quantum computing, and cybersecurity. Aditya sir's leadership has played a crucial role in pioneering innovative solutions for emerging technologies, including AI, high-performance computing, and digital forensics. As a scientist G under mighty Government of India, he has spearheaded numerous impactful projects, including collaborations with the Economic Offences Unit, Bihar Police, focusing on the cybersecurity, cybercrime investigation, and capacity building for law enforcement. Shri Aditya's commitment to advancing the nation's technological landscape is reflected in his strategic leadership at C-DAC and his dedication to fostering skill development in emerging technologies. His influence and contributions continue to shape the future of India's digital infrastructure. I request Sir to deliver his address.
So, good morning, Jai Hind, Namaskar. Professor UB Desai, we generally met in the mighty. Okay. So we have a unique opportunity today to hear you here. And Professor Ketan Kotecha, we already met, 4 or 5 years back when I was in C-DAC Pune, heading a group. My colleague Lakshmi Sai, we have closely related and closely working together on some of the cybersecurity projects. Okay, and we used to develop at Patna, and then he was the man who was testing those solutions when he was with the signals. My colleagues from C-DAC, the faculty members from Symbiosis, the students, participants, the speakers. It's my broad privilege to be here in this beautiful campus of Symbiosis. Always be a real momentous time when I come here, such a beautiful surroundings around. And I'm very happy to see that the culture of AI has been created out here, and the way directors have had uh, described. I'm sure that we are going to go ahead and going to create a lot of good human resources in the AI side. When coming back to the quantum, I have a vivid memory when we started first in 2015 or 2016, when we had a C-DAC started working on this mission programs, multiple mission programs for C-DAC. And one of the mission was the quantum computing, and then we had actually it was a pathfinding, okay, that how to go, what to go, what to do, what not to do, and all. So something was happening, a lot of discussions were there. In fact, Amit was involved into that. He was coordinating with the director general, that time, whatever he was director general. And we kept on working towards and that. Then 3-4 years back, we realized that we actually have to start doing actions, and we started preparing the project proposals and all. And I'm happy that 4 or 5 centers of C-DAC, they are working on multiple projects. We have a quantum simulation project, and all. We have something on this communication side. We have on the sensing side. So all those domains of the quantum we are actually touching upon. I was the head of the Kolkata Center as well, and there we have a specialized in quantum sensing. Patna is doing this quantum simulation, particularly on the GPU and all, on HPC and all. So one thing I have realized that everybody quantum is such a thing that a lot of things are coming up, a lot of noise is happening, a lot of new dimensions are coming up. Everybody is trying to do everything. So I have in fact tried to contain. In fact, talking to the people at C-DAC that you also have to define no path where not to go. Okay, because quantum is something which can't have a very full spectrum thoughts you can give it here. We have to go to deep dive into some of the technologies. Some of the verticals are identified and go to deep dive. If you can be at the shallow stage, you won't be able to achieve anything. So that was kind of thoughts I had, and then we generally interacting with the people and trying to identify the strengths of the teams at different C-DAC levels. And also, I'm trying to that these teams should interact with the similar kind of mindset of the people of the other institutions, with the academics, with the industry. In fact, we have many what you call startups are coming. We have the small industry like this. They are one of the speakers are also here today from the institute. So those are some of the things which was actually coming up, and then we realized that one thing we realized that the quantum, the way things are happening, as Professor Curtis mentioned about that, when it will come, when we realize that actual things will be coming up. One thing is that that a lot of futurists have already been convinced us that yes, quantum is going to come up in a big way. It's a new next big thing which is coming to the domain after the AI, and the complexity increases. Then we have a symbiotic relationship between the quantum and the AI. So you can't think actually two technologies separately. And as you move towards we have to see that other technologies are also merging with quantum. Other not only the technical aspect, the humanity aspects, the medical aspects, all those things are merging together when you talk about the quantum and all. So this time I have coming up a little radical thoughts had come up when I was thinking about what to talk, not to talk and all. One thing is very important since the quantum is going to take a shape near future. We need to have a kind of democratize the knowledge base of that. Many people, if you talk about quantum, they don't know anything about it. To democratize that knowledge. I'm good that Symbiosis has started some courses as a part of the BTech program in this quantum and all. So that should be there at all the places. So how to do that, what to do that we have to decide. But at least we have democratized it. It should be available to everybody. It should understand. They should not have a fear about what kind of things quantum, what kind of technology quantum we are going to take on. So these are some of the aspects we have to think. Second aspect, which is coming to my mind, sir, Desai sir, is that 17th, 18th, 19th century, where a lot of scientific discoveries have happened. Okay, mostly has happened in this Western countries, US and other places. We have not contributed our bit, or we have not been recognized. Two things as a country. This is the kind of opportunity right now. If you actually do the quantum things, we have to redefine the things with the quantum using the first principle thinking. Okay, what is the first principle thinking? If you can talk about is basically breaking down the complex system into the fundamental units and all. Okay, that is the first. Then we have to identify underlying principles, laws, and rebuilding from scratch, unmasked by conventions. So those are the first principle thinking. How to apply those first principle thinking to again thinking about the scientific theories which has been done 200 years back, how we can redefine those aspects. Okay, how we can because a lot of assumptions have been made during while defining those theories. So how those classical physical limits are there, how you can overcome those limits and all. So those are the, some of the aspects I just wanted to share with you. We have to work today, particularly academia. Academia is always having a very, very deeper thoughts on innovative technologies. As institutions like the C-DAC and all, we have most of the applied side. Applied side means shallow thinking and all. But when you have to deep thinking, you have to go to the academia. So that's very important that but we have the capability to deliver the things as per the timeline and all. So we have to join hands together and do the essentials to do good for development of these areas. Another area which is I am thinking very seriously and I'm thinking to contribute also is basically a pathways to enhance human potential using the quantum technologies. Going to be a very, very important aspect. So quantum may be the very, very important technologies for the physical health, mental health, for the cognitive enhancements, for the social intelligence, and for that extent, for this spiritual growth as well. So these are some of the things which we have to think when you are thinking about the quantum. I was attending a conference at Jadavpur University in Kolkata. I was a speaker there talking about the science of consciousness. Mostly people are talking about this how to achieve this through the quantum mechanism. So these things can be utilized for doing the things. Maybe we're talking about the quantum inspired human models. Okay. Quantum based consciousness and all those things. So those are the important aspects for the in this technological area where we are challenged by the technologies today. Being human is challenged by the technologies today. So we have to have these kind of technologies in place where we can think of having the better human model of ourselves, or we have to evaluate ourselves or evolve ourselves as a better human being. Till the time the technologies were there, which was helping you out in your muscles, like whatever the or like supporting your muscles basically. Now it's supporting your cognitive structure as well. Okay, so right time to talk on these areas, and we have to take it further. And I'm very sure that with the kind of collaborations what we're going to have, and the way that how it has been created, the government is putting the money and all. We are very sure that we are going to have our own say in this world on the quantum technologies. Thank you very much.
Yes, thank you, sir. Now it gives me immense pleasure to introduce our next guest, Dr. U.B. Desai, sir. Dr. Uday B. Desai, sir, is an esteemed academician and founding director of IIT Hyderabad, where he served from 2009 to 2019, propelling the institute into the top 10 engineering colleges in India. He is currently a professor emeritus in electrical engineering, chancellor at ICFAI Dehradun and Anurag University, Hyderabad. And also he is designated with honorary distinguished professor at Laksha University. Additionally, he is a strategic consultant for TSDSI, that is Telecom Standards Development Society of India. Dr. Desai has been a mentor director for IIT Bilal and IIT Chittoor, shaping the future of these institutions. It's a very big, I mean, it's a charismatic kind of a thing. So, sir, please allow me to.
They can Google him. Yesterday also I said,
So, sir had it allowed me to introduce him yesterday. So,
thank you so much. I think, we spend more time introducing people than listening to the speeches that people have. So I think we need to cut it down. And I think you overdo this thing. And nowadays with all kinds of searches and Google, you can get enough information you want about anybody in the world. Okay. So first of all, I'd like to thank Professor Kotecha for inviting me. I think it's indeed my great pleasure to be here. Nice to be, and I don't come to Pune very often. It's nice to be here in this beautiful historical city, and that too on the hilltop. So from the guest house, you get a beautiful view. So you don't want to take it. I mean, I had to shut the windows because it'd be too, curtains, it'd be too dark otherwise. It's so beautiful both at night and during the daytime. Thank you very much, sir. And I must also thank Dr. Shruti ma'am. Yesterday we had a very interesting discussion, and whether she was being honest or not, she was very happy with what the comments I made. I hope that is really true. See, I think, and I like to congratulate. I think quantum, as everybody has said, and I resonate with all the thoughts that have been expressed before me. It's a big thing that is happening. Only time will tell what it will deliver. It's a risk one has to take. Yeah? And as was mentioned earlier, India has not been a leader, okay, and not because of want of talent. I think we are a risk-averse country. I sit through enough committees in Delhi, and we want a guaranteed answer. Whenever we fund something, we want the solutions before we fund it. Now, if you are not going to take risks, you cannot be a leader. You can only be a leader, when you will take risks. Okay, as we can see in cricket, we have people like Rohit Sharma, Virat Kohli. They take risks. Sometimes they get out, and many a time they get us a victory. But that's the kind of risk you have to take. Yes, you are going to get out. There's no way out of that. Everybody has that day off. So I think that's one of the reasons, in a sense, I think we need to have that courage to take the risk and to accept that failure is part and parcel of our activity. And the reason I'm saying that, we have 3 missions going on right now. Quantum mission, everybody talked about, and at least something like some 20, 25 institutes are involved at different levels, hubs and lead institutes and member institutes, etc. There's another mission where I was very actively involved. It's called National Mission on Interdisciplinary Cyber-Physical Systems. There are 25 hubs which have been set up. It's about 5 years old. Technically, I would say about 3 years because we lost 2 years as part of the COVID. So, in fact, ISER Pune is one of the hubs out here. There's a third mission. So this is approximately a 6,000 crore mission or 6,400 that was mentioned earlier. Then cyber physical was 3,600 crore mission, and there's an AI mission. I really don't know exactly what is happening out there. I think some hubs have been set up last I heard, and again the same structure will be there. Maybe level A, level B, level C. The vocabulary will change. Okay. And that number kind of varies. Again, I don't have the exact number, anywhere from maybe 6,000, 7,000 to 10,000 crore. Okay. The point is that yes, this is fantastic. I'm extremely happy, but we take too long in setting up this mission. Okay. So I'm being a little critical out here. AI mission, I was involved way back. I think it was 2016 or 18, when many of us got together. Professor Kamakoti, who is now the director of IIT Madras, all of us were part of it. P.P. Chakrabarti, who was then the director of IIT Kharagpur, etc. We all wrote all the mission documents. And it took, every time I would ask, I think Sahani retired, who was the secretary, Mehti, and now I think Krishnan is the secretary. He finally got it done. And every time, oh, it will happen next year, next year. So we just take too long. And I really couldn't understand why in AI we took nearly 6 years to launch the mission. It was a no-brainer when we started the discussion. I think sometimes that's implied, we wanted some surety. It's not just them, at all levels, the files keep moving up. At every level, they want a bigger and bigger surety. That every rupee that we spend, is going to kind of bring something to us, etc. But I think in some cases, we have to take those risks out. That's one message I would like to give. I'm very happy that it is happening. Okay. Currently, if you look at the status, Before the quantum mission, work was done. MIT funded, for example, a big project, several projects in quantum, and I was the chair of the committee working group which was recommending this project. So of course, approval is given by the secretary and the financial advisors. So one is at TIFR. There I was not involved. They have an 8-bit quantum computer. It's already functional. Another one where involved, not that I'm not a quantum expert, let me make it very clear out here. But I do understand broadly what is required. So another one we funded was a joint project between, we meaning METI funded, ISC Bangalore and Raman Research Institute. They have a 5-bit quantum computer. Okay, they have built it. I also saw it out there. One of my former students who was on the faculty is also kind of involved with it, Chetan Singh Thakur. Okay. So those are the two that are kind of there in India, which is active. Another piece of interesting news is IBM recently, I don't know whether they sold it or donated it, about 120 qubit quantum computer to RPI, Rensselaer Polytechnic Institute. So that's very big news that for the first time now students at RPI have access to a quantum computer to play with. See, that is very big. In fact, any activity that we do, if students don't have access to it to play with it, that activity is not going to go too far. Okay. So in fact, these are I'm going to be critical out here. Like even with the C-DAC is out here, and I'm also part of that national supercomputing mission. And one of the proposed suggestions I had made, which was accepted by Dr. Saraswat, the then Secretary Sahani, Dr. Bhatkar, everybody, was to have a 1 or 2 petaflop machines at C-DAC. I said, house it wherever you want and let any student in the country. The student could be in Darbhanga, okay, and if there's a college there, as long as he has a proper Aadhaar and ID card for the registration, she should have access to this particular. They can log in and start playing with the computer. Every time I talk to Dr. Darwari, he says, yes, almost ho raha hai. I think again 6 or 8 years have gone by. Oh, almost ho raha hai. That is almost, that is like I would say, the theme of our country, almost ho raha hai. Okay. So this has to change. I think we need to get access to the students. Somebody else also mentioned out here the democratization of education. And democratization does not mean that I have to teach quantum computing. Today, it's available on the net. Anybody can go and access lectures. The best quantum scientist will give you the lectures. There's chat GPT, you put in some query, bingo, you'll get all the answers. Okay. So it is not that, but access to equipment. That is what is changing. You go to Stanford, the RPI is not among the top 20 universities in the US. Okay. And they have now access to a quantum computer. Yeah, maybe they are in New York, this thing. IBM has a big center in New York where they develop the quantum computer. Maybe there's some collaboration, like you have C-DAC Pune, Symbiosis, etc. And they got it. But that's a great thing. In fact, one particular meeting I was involved as part of the quantum mission. I'm not a member of the quantum mission committee. I was part of the cyber-physical system. So I made a proposal. In fact, they also mentioned that should we buy a quantum computer? And I immediately jumped, buy it. It's not cheap. The rough cost is about $100 million. But think of it, we brag and do a lot of chest thumping. We are a $3 trillion economy. If you're a $3 trillion economy, what is 100 million? You count the percentages, okay? You can quickly do that. Now, I think that is an investment which the country has to make. It is going to take us ages to develop our own quantum. And here also I'll have a debate. So ISC developed a 5-qubit computer. C-DAC, ISC, and a whole consortium made a proposal for quantum computing. I think it was approved. I think you must have got the money also. I think one of your colonel or somebody was. He was the lead person out there. We had a lot of discussion, debate. We made them sweat a little bit, rewrite the proposals and other things. Finally, it was funded, and I had a big argument with Apurva Patel. He is a professor. Recently, he just retired. May he still continue at ISC Bangalore. I said, look, you have built a 5-qubit computer. Now go for something like 40, 50 qubit computer. He says, no, we will only go for 10 qubit. And I said, why don't you leapfrog? It's okay if you fail. MIT is funding you. It's not that we are not funding you. But somehow he was still tentative. I really don't know why he's still tentative. Of course, I'm not involved in designing it and building the machine, but I think that is the leap because 5-qubit computer gave them the experience of what is required to be done, where they should go. Why can't they now jump and go say, okay, now we'll take a leapfrog, go from 5 to 50. I think they can do it, if you ask me. I know they have the talent. Money will come. Okay, if IISc Bangalore will ever to ask for money, they will get funding. I think it is very difficult for any ministry in the country to say no to IISc Bangalore, particularly when you look at quantum science. But is that, the confidence and the willpower they came at, one can do it. So we talk about it in the meetings also. Oh, yes, this quantum mission is going to be like the Manhattan Project. But I really don't think it's going like the Manhattan Project. And I hope all of you are familiar. After watching Oppenheimer, you will know what the Manhattan Project is. But I think, that Oppenheimer movie, the Manhattan Project, is like, tells how America thinks. We don't think that. Now, a lot of other things can be said. I'm sure they will have. But IIT Madras is doing fantastic work in quantum key distribution. They have set up a small network. Again, it was funded by METI. And now I hear that they have a plan to take all the way from Chennai to Delhi, a quantum key distribution network. So that's what I think C-DAC, maybe C-DAC Pune is not involved, but I think C-DAC Chennai, Bangalore is involved in Chennai. So initially they'll go from Chennai to Bangalore. Currently, I think it is SETS, IIT Madras Research Park. I'm saying this because you should be aware of at least what is happening in the country, what is happening elsewhere. As far as the technical details in quantum are concerned, there are enough experts who will talk about it, so I don't need to deliberate on that particular part. The other part, which I think is, which was mentioned earlier, the confluence of AI, quantum, that is going to play a big role. Okay. Of course, AI, the big thing is like, Professor Kotecha mentioned, yes, we started, in fact, my lab there was called SPAN Lab, Signal Processing and Artificial Neural Network. That lab started way back in 91. And the name was not coined by me, name was coined by a couple of students. I think it was Zubin Ditya and Prashant Munkur. So they are the ones who coined it. So way back, we thought of having a name called ANN, which today, of course, is like a in thing. Okay. So it started. So this confluence that will occur between the two can be quite phenomenal. And the key thing I'm saying is that we need massive computing. C-DAC has built petaflop machines, fantastic. Last I read, Argonne National Laboratory in the US, of course, it's a very defense thing. They don't talk about it much. Somewhere a small news package. They are building an exaflop machine. Okay. And they are and they are going to be having a trillion node. Currently, we have billion node LLMs of them, trillion node LLMs, and they're going to feed in every scientific paper that exists in the world. Eventually, what will happen if you want any question on science, you just go to that machine, type it in, and you'll get all the answers that you want. You don't need me, you don't need any professor, you don't need anybody else, you and your computer. That will be the relationship that you'll have. So I don't know how that's going to work out. But see, that's the level that they're thinking of. We are at petaflop, they are 1,000 times ahead of us. Okay. So I think that's the kind of risk that is required. What next? You place your bets. It is a betting game. Science and technology in particular, even science is to some extent a betting game. You bet on it. The other example, technology which is not related to broadly what we're discussing, which I think India is going very slow, and I'm going to mention CRISPR. I don't know how many of you have heard of CRISPR. Okay. So this is an amazing technology. Also, it has two sides, the double-edged sword. It's a gene editing technology. So, very simple, there's a nice program. I think I watched a movie called Human Nature on Netflix. It may still be there, or you might be able to rent it. Just check Amazon Prime or Netflix should have it. It's a fantastic documentary on CRISPR. Okay, I think the lady, she got the Nobel Prize also, professor at UC Berkeley. I'm forgetting her name right now. Okay. So I think what it does, very simplistically put, you have a word processor and we do the editing, right? If the spelling is incorrect, we'll take the letter out and we'll put a new letter. Literally, they have a technology by which you can do the same thing with your genetic code. So when you are born, for example, and if you have a genetic coding shows that you have, say, Parkinson's disease gene, you can remove that gene, replace it with a healthy structure out there, and bingo, you will not get Parkinson's disease in your life. Now, this sounds almost like science fiction, but it's happening. Of course, it has the flip side, that tomorrow people will say, look, I only want blue-eyed, blonde hair, white kids, that's it, so that's another problem. But so so every technology has that particular issue out there. But the proof of the pudding in this technology is that FDA in the US recently approved, I think few months ago, maybe 6 months ago or so, for sickle cell diseases. If you have heard of sickle cell diseases, they can use CRISPR therapy. Now that's big news. That means CRISPR has something in it because FDA is very strict in terms of what you can do. So you can use CRISPR therapy. Now, what I keep thinking is that CRISPR, AI, quantum, if the three come together, what's going to happen? I think it can be quite, I'm sure in the US people are thinking, there is rarely one can say, I'm the first to think about it today. The world is we all connected, all of us know what is happening. I'm sure they are thinking about it, maybe in Europe, maybe in China. China is far ahead of us, I think, so China is looking at it. So I would say that this is a great initiative. Once again, I congratulate Symbiosis, for holding this workshop. We need many more of this, but we need to take a leapfrog approach in our overall thinking and overall technology. Thank you so very much.
Thank you, sir. I would now like to invite Dr. Shruti Patil, Head of the Department of AI and ML and the convener of this Quantum Symposium, to deliver the vote of thanks. Dr. Patil has been a key figure in organizing the symposium, ensuring that every aspect has been correctly coordinated. Over to you. Very warm good morning to one and all the dignitaries on the dais and off the dais as well, the C-DAC team, all the participants, all the faculty members of Symbiosis Institute of Technology and AIML's department, as well as all the student volunteers. So we have reached in the end of the inauguration session, and this was an event which we have planned when we have invited Amit Saxena sir for the evaluation of our program structure, and the event has been completely executed in 1 month, well coordinated with the C-DAC team. A very big thank you to the C-DAC team for trusting the AIML department for organizing this workshop, as well as a heartfelt thanks to all the dignitaries who have flown from out of Pune, all the speakers who have come from out of Pune, and all the organizing team as well, who has taken immense effort in doing all the work, especially Dr. Archana, Dr. Shilpa, who has been instrumental from the department. Lots of guidance we have received from Amit Saxena sir, Amit Srivastav sir, the entire C-DAC team, and it was actually an experience of working as one team. It was not SIT and C-DAC team differently working for organizing an event, but it was one team which has organized and done all the efforts. So thank you so much everybody for joining us today. A very heartfelt thank to our director sir, Dr. Ketan Kotecha, for extending the support, the guidance for every event that we do in the department, and also motivating us to push the boundaries to learn new things as well. So thank you so much. Yeah. Yes, thank you, ma'am. Now, before we formally conclude the session, we would like to provide you a glimpse of the pioneering work happening in the field of quantum computing, and we would like to present a short film showcasing various quantum projects currently being undertaken at C-DAC. I request the dignitaries to please.
Welcome to the forefront of innovation, where quantum leaps in technology are made every day. Join us as we delve into the projects underway at C-DAC, unlocking the potential of quantum technologies. C-DAC has successfully implemented and is working on many projects in quantum technologies with the support of the Ministry of Electronics and Information Technology. In the area of quantum computing, the Quantum Computer Simulator Toolkit has been developed collaboratively by the Indian Institute of Science, Bangalore, IIT Roorkee, and C-DAC. QSim is accessible on cloud allowing researchers and students to write quantum code for developing quantum algorithms. In the Center of Excellence in Quantum Technology, a collaborative project with the Indian Institute of Science and the Raman Research Institute, Bangalore, FPGA-based quantum control and measurement hardware for superconducting QPU architecture alongside a Python software framework for the quantum measurement hardware has been simulator on the Param supercomputer. Aims to accelerate quantum algorithm execution with various processing cards, including vector, GPU, and FPGA. The ultimate goal is to establish a quantum experience center for a national quantum software development cloud environment. In the area of quantum communication under the Metro Area Quantum Access Network project, a consortium comprising IIT Madras, SETS Chennai, EarNet Chennai, and C-DAC recently demonstrated a successful quantum network public testbed in Chennai for quantum network and QKD research in India. Development of agile and ad hoc free space-based quantum communication using drone pioneers agile quantum communication via drones, featuring in-house development of an airborne system with quantum pointing and tracking for secure mobile quantum communication. It can be the pivotal link in quantum satellite networks, promising transformative advancements in diverse technologies. The high-performance programmable simulation framework for the Quantum Network Communication Project is to develop a framework to simulate quantum communication networks on high-performance classical computing systems. The framework allows the users to model and design protocols for quantum communication networks. The Quantum Safe Financial Transaction Framework project is for building a quantum-safe financial transaction framework that will secure financial transactions even in the presence of a quantum-enabled adversary with quantum computers. The project focuses on developing indigenous quantum key distribution for business-to-business development, post-quantum public key infrastructure. It is a multi-institutional project by IIT Madras, SETS Chennai, and IIT Kurnool, and develops a post-quantum crypto token using Crystal's algorithms. These algorithms are implemented on hardware platforms and integrated with the token, enhancing the security of the public key infrastructure against both classical and quantum computers. Development of a system capable of quantifying the presence of pollutants in water with ultra-fine levels of concentration. This project is for the development of a quantum optical sensor to detect arsenic and lead in water at incredibly low levels, up to 10 micrograms per liter. It uses entangled photons to achieve this ultra-high sensitivity. Qubit Studio is a quantum accelerated computing laboratory at C-DAC Bangalore, launched on the 23rd of January 2024. It focuses on integrating quantum technologies with conventional HPC architectures to advance quantum accelerated computing. The studio aims to develop hybrid systems combining photonic computation and communication with HPC for practical quantum computing applications. The Quantum Technology Lab is the first of its kind at C-DAC Pune and was inaugurated on the 25th of November 2023. It features a clean room for experimenting with quantum technology devices in the areas of communication and control electronics. The lab houses high-specification equipment for testing, and characterizing these devices. In future, various projects are proposed, like the establishment of a quantum reference facility, indigenization of technology for a quantum computing ecosystem, next generation quantum computers, and photonics-based computing. Leveraging on the capacity development of quantum machine learning, use cases and applications will be developed. C-DAC is working along with its collaborators in quantum technologies, aligning to the goal of the National Quantum Mission with the support of the Ministry of Electronics and Information Technology, pioneering the quantum technologies for a brighter future.
So with this, we formally conclude the inaugural session of the Quantum Accelerated Computing Symposium and Workshop. Thank you to all the esteemed guests and participants for joining us today. We look forward to a series of insightful sessions and discussions ahead. Now, I would request everyone to please rise. We'll have a group photo from this end. Everyone, please stand at the same place. Entire span आ रहा है ना?
You can take, we'll string it together.
Done?
Yes.
देखो मैं चेक करता हूँ, तुम देखो अभी अभी
ठीक है I would now request the participants to join outside for a short tea break, and then we will proceed with the further sessions. All the sessions would be conducted at the same venue.
Okay.
All of you are requested to proceed for a small tea break and then join us back at the same venue for the further sessions.
Okay. Hello, ma'am.
Is the lead technical manager of the National Quantum Mission and has received prestigious honors, including Vishishta Seva Medal. We now invite him on stage for a session on applications of quantum technologies.
Jai Hind everyone. First of all, I would like to express my gratitude to C-DAC and SID for giving an opportunity to talk in front of such an elite audience. And as the symposium, they have very well being done by C-DAC. As the full form of C-DAC is Center of Development of Advanced Computing. So it is their mandatory role of the as a mandatory role that they are the ones who has to develop the next quantum, next any power computer. Like defense has a mandatory role to defend the nation. Next, C-DAC has a mandatory role to build the next powerful computer. Today, it is a supercomputer built by them. Tomorrow, there will be a quantum computer or any other things. That is their mandatory role, and they are doing very well. And the second thing is that for any technology to develop and nourish and flourish, the two things are required. One is the money and the manpower. few years back or few decades back, as a nation, we may be thinking that we are not self-sufficient with finance, but today as a nation, we are self-sufficient with finance. There is no issue with finance. So the money part is taken care of. Second part is the convenience of the trained manpower. And the major role comes from the institute like academic institute like SIT, taking a pioneer step. Okay, this is the mission which is coming up. This is the technology which we are coming up. We have to upgrade ourselves, and they are doing this symposium. So my compliments to both of them. Before we go into the presentation in proper, you must be mesmerized or must be thinking, okay, such a modern topic of quantum technologies and what the images of Hindu gods are doing in this. This has nothing to do with the religions or anything, but it has been seen that across the world, whatever the answers we are not getting from the quantum physics or quantum mathematics and mechanics, all this, in those answers people are getting from Rig Veda and everything. So you name a topic which is not addressed in our Vedas. So when we were talking about this Indian knowledge system, people don't take it seriously. But when foreigners like US, I will quote, I know also, around 20 of them are sitting in Varanasi from the last 2 years studying Vedas so properly, and they want to integrate with the quantum. That is the level that they're thinking. But when we talk about this, but when it comes from them as a paper, definitely we will take it seriously. Having said this, I request the audience to read this statement. So this is absolutely sad and applicable. We have to be visionary. We have to be thinking forward. We cannot be just followers. So now coming to the presentation overview, how we are going to cover, we have just seen, we will see the need, what's the need, and there are few basics. I'm not expert in quantum. I'm a technical manager level. If you ask me to write equation in quantum physics, I will not be able to write it. But what I can do is that I understand the technology and its application part. There are very prominent scientists here, like Ma'am Professor Ghosh is there, Anindita Ma'am, and they are the one who are expert in deep into them. So they will be able to answer everything. Then we will see a few application of it and also an overview of the national and international funding and definitely the recommendations. So before coming into this technological perspective, if we have to see how the mankind history has evolved, if any nation which have, it can be divided into three phases. Any nation which had expertise in agriculture, they were able to dominate the entire world. That was what was the Indian civilization and the Egypt civilization. So they were experts in agriculture and they were dominating the world. After this thing, the thing came of the colonization and the industrialization. And any nation which was expert in this field, they were able to again dominate the world. Classical examples of you take a nations in the Europe, Denmark, England, or anyone, they were expert in this and they were able to rule them. Third thing is that after this thing, the phase came of the capitalism. Any nation which was expert in the field of capitalism, who had the control of the finance, were able to rule the world. Classical example is US. They understand finance to such a level, they exactly know how to make the world move. Having said this, then why the world now is moving in this field? The edge of the capitalism is almost coming. And the third revolution or the fourth revolution, which people are saying, is that a nation which will be excellent in this field, especially in the quantum field, will be able to rule the world for another 100 years. If you see Europe, why they're taking out from Europe as a nation does not have any natural resources. They only they can survive on technology only. But they miss many muscles like us, and especially in the IT thing. So they are investing in this field in a big way. Similarly, the Middle East is investing in this space because they know that the oil will today or tomorrow will finish, and what they will do. So now coming to the topic in particular.
Connection to this is not there.
Okay. This was just a small video. I want to summarize today what I'm going to summarize that whatever the edge that we want to get achieved from the classical physics, we have almost achieved it. And when we are moving ahead, there are a number of things that are happening on ground which are not being able to explain by classical physics. Those things are being explained by the quantum physics. That is the reason that the world is moving in the branch of quantum physics. Okay. So after this talk, if you after this 2 day of session, if you think that you have not understood quantum, nothing to worry. Richard Feynman said that I have not understood quantum, my students don't understand, nobody understands quantum. So if you have not understood and gone outside, you have a good fair level of IQ. If you have understood, then there is some doubt. So now coming to the quantum science in particular, on all the slides, the two words which are important is that I have underlined is exoptic and quantum. How our brains have been tuned, not with the previous brains, presently from the last 200 years, so how we have gone under the slavery and everything. We have been tuned to think like that 1 + 1 will be equal to 2. This is not how the Indian system is to work. So what I'm trying to highlight is that quantum is counterintuitive. You cannot explain, but things will happen on the ground. So if you take with that thought process, you will be able to move ahead. Just see this slide. There are various terminologies which are applicable to quantum. If you understand these two, especially the superposition and entanglement, you will be able to understand quantum little bit and to start to apply. This is the first step, and you can go deep into it. So what the superposition, I will try to explain. Superposition is the ability of a system to exist in multiple states at a same point of time. Again, I will repeat, ability of a system to exist in multiple states at the same point of time. So suppose in a classical scenario, I flip a coin, I will get a result as either head, oblique, tail. But in a quantum scenario, I will be able to get this combination of this head and tail. This all combination I can achieve. That is called as superposition. And a very famous professor in MIT used this example to explain superposition. There is in Mahabharata, there is an episode called Ras Leela, where the Krishna has in at same point of time is available at 1,000 places. This is the classical example of superposition, ability of a system to exist at multiple states at the same point of time. And now coming to the entanglement. Entanglement means if two things are entangled to each other, even though they are not physically connected, then also if I do some changes in one thing, the other thing will immediately happen in the other thing. So suppose I will give you a very, very rudimentary example to it. I take two coins entangled to each other. I keep one coin here and I keep another coin say in New York or anywhere. They are not physically connected. They are not connected in any manner. If I flip the coin here, immediately the coin will get flipped that side. That is entanglement. अगर हमने जुड़वा मूवी देखा है सलमान खान का, if there are two brothers they did, so whatever one brother does something, immediately the other brothers happen. That is a classical example of, or the Bollywood example of entanglement. So if you have understood these things, it is in a very, very top level, then you will be able to go deep into it. Okay, then we can study more and more. And how this entanglement is explained, again, there is a classical example in Mahabharata, where the king is there, he cannot see. So he has some person, of forgetting his name, Sanjay. So he created an entangled state. One state is in the battlefield and one state is in the, whatever the changes are happening in the battlefield, he is able to visualize this. This is how entanglement is explained. And now having seen that basics of quantum science, what are the applications to it? So people are talking about quantum computing, quantum technologies is not just about quantum computing. Quantum computing is just one vertical of quantum technologies. Now, I don't have to explain, all our good BTech, MTech, all students are here. There is a classical in the classical computing scenario, we have either bits 1 or 0. Whereas in the quantum computer, similar to bits, we have qubits. And the qubit, does not exist only in the 0/1 state. It can achieve in the combination of zeros and 1. And also at all the states can be achieved at the same point of time. So if I have this quantum computer, if so much of computing power is available, then what is the use of it? Let us try to explain, understand that with a small example. Suppose I have two friends, okay, and I have bought a new Firefox cycle and I have put a combination lock of it 001 like this. And both of them want this cycle, I am not giving them. Okay, so one is a classical friend, one is a quantum friend. In a classical scenario, if you see the number of combinations that are possible are 8 combinations 000, 0, 1, 0, like this, all 8 combinations are there. When I have a classical computer, when I will try to break this thing, I will put this combination one by one. First, I will apply 0, 0, 0. It may be success. Then I will apply 0, 0, 1. So simultaneously, I cannot have one after one. I will be able to apply. But whereas a quantum computer, when it comes to it, this all 8 combinations are available to me at the same point of time. Means in a quantum computer scenario, if I have a 2-bit or 3-qubit, I will be able to break the lock in one go. That is the power of quantum computer. So these are the statements available on the internet. How true or false, that the time will tell. But this is what people are saying. So what are the quantum computing? It is not like a general purpose computer which you will have now you have in a mobile or in a laptop. It are very specific computers which will have specific roles to it. Either you can achieve good simulation, either you can do good search, or you can do good optimization. These are the 3 to 4 verticals which you can use a quantum computer. So these are some of the advantages. You can just go through it and I will explain. Especially this is the one which has gained the entire world lot of traction. So presently, when you are doing a banking application, sitting anywhere, you use some protocol and encryption cryptography, RSA or elliptical cryptography. What they say that if you use the entire computing power of the world today combined together, then also it will take 10 to the power of 6 years to break to one code. And if you take an analogy, today at the years is around 10 to 3 or 10 to the power of 4. Where if I have a quantum computer, I will be able to break in days. So when the world came to know if that is the power of quantum computing, so I will be able to break every financial transaction. I will be able to know every other enemy secrets. And recently, around 3 days back, China has published a paper how using D-Wave quantum computer they are able to break RSA. How true or false it will be sooner or later, but they have done a publication in a very popular journal that has to be taken. And this application of quantums are huge, especially to the people who are from the computer science background. They can do a drug discovery. Quantum finance is one vertical. Quantum optimization, logistics are few of the advantages that application you can do. So to achieve quantum or qubit, which we called, it is not easy to achieve a qubit. Qubit have various properties to, so I cannot take this electron or something and it has a superposition or entanglement. To achieve that property, there are a few particular ways to implement it. One is the superconducting. You can use the ion trap, then neutral atoms, then photon. Dr. Santanu Sardar is there here, who will be explaining or he will be highlighting how he has built a superconducting quantum computer. So now so each way of implementing quantum computers requires a different ways of implementation. Whereas for a superconducting quantum computer, these are the unique processor environment. You require a shielding environment less than 50,000. Pressure should be as 10 billion times, and temperature should be as less than 220 milligrams. At that time, only a material or whatever you take atom or something subatomic level, that will behave a quantum properties. Means it will have superposition, entanglement properties where you can harness the power of quantum computing. So this is an example of a 4-qubit. If you see in the background, this is how the shielding has been done. From that moment, the temperature has been reduced. So this is almost equal to double the size of these 2 rooms. So these are the few slides of a quantum computer happening across the world. I don't have access to the ours one, but definitely next time I will put that slides also. These are the various ways. If in the down way, if I'm not wrong, this is iron trap. This is superconducting. This is maybe if I'm not wrong, it is neutral matter. Yeah, nitrogen vacancy also you can use to implement a quantum computer. This is the D-Wave quantum computer, one of the starting one which started in Canada. Using this only, Chinese are claiming that they are able to break popular encryption schemes. So yeah, so we have heard about quantum computer, their application. Let us see more applications to it. So I just brought out, if adversary has, if suppose China or Pakistan has a quantum computer, he will be able to know all the secrets of defense or all the things. So what is the risk? What is the rescue to it? Again, quantum physics only come to do a rescue for this. So what is quantum cryptography? Quantum cryptography is nothing but ability to have a safe communication even in the presence of a quantum computer. That is what a quantum cryptography is all about. Quantum cryptography is divided into two domains. One is the quantum key distribution and all the post-quantum cryptography. Quantum key distribution totally lies on the principles of quantum physics, whereas the post-quantum cryptography does not works on the principle of quantum physics. It works on hard mathematical problems like lattice-based cryptography and code-variant, multivariant-based cryptography. Post-quantum cryptography has no quantum vertical to it, but papers are saying and publications are saying that they are immune to the quantum computing power also. So this is how a quantum key distribution will work. People take famous example of Alice and Bob. I don't like them, so I have my example of Raman. So if the two people are want to communicate to him, if even if the Ravan is the eavesdropper, whatever the things he is doing at these two places, this he will not be able to know it. So in a quantum key distribution, first of all, no cloning is feasible. Even when an eavesdropper is trying to take some information, immediately the source and the receiver will come to know. Whereas such type of scenario does not happen in your normal. Suppose I'm doing a banking transaction with the bank. If a hacker comes into it, does that break the encryption? Neither the bank or neither me will come to know. But if I'm using a QKD, both the bank and I will come to know that something is happening. And again, I mentioned to everyone that QKD is not a cryptography protocol to do encryption. QKD is only not an encryption protocol. So let's go through the slide. So one algorithm which is immune to any computing power today or in future also is one-time pad, but it's very difficult to implement one-time pad because of its requirement. One-time pad can be implemented using a QKD. So I was just speaking to some of the professor in the institute. This is the China, which claims in 2017 or 18, which was saying that satellite-based QKD they have done it between China and Vienna. And I just want to highlight one point on this is that we all talk about as a nation as a brain drain. We make the people mature, we train them, and immediately they go outside. They work on products, and that same company from outside sell to us in 100,000 times. But in China, what is the case of a reverse brain? This scientist who was working in Vienna under some professor, he understood everything, learned everything. After 15 years, came back to China and implemented this thing. So that is what a nation requires. And so, as I mentioned, post-quantum cryptography. Post-quantum cryptography has nothing to do with quantumness. It works on hard mathematical problem of code-based and multivariates. And there is an organization called NIST, which has recently launched this encryption protocol. At some discussion level, we were having when this NIST started our today. When you do a banking application, HTTPS जो crypto suite use करते हैं, that is being used by across the world. But as a nation, we at that point of time, we may not be capable enough to implement a crypto suite. But now the entire world is changing, but somehow we are still not having our own crypto suite, and we have the best mathematicians across the world. I don't know what may be the reason, but if given a chance, we should have our own crypto suite. So this is just a quick comparison of QKD and PQC. Scalability, QKD is difficult because you require hardware devices at both the places. And the hardware, yes, it is dependent on a new set of hardware, whereas the PQC is, you can upgrade an existing, this laptop pen also we can upgrade it to quantum safe. And media dependency, QKD is either it can be fiber or free space, whereas the PQC is not media dependent. Okay, we have seen the application of quantum in the field of quantum computing. Also, we have a fair understanding in quantum communication. Now, let us see and understanding from quantum sensing and meteorology. Just go to the slide. Before GPS came into action, we used to have gyroscopes to navigate. But why gyroscope was discontinued? Because it does not have a good efficiency or accuracy. But now, with quantum sensing and physics coming in a big way, we can achieve or improve the accuracy in such a manner that we will be able to navigate without the help of GPS. That is the power of navigation, inertial navigation system that you can achieve with the help of quantum sensing. So navigation use case, I will come from the defense background, so I will give the. We have nuclear submarines. The role of the submarine had to be under the sea for months, years. But only one reason or they're prone to detection is that at regular intervals they have to do a GPS log. They come to the surface of the ocean, and the moment they come to the surface of the ocean, the radar detects it. Suppose I have a nuclear submarine and I have an inertial navigation system based on quantum physics. I do not be dependent on the GPS, and for years and years I can be under the sea rather than the fuel and other things are taken care of. So this is one thing. And we will be also able to navigate in a dense forest environment and other places. Just go to the next slide. So I will just try to explain this thing. So in a radar scenario, classical radar, with the BTech of third semester, we have a radar section subject based data. How does the radar work? I don't have to explain. We fire an electromagnetic wave, reflection happens, and detection happens. Okay. But the problem is that when their enemy has a stealthy aircraft, all these electromagnetic waves which are hitting to the aircraft, they get absorbed or reflected in various directions. The detection becomes almost difficult. So what we do, we enhance the power to detect it. But the problem is the moment you enhance the power at the ground zone, you yourself are prone to bombardment, counter bombardment from the enemy. So in this scenario, what we can do as an quantum radar, I'll try to explain. In a quantum radar, I said that we will generate two entangled photons. One photon I will keep at the low level only, and another entangled photon I will fire towards the target. Let the target absorb it, deflect it, whatever it does. Whatever the changes will happen here, immediately those changes will happen here because of the property of entanglement. So this is how the principle of quantum radar works. People had doubts on this whether this is the open source, where again China claims that they have built a quantum radar, and India as a nation is still catching it. So quantum sensing, again, go through the slides and I will try to explain. So where again I will be able to see through the walls and everything. In the classical example, like when terrorists attacked the Taj Hotel, if I had a quantum camera, I will generate entangled photons sitting outside the door. I will fire the entangled photons and they will come to this and they will do the entire mapping of the camera. So I have the complete visibility without going inside. And this is not a myth or this is not an imagination. Things are happening on ground. And from communication background, suppose you have HF, you have different type of antenna. UHF, you have a different type of antenna. Satellite, you have a different type. Where if you have a quantum antenna from 0 to 100 gigahertz, you have the ability to do the same thing. And ARL USA has almost done all this using Rydberg atoms. So in a nutshell, what are the applications that we can break enemy communication and other advantage? You can do drug discovery. It is not that quantum computing has only application from defense perspective. And from the last 1 year when I'm outside, I'm seeing immense applications, especially in the drug discovery, quantum finance. I'm presently advising two companies that are extensively working on the quantum drug discovery. So I'm seeing how the output will come into it. So it can break enemy communication. It can protect your own communication. It can detect stealth aircraft. You can navigate without GPS, see around the corners, and definitely accurate landmine detection also in single antenna for all. Now a quick environmental scan, international research. So these are the things. So what I'm trying to say is that the development is still in infancy stage, And what the stage it was in 1950s in the semiconductors, you can imagine the quantums are in this stage. So any nation or any company which will work on this thing, which will, I will say that they will be able to rule the world. That is what happening with the semiconductor industry. And the pioneering work is being carried by this. Recently, I have gone to Singapore, to see as a small nation, and the Singapore is almost like Pune. That's it. Pune जितना बड़ा शहर है पूरा देश है. And from 2007 they have this quantum mission, and more than good amount, 70 to 75% or some figure are all are Indians who are working on this, and the type of work they have done is extremely good, and that shows the leadership, and that shows the visionary. We had 2017 we started, 2018 we did the announcement, and 2024 just we passed the proposals and we are getting ready. Why I'm trying to bring out is that few of you will become the leaders, few of you will become in the decision making after that. Please don't delay decision. The quality of the leader is visionary. He has to be dynamic. He has to take risk taking decision. If you take risk-taking decisions, if you're true to your decision, nobody will question. Questions arises when your decisions are bent towards left and right. Again, some international research. Why these pictures are being shown? Because people talk it as a myth, but it is not a myth. It is happening also. How do we analyze which technology is coming up? There are two ways to analyze the amount of research paper which are coming and amount of funding going into it. So if you see the number of research paper which is coming in this field is increasing day by day. And definitely these are the number of patents which are given by the various nations. And if you see hardly any patent, but good amount of Indians are working in this field. But for others. Coming to the funding. So this is the status of the international funding. Now India also has joined the bandwagon, and now we have, as mentioned in the morning, around 6,400 crores mission has been announced to it. So this is the yearly budget. I'm not talking about a one-time. And these are open financial documents are available. Now coming to national research have gone very, very fast. This have not capturing everything. So just an overview, National Quantum Mission is HRI, Allahabad, RRI, IIT, Mumbai, Delhi, Madras. I say these are the few institutes which are doing very, very good. And I missed DRDO and few other laboratories I missed. But this is not, but now work is very good manner in this field. So a recommendation or something like that, as I bringing that as a nation, we missed many buses. But if again the nature gives chance to everyone, the entire world is changing and upgrade to one technology to other technology. I was having a discussion of project review in IIT Madras, and I was saying here you are doing PhD, what he will do. He was wanting to join to do some work in India, but he was not getting an option. Then definitely he will go outside. So if I want my son to be here only, if I don't want him to go outside, only way to enrich or make it available is to create an environment for him. If I create an environment, if the funding is available, why that person will go outside? He will not go outside. So it is very easy to blame that PhD students are going outside, people are going outside. Some level of inside thinking has to be done by senior leaders also. But what I'm trying to bring out is the system or the society is nothing but you and me. If the system at the top leaders are not going, you should suppose to be changed. That will be a hardship, but the hardship has to be taken by. The PhD student cannot give this excuse, this that there is no enough environment. You create an environment. Or if you don't create an environment, you go outside, come back to the India as a nation and then do it. आप चेंज करोगे तभी चेंज होगा, कोई और आएगा नहीं चेंज करने. So and that's it. This is my famous quote: a nation's strength depends upon what it can do on its own, not what it can borrow from others. That's it. Jai Hind. Thank you very much. If I would just like to take a few questions, something is there. Sure. Thank you very much. Yeah, please go ahead.
Thank you for the wonderful talk. And your talk made us feel something that we have heard. Once a soldier, always a soldier. So you're always talking in terms of, nation first. So there's, I have two questions.
Please. If it is technological deep interest, then it's people said they don't have.
Just from what you said, sir. Sir, according to you, according to your studies, how close are we to integrating QKD into existing communication networks? Perhaps when we are talking about defense.
It is very much feasible. We have already did a trial way back in 2019. Dr. Nidita is there. She will talk about it. We have did the trial. And already defense has placed in an order to integrate the QKD system.
And one more thing about the quantum radar that you spoke about, sir. Do you think the quantum radar struggles with range issues?
No, there will be no range issues. This is what the papers are suggesting.
Because quantum states, as we have read, they tend to degrade over long
See,
distances.
that is the aspect of coherence. Definitely decoherence will be there where the climate, condition, temperature, pressure, all will the moment decoherence will come, it will lose its quantum properties. But there are ways and mechanisms to nullify that. Quantum error corrections are there, course corrections are there. So I'm not the right person to give the technological answer, but what I have seen the work which are done, it is technically feasible. And some work I have seen within the Indian ecosystem. Anything else? Thank you. Jai Hind.
Thank you so much, sir, for your insights. To honor Colonel P.Sai Sankar, sir, I respectfully invite Mr. Amit Saxena, sir, scientist E at C-DAC, to join us on the stage for felicitation. Colonel, sir. Our next distinguished speaker is Mr. Amit Saxena, sir, scientist E at C-DAC, specializing in quantum computing. With over a decade of experience in strategic projects under the Government of India, Mr. Saxena is the key contributor to the National Supercomputing Mission and serves on the task force for big data of life sciences. His work focuses on developing quantum algorithms and HPC-based quantum accelerators, and he actively promotes quantum computing education through workshops and training. Representing C-DAC in the National Quantum Mission, he brings expertise in grid computing, cloud computing, and quantum application development. Thank you, Mr. Saxena, for joining us. I would like to welcome him on stage for a session on quantum accelerators.
Yeah, thank you so much. Yeah, thank you. So I think we were waiting for Shri Nikhil Malhotra from Tech Mahindra, but due to some personal emergency, he could not come. So I am taking this slot. So I will try to be as brief as possible, as Colonel Saishankar has given a very good overview of what are the various technologies, what are the various areas of quantum where we can apply. So I will specifically talk about the C-DAC perspective. You know everyone that why we need quantum computing. C-DAC is known for its supercomputer, and C-DAC is doing a lot of work of HPC quantum application. You know, this is the first Param supercomputer that C-DAC was made for. And after that, in 1987, we had this Param system. It was C-DAC introduced this cluster computing, which is now de facto standard for these supercomputers. So we are working in now every supercomputer is based on a cluster computer approach. Other than in the earlier time, it was like vector computers and those type of systems, but now it's all cluster computing. It's a concept view of a C-DAC. So under National Supercomputing Mission, we have many supercomputers installed, you can see. And recently, our Prime Minister has inaugurated indigenous Rudra-based supercomputer. So these are all the installation of the Param supercomputer which we have. So we had this opportunity to go to Finland, and we have seen this IQM-based quantum computer. You can see how this quantum computer looks. And mostly the part of this quantum computer is like a dilution filter. It's mostly all the cooling part. The chip is at the top, at the bottom. You can see at the bottom there is a cylinder, the quantum chip. There is only one quantum chip actually. So that quantum chips is having qubits. So that is at the bottom side. So this is you can see this is covered in the left hand side. You can see it is covered by a shield. This is the since the quantum qubits. So they are very much prone to decoherence. So they can lose the quantum state. So that's why it has to be shielded by magnetic field, electric field, and those type of things. So this is how I think a superconducting based quantum computer looks like. C-DAC is working on HPC quantum integration. You can see at the right hand side our Param Siddhi supercomputer, and the left hand side is the concept Param Q. So we are soon going to have our own Param Q based system where we will be working to integrate a quantum computer with a supercomputer. So that is going to be HPC quantum integration efforts. This is the global scenario of the quantum computing. You can see the market is growing, a lot of startups, a lot of companies, a lot of even you can see every big company is having a quantum division now. You can see TCS, you can see Infosys, you can see Tech Mahindra. They have built a quantum makers lab. So all the big Indian companies are having a quantum division. This is our nation scenario. There are a lot of academic institutes, there are a lot of industry, and there is a lot of startups which are evolving in our country. So this gives a national scenario where you can see academia, service provider, government agencies, startups, they are working together and to fulfill our national quantum mission objectives. So when we say national quantum mission, national quantum mission is India's quantum mission, and we involve academics also. So academic has a very big role to play. Now, when we say quantum market, it is growing with CAGR value of 33.1, and you can see a lot of investment in the quantum and a lot of scope for the startups to grow. So let us talk about a brief history of quantum computing. You can see it all started with the Richard Feynman when he said that quantum phenomena can be used for the computing. Then David Dose and then Peter Shor and Love Grover. So you can see always in every scenario there is one Indian background person. You can see Love Grover as an Indian person. So we invented a popular algorithm of quantum search. Why we are having this quantum computing? As you can see, all our supercomputers, they are based on the transistors. Okay, the base of the any CPU is transistors. Now, when we say it is a PNP transistor, and the gap between the P and P, there is a gate. Okay, so we have to apply the potential. Now, this gap cannot be reduced. Why we are increasing this power? Because we are decreasing the gap between the system. So, after some time, this gap cannot be increased because the gap cannot decrease because the electron can show the tunneling effect. It can pass through it. So at that distance, beyond that distance, we cannot decrease this gap. So based on that, we cannot reduce the transistor size, and based on that, our computing power is not increasing. So Moore's law is failing in that context. That's why we need new computing approaches. So this is the evolution, and this is how a quantum computer looks like. I have taken this picture from the IBM. So this is you can imagine like how the earlier supercomputers look like. Okay, how the actually earlier computers look like. So this is how the scenario of this quantum computer was. So it is like a room, but soon you will see a modular approach. Soon you will see, as the time grows, you will see a quantum computer also as a portable device. So quantum computing principles already I think has been discussed, like superposition, entanglement, tunneling. These are the three basic principles of quantum, and how we are using it in this computing approach. So this is very important concept when we see that the basic nature of quantum, like at a subatomic level, everything is like a wave. Okay, unless we observe it. The moment we observe it, it becomes a particle. So this is a basic concept of this quantum phenomena. So it's like a wave and particle based on the observation. Okay. So we can see classical bits at 0 and 1, qubit as quantum bit. It is neither 0 nor 1, or it is both 0 and 1 at the same time. This is the phenomenon of superpositions. We can understand it by giving a basic principle, like when we have tossing a coin, whether coin is either head or tail, but when it is in the air. So this is only to understand. Okay, it is not exactly quantum, but to understand that we can say the coin is in air. Then what is the state of the coin? It is in the superposition state. We can say, okay, to understand it. Then we can see the power exponential is very well exploited in quantum computers. So you can see chess where we can put 1 grain at first, double it in second, double that in third. So if we keep on doing it, this will require about 18 quintillion of the grains. So this is the power of exponential on a chessboard if we try to put it. So the same power of exponential is being exploited by the quantum computer by qubits. So when we say 2 to the power n, okay, so it's all 2 to the power n. So whenever it comes to power, it becomes exponential. So that power is being exploited. So similarly, we can see when we are having a lot of states in the computation space, if we have a lot of states and we want to get the answer in one state. So that is the principle where quantum computers are very much useful. So like in drug discovery, we have a lot of molecules. So a lot of molecules are there, and which molecule will bind as a drug target. So if you want to find it, the quantum computers are very good for that, because they can in the superposition, they can make the superposition of all these molecules, and finally we get the one answer in one instance. So this is how the basic principle of quantum works. And now we have more states, like 2 to the power 2. So then we have 4 states. 2 to the power 3, then we have 8 states. So based on that, it exponentially grows. So how the quantum computer get the result? So like we have 3 answers: 0, 0, 0, 1, 1, 0, 1, 1. Okay. Now if we observe it like we have to do shots, we have to get the result many times. Like suppose we get 100 times. So what will happen? 50 times 0, 1 comes, 17 times 1, 0 comes, and 33 times 11 comes. Okay. Then what is the correct answer? It is all probabilistic. So correct answer may be which come 50 times 0, 1. So it all based on the probability. So whatever answer comes more number of time, it is the real answer. So quantum computer will not give you a definitive answer. It will give you a probabilistic answer. So you have to find out the real answer by running multiple shots. This is a very basic quantum qubit implementation, where you have one axis at 1 and 0 axis. Okay, and psi is the general state in the superposition. How we represent psi is actually alpha 0 plus beta 1. That is a very important part. Now alpha and beta. What is alpha? Alpha square is the probability of that it will be at the 0 state, and beta square will be the probability that it is at the 1 state. Now how do we calculate it? So alpha is actually projection of psi on 0 axis, and beta is the projection of psi on the 1 axis. Okay, based on that we get the probabilities, and whichever probability is the more, the answer is that. That is a basically just to understand the quantum representation geometrically. Okay, so similarly it can be represented where alpha and beta are the probabilities as per the Max Born rule. So alpha square and the beta square is always 1, because the sum of probability is always 1. So this is the qubit representation. Now we come to various methods to implement the qubit: superconducting based, semiconductor based, trap diamond based, photonic based, defect based qubits, diamond, topological nanowire qubits, NMR based. So these are the various ways to implement the qubits. Now, which is the best one? Nobody can say no. Okay, these are all in the experimental phase. Right now, superconducting is being progressing because more number of qubits are being given by the superconducting based things. But we never know, photonics may come with a very good scaling factor. Only the problem is the interaction between the photons is a difficult aspect. So based on that, we never know which particular methodology will come up. Okay. So right now, experimentation, as you can see, National Quantum Mission, all this type of technology are being taken in consideration. Okay, we have not taken one technology in the consideration for the qubit implementation. So based on that, whichever will come in the future will lead. Okay, or maybe we can have multiple technologies leading this qubit implementation. So you can see the scenario, global scenario, where IBM is like with 1,000 qubits, Google has already, but it has stopped publishing now. DWAVE came with 5,000 qubits. Recently, our TIFR has Dr. Santosh Sardar is there. I think his lab and TIFR, they have developed a 7 qubit system, indigenous homegrown qubit at TIFR labs. So that is Indian first indigenous qubit being developed as 7 qubit. So what is C-DAC strategy is actually to focus on, as you can see, we are under Ministry of Electronics and IT. So our focus is on the electronics and IT part of that, software part, electronics part, and we are developing the quantum computer ecosystem around these technologies. So C-DAC has developed QSim. I think you have already seen the movie where we have demonstrated all our projects and products that are being developed. So QSim is available, qctoolkit.in. If you type, it is available on the cloud. You can use it. It is free to access by any student. Anyone can access it. Okay, so it is given at qctoolkit.in. You can access it, and you can send an email. Your account will be created. And tomorrow we are going to have a hands-on on QSim. Okay. So tomorrow there is a workshop, there is a lab here. So hands-on will be there. You all will be enjoying this session of the QSim demonstration. Now we talk about National Quantum Mission, and Saisender is here. He's prominently he has done a lot of work in this national streamlining this National Quantum Mission. He has helped us a lot. So this is a prestigious quantum mission, and everyone in the world is looking towards India based on this quantum mission. There are basically 4 hubs being set up: computing hub, communication hub, sensing and metrology hub, and the quantum material and devices hub. 6,000 crores has been sanctioned. Now, various opportunities in the area of quantum computing is artificial intelligence, drug discovery, optimization, cryptography, and financial services. These are some of the areas, but many areas this quantum computing can be applied and used. In the AI, I think in the AI, when we see quantum AI, it is like amalgamation of quantum and AI, where we can use the kernel methods. We can map the feature on this quantum space, Hilbert space. So when we see Hilbert, which is a complex number space, where we are multi-dimensional space. So these quantum features, classical features, can be mapped in the quantum area. So using this, I think we have developed a convolutional neural network for medical image classification. This is one of my student. She did it, and we published it in some IEEE workshop, and it is recently be published. So this is again one of the journal quantum computing will publish this data, pancreatic cancer data classifications. Then we are working with the quantum accelerator project, where QSim based simulations are being accelerated. Since C-DAC is working in mostly in supercomputers, so we have taken GPU card, vector card, FPGA card, and we have taken our QSim. Now that QSim is right now coming with 12 qubits, and it is taking a lot of time on a single CPU basis. So how can we increase the qubits, or can we reduce the time of the execution of these simulations on the system? So we have already developed 3 test beds, and we will soon be releasing it also with the QSim. Now, the major area is HPC quantum prediction to solve the problem like artificial intelligence, drug discovery, optimization, cryptography, and financial service. You can see when we say classical HPC, it works on the MPI, OpenMP, OpenACC, Slurm-based job managers. And when we see quantum, it works on QSKIT, QSIM, CIRC, and all those type of simulators. Now, how to merge all these things so that it works seamlessly? So this is the effort that we have taken. And we are trying to see, first we are developing a test bed where we can see all this type of transpilers, compilers, and all those aspects which can be merged together. And finally we have to solve a problem. Okay. And most of the problem domain people, they don't understand much about the supercomputers. They don't understand much of the quantum computers. They know that we need to submit a job and we want to get the answer. Let the area of drug discovery. Okay, so we want to know which is the best drug suitable. So based on that, we have to give a integrated, seamless environment where HPC quantum can work together to solve a problem. So this is a mandate that C-DAC has taken, and we are working. My colleagues are there, somebody then these people so with HPC. So they are working with us so that we develop a HPC quantum integrated solution system. Okay. We believe in the open quantum architecture, where the quantum computer development itself should be open, so that every entity has a space to contribute to it. Okay, if it is closed system like IBM is using, so then there is a very less chance to contribute. So we are building an open quantum ecosystem where quantum computer itself, from direction filter to all this software to electronics, they can develop collaboratively, and then we can have it as a open quantum ecosystem development that we are doing. So there are various opportunity in this area of quantum computing. We can, I think we have to involve each and everyone. We have to collaborate. That's why you can see we are doing it in Symbiosis, so that we can collaborate in the area of AI/ML in the quantum. So we have to collaborate. We have to come out. We have to talk with each other. And finally, these problems are too complex. It cannot be solved by anyone alone. We have to come together. We have to talk with each other, collaborate, and finally, we have to not only solve the problem of nation. We have to solve the problem of humanity. Because drug discovery and those areas are a problem of humanity. You can recently see in COVID, still we don't have medicine for COVID. Why? Because we are not having any powerful supercomputer, even the exaflop, to simulate this COVID drug molecules and to map all the drug to this COVID virus. So based on these things, we have drug discovery, AI-based things, cryptography, financial services. We have various candidates for building quantum computer. It is not a single, as we have already seen. We have quantum dots-based things. We have quantum photonics-based things. A good quantum computer will be that can provide a new computing power, opportunity, and curiosity to solve many problems. So finally, the aim is problem solving. And we must have some quantum computer application base libraries which will support both quantum as well as HPC together. So those library has to be built up from scratch. And finally, we give a total ecosystem where the problem can be solved in a HPC quantum integrated environment. So this is how we work in a quantum ecosystem where scientific research, we have to make a quantum algorithm repository, quantum accelerator is being developed by us. And then finally, we have to give the education, training, industry standards we have to follow. We have to give quantum interfaces. And finally, with the quantum simulators, we have to simulate all these applications on a HPC quantum integrated environment in a seamless manner. So this is our aim. Thank you so much. If any questions, maybe you can connect me offline. I'm available here. Thank you.
Thank you so much, sir, for such an insightful talk. To honor Mr. Amit Saxena, I would like to invite Dr. Archana Chaudhary, ma'am, for the felicitation. Our next distinguished speaker is Professor Joyce Ghosh, an expert in quantum photonics. She holds a PhD from JNU India and has held prestigious fellowships at ICFO NIST and University of Saarland, Germany. An associate professor at IIT Delhi, she leads research in quantum communication and light matter interactions. Professor Ghosh is a principal investigator for projects funded by DES QSet, DRDO, and SERV, and serves on the Joint Quantum Communication Working Group in ISRO and the National Quantum Mission. In July 2023, she presented on quantum communication hardware at the national meeting with the principal scientific advisor. Thank you, Professor Josh, for your contributions. We would like to invite you on stage for your session on trusted node-free secure quantum communication.
So good afternoon, audience. First of all, I'm Joy Ghosh, Joyce. I'm from IIT Delhi. And Amit, thanks a lot for this kind invitation. It's my first time in SIT and it's a beautiful campus. I have seen other parts of Pune. Actually, I've been to ISRO Pune several times and also in Ayuga, I've been invited several times. But this part of Pune is actually fabulous. And I also like the C-DAC campus and also SIT. So it's a pleasure. And thanks to Amit and the organizers for inviting me. So I'm going to speak about trusted node-free secure quantum communication. I understand this workshop is rather on, maybe the focus is more on quantum computation, but this is a little hatke. So, but it's all under the same quantum technology umbrella. So we work specifically on quantum communication, and we work both in free space as well as fiber-based technologies. And what we rely on is trusted node-free, so we don't have to depend on any particular node. So these are terminologies used in secure quantum communication, where you can successfully do any kind of communication between two parties, of course quantum mechanical parties, and do them in a secure fashion. So So I thought I'll just give a small overview. So already there were very good introductions given by Colonel Sai Sankar and also Shri Amit Saxena ji. And so I can skip a few of them, but I just wanted to show this particular slide. So these are international endeavors. This is from the group of Rupert Urson, and this is from the Chinese group of Jian Wei Pan. And they have shown a quantum communication network based on fiber networks, and part of this is also based on free space interconnects. So I'll just read up from the slide because a quantum communication network enables widespread connectivity for multi-user communication and secret key distribution. The scalability of quantum communication networks require compact, fiber integrated, easy to deploy and efficient WDM sources for multi-user QKD. Free space interconnects are also required, and quantum repeaters are required for long distance transmission, particularly in areas which are not suitable for fiber installation. So you need both free space links as well as fiber based, quantum communication network in order to do it for a wide scale network. So, and the work is underway to leverage trusted quantum satellites to enable end-to-end global coverage. So in this regard, an efficient multi-user source of polarization entangled photon pairs is actually a backbone for the establishment of such quantum communication network. So there are many more endeavors, and people are working across the globe in this particular, technology, and they have their own methodologies. But these are some of the, the ones that have been demonstrated very well. So what are the security considerations in quantum key distribution? So as we know, so quantum mechanics relies on the no cloning theorem, and so there are some other properties, and entanglement is also another property. And there are different kinds of QKD protocols. We can broadly classify them under two different umbrellas. One is the prepare and measure based protocols, which are the single photon based protocols. And some of these protocols are the very famous BB84 protocol, the B92, and there are several others, right? And some of the BB84 protocol, the single photon protocols, have been demonstrated very easily with attenuated laser pulses. And people have also the MESSIA satellite that I think Colonel Sai was talking about, and also I think probably it was also mentioned by Amit, right? One of the protocols that was demonstrated was the BB84, and also they have also demonstrated the entanglement-based protocols. Now, one thing is when the BB84 protocol uses attenuated laser pulses, most of these demonstrations were done with attenuated laser pulses and not with true single photons. Then they are prone to attacks which are called the photon number splitting attack and the intercept and recent attacks. Right, so there are other kinds, right? So it's always desirable to use a true quantum source for such kind of protocols. Now, the other umbrella are based on the entanglement-based protocols, because you can also do QKD with pairs of photons or pairs of quantum entities based on entanglement. So entanglement-based protocols are the two historically, the Eckert 91 protocol and the BBM 92 protocol. So BBM 92 is like a big brother for the BB84. So the BB84 is single photon, and the entanglement-based variant of that is the BBM 92 protocol. Now, why entanglement-based protocols are supposed to provide more security? It is because the true single entangled photon sources involve, so they are inherently random. There's a Bell inequality test which is involved in order to decipher entanglement and prove it. There's high security in the inherent randomness, which is a part of these sources. And they are resilient to eavesdropping. Eavesdropping attacks are those Ravan attacks that Colonel Sai talked about. So anybody who's trying to eavesdrop in between the entangling, partners, there's an inherent resilience of these protocols to that. And entanglement-based protocols can also offer long transmission paths. So if you tweak the one of the photons here, the partner or the entangled photon also gets affected, right? So in that way, you can actually offer resilience to eavesdropping, and you can also, because these photons can travel across spaces, they are like flying qubits, and there's actually no hurdles. If you ask about what is the limit for this transmission, there's actually no hurdle, but there's decoherence in the atmosphere for free space protocols. Then there's also fiber attenuation. So there's of course there's a limitation over the length with which you can transfer these photons. And in order to circumvent that, one can actually also go towards repeaters, quantum repeaters, and that's also a way ahead to go for longer distances. Then there is an inherent source independent security, and that makes it trusted node free. So if any node is attacked or any node collapses due to some problem, then the protocol still remains okay, and it does not particularly depend on the properties of that node. It becomes trusted node free in that sense. Now, everything is based on entanglement. So what is entanglement? There's already an introduction, so I will not elaborate much. But just, going back to quantum mechanics and what's the definition. So it's a phenomenon that occurs when a group of particles are in a joint state. The individual state of the particles are not well defined, but when the particles are in this joint state, that state is very well defined. That is the entangled state. And you cannot actually describe the quantum state of each particle. So you cannot actually write down this joint state in a separable manner, right? You cannot write it as products of individual states. So that's not possible. So entanglement is such, and as Einstein explained it, the phenomena can be explained as spooky action at a distance. So if you take the entangled parties, you separate them spatially, you take them away from each other. They are born and they are correlated out of some property that defines their entanglement. But now if you take them spatially apart, then they are still entangled, they are correlated, right? And so if you do something on one of them, the other gets affected. So this is a spooky action that occurs at a distance. And this was very bizarre for people who did not understand quantum mechanics or quantum entanglement initially. It took some time for people to accept this, but we see them now in the lab. We see them now for applications, as we know. So it's pretty much there, and it's a real phenomenon. Now it has many applications. Applications in quantum computation, for example, entanglement allows to enhance the efficiency of certain algorithms. Then, of course, it's pretty much the heart and soul of quantum secure communication, both satellite, free space-based communication, as well as fiber-based communication. Of course, as part of cryptography, it has a role to play in quantum key distribution, in the distribution of successful keys. And it also plays a big role in quantum networks, as I explained. So quantum networks typically consist of these quantum nodes and interconnecting channels. And you can actually interconnect different nodes sitting at very different distant locations through such entangled photons, which acts like flying qubits. So one of the photon goes to one node and the other photon goes to another node. And in that way, entangled photons can transfer their entanglement to the two nodes. So two nodes now, although they are sitting at different locations and they are not covering that distance themselves, the two nodes get entangled in this manner due to an interaction with an entangled photon. So just one technical slide on, there are different methods of classifying or characterizing entanglement and some properties. So you all can just Google that, or you can go back to some good textbook to read about them. But this is how we actually classify entanglement. So we classify through concurrence, through fidelity. How good is a quantum entangled state, an experimental quantum entangled state? How good it is to one of those popular Bell states. Bell state is one of those 4 maximally entangled states, which are out of bipartite entanglement. So bipartite means 2 parties entangled together. Now then there is also the very important S parameter, which is the CHSH Bell's inequality. So the S is restricted within an inequality less than greater than 2 and less than 2√2. So if it is more than that, I mean, if it violates that, any system that violates that inequality has prospects of being entangled. So that is what we also characterize for an experimental setup. A little bit more about the qubits. So there was already some introduction that was, I think, Amit talked about the qubits. So there could be different examples of qubits. We are passionate about photons. The main part of this slide is about photons, and there are different degrees of freedom, different properties of photons in which you can encode information. One being polarization, which is very popular. So there's horizontal, there's vertical polarization. So polarization, by the way, is dichotomic. So again, a two-dimensional property. So horizontal, vertical, or you can have diagonal polarization, so which is a superposition of horizontal and vertical, 0 plus minus 1, or circular polarization, which is again a superposition of horizontal and vertical. So any three of these, they can serve as mutually unbiased bases. And you need to prove entanglement in these three bases in order to show a successful, entangled system. Now, another property which is very popular, and it has a lot of, so there's a lot of work also in classical physics based on orbital angular momentum property of photons. Now, orbital angular momentum is actually a multidimensional property. So it's not restricted to two dimension, unlike polarization. So L is the quantum number, and L can assume any integral value, plus minus 1, plus minus 2, plus minus n, for that to say. And it tells you that photons, it's not necessary that we always think about plane waves, where the k vector, or the propagation constant of the photon, is in one direction. So these are special properties of photons whereby they have orbital angular momentum in which the photons move out in a spiral manner, or they either spiral out or spiral in. And based on that, you can associate the orbital angular momentum property. And the wavefront of these photons, of beams of photons, they are not plane parallel, so as to say. Right, so this is another interesting property, and it helps for high-dimensional quantum computing. It helps for high-dimensional quantum communication as well. A lot of studies being going on. Now there are others. So these are all about photons. Then there are, as we know, there are also two-level atoms, electronic spins. There are superconducting qubits, and many other systems out of which you can have a qubit and you can encode quantum information there. Now, we are talking about entangled photons and entanglement, right? So one of the workhorse technique to generate entangled photons in the lab, and also for any of these applications, is spontaneous parametric down conversion, which is a nonlinear optical technique, a second order nonlinear optical technique, whereby you incident such a crystal. So this crystal needs to have a non-zero chi2. Chi2 is the second order nonlinearity. You incident it with a pump photon. The pump photon splits into two partner photons, signal and idler. Now, these two, signal and idler, are the two photons which we want them, which we can entangle, which sometimes when they are produced, they are entangled. So there are different experimental techniques to have them entangled, or get them already entangled from the crystal. So anyway, so this is the workhorse technique to generate such entanglement. And this technique, of course, follows energy conservation and momentum conservation. And there are different kinds of phase matching, more details, technicalities there. But you can have different kinds of entanglement possible, entanglement of signal and idler possible through such technique. One such example is given here. So this is one of the Bell states. So if you're encoding in the polarization property of the photon, H is the horizontal and V is the vertical, S and I are signal and idler. So when the signal is horizontal, the idler is vertical, or vice versa. And if you can write down the joint state of the photons as such a state, then you have achieved polarization entanglement. Now there could be different variants of this state. You can also have a plus. You can also have HS, HI, and VS, VI. Right? So there are different kinds of states possible, and those are the 4 Bell states. Depending on your experimental technique, you can actually have different kinds of protocols. Now, there is one way to understand the correlation of the photons. Sometimes these pairs of photons are correlated, and that's good for entanglement. So when they are correlated, this is known as a joint spectral intensity pattern for the joint state of the photon. When it is an inverted, like it's a negatively tilted ellipse like this, we say that the photons are correlated. And when it's a circle like this, or maybe it's a normal ellipse, then the photons are mostly uncorrelated. Now, different pairs of photons with different properties have different applications. For example, when they are uncorrelated photons, when the signal and idler share a space where we can say that they are uncorrelated, they can actually act as a heralded single photon source. They're good. And the spectral purity is very high for that. For entanglement experiments, mostly the photons are highly correlated. So anyway, technicalities. So this is one picture I like to flash. So this shows two different setups to tell you that photons can be entangled in free space, but they can also be entangled in a fully fiber integrated setup. Right. So these are the two pictures, and there are different kinds of entangled states that you can have them onto. So it's in free space, fiber-based, and so with that, I come to our slide, our group slide. So we are the quantum photonics group in IIT Delhi, and our group works in different regimes. The most interesting part, which is probably here for the audience, we work on both fiber-based quantum communication as well as free space quantum communication, and we also have interest in silicon nano waveguides to again produce correlated and entangled photon pairs. That's silicon actually doesn't have chi2, it has chi3, which is the third order nonlinear process, and the process is called spontaneous 4-bit mixing. So our group is also exploring that. And apart from that, we are also interested in coherent light matter interaction, quantum detection based on squeeze light, etc. So this is our group, and all students, and this is really the workhorse behind the quantum photonics group. Not elaborating more, this is just snippets from our lab, very old pictures from our lab, and this is the table that shows the fiber integrated source, the free space source. Now they are much bigger, and they actually occupy different tables. Now the lab looks really different. So now coming to the work, so we work both on quantum like free space as well as fiber based. Now the two broad directions for quantum communication are in the optical band, where people target this wavelength. So between 700 to 850 nanometers, most of the demonstrations for free space quantum communication have been in this range. And here the sources and detectors are pretty well developed. And these are basically the free space optical and satellite communication, which connects several places on the globe. The other regime where people like to work is the telecom band, which lies between 1400 to 1600 nanometer, 1550 being one of the most popular parts, the one of the most popular wavelengths, and around it, the covering the S band, the C band, the L band, all of that. Here again, the sources are pretty well developed. The portable detectors are not so well developed, but there are high efficiency SNSPD detectors, which are very efficient, and people utilize them. Excuse me. So based on this fiber communication network, one can again, connect different parts of the globe. So particularly, I'll be first focusing on the free space part and our group's work in that. So we actually have a project with DRDO, and we work on free space quantum communication. So we have actually experimentally in the lab, we have developed a bright source of narrowband polarization entangled photons from a thick type 2 PPKTP crystal. This is a very simple picture of the setup. Here we actually incident with the UV light. This is the PPKTP crystal, which in which SPDC takes place, which produces the signal and idler photons. We can image the photons through the EMCCD camera. We can also pass through and project them onto an entangled state. So this is a beam splitter, a 50-50 beam splitter. And then on each arm of the beam splitter, we have single photon detectors and polarization analyzers to analyze the quantum joint state of these photons. And then you have, through the method of coincidence detection, we actually project the photons onto this particular state. So this is how we characterize entanglement. So this is the 2-photon interference experiment that you do. So based on different settings of, so if you can imagine that this is Ram and this is Lakshman. I'm not calling it as Alison Bob, but those are the popular names. But if you can imagine that this side is Ram, signal, and this side is Lakshman, which is the idler. So we want a communication between them. So first we have to entangle them. So these are as a function of different settings of Ram. You scan the settings of Lakshman and you get these two photon interference experiment. So this is a signature for entangled, partners or entangled state. Once you have these two photonics like interference experiment successfully, then we go on to measure what is known as a quantum state tomography. And so this is the quantum state. I really have to get into the quantum mechanics of all of this to explain, and that will take more time. I will not have the time actually to go into that. If there's a question, please ask me later. So recently, not so recently, actually last year, we have also demonstrated the BBM92 protocol based on this source. It's a powerful source because although it is type 2, the brightness of the source is about 10 to the power of 6, 10 to the power of 5 photon pairs per second per milliwatt per nanometer. And that is a way you try to characterize or you talk about the brightness of your source. And we have done the BBM92 protocol in which, again, so this is the entangled photon source based on the PPKTP crystal. There are 4 single photon detectors on each side. So there are total 8 detectors. So this is the Alice side or the Ram side, and this is the Bob setup or the Lakshman setup, let's say. And you want to send a key from one party to another. So that's the QKD experiment that we did. And we got a very good QBER, as you can see. So this is the qubit bit error rate as a function of this QKD experiment. And so this is a function of the pump power with which we are incidenting on the crystal and in order to crank up the photons. And we can go up to about 30 milliwatts, and we are still below the threshold of 11% for the QBER. Now, this project is actually part of a bigger objective whereby we are targeting, because we want to combine ultimately not only polarization, we also combine it with orbital angular momentum of the photons, and we want to do it in a fashion such that the entire setup becomes alignment free, or rather rotational alignment free. Now, what is the and anti-diagonal. So you would, if it is in one reference frame, then there is no problem. The information goes exactly. But if there are 2 reference frames which are not, they are moving with respect to each other. And a typical example is between 2 satellites. So one satellite can rotate with respect to the other. So when I'm sending out photons from one satellite in terms of H and V, when it goes and reaches the other satellite, maybe that satellite has turned. So the H and V information, when it gets received on this other satellite, that has now gotten distorted because the HV is no more HV, right? So particularly for communication between 2 parties that do not respect or do not have a common reference frame, which could be in many of these applications, there you need to, so encoding information in terms of polarization becomes a little bit dangerous. So with the smart involvement of orbital angular momentum, in addition to polarization, you can actually encode information in rotationally invariant logical qubits. So qubits that irrespective of rotation, they will remain unaffected, right? This is something that we do in this particular project based on that PPKTP source. And recently we have demonstrated again QKD based on that. And we have shown the rotational invariance of this particular protocol. So this is the rotation. So this is the Alice side and this is the Bob side, or Ram and Lakshman side. And in one of these is on a rotational stage. So as a function of that rotational angle, we actually try to see what is the entanglement, fidelity, what is the S parameter, what is the QBER, etc. So when you encode, so the blue points are actually the hybrid qubits, which are in terms of this logical encoding through orbital angular momentum as well as polarization. And the black ones are just purely based on polarization qubits. So as you can see, as a function of the rotational angle, the S parameter for the blue ones, when we are based on these hybrid system, hybrid entanglement, they remain intact. Similarly, the fidelity is continuously high and about 95% for the hybrid qubits. But for the polarization, as you rotate the stage of RAM, let's say with respect to Alice, as a function of that rotational angle, the fidelity drops, which shows that your protocol, which is dependent on polarization, will fail when you have one of these parties rotating. The stage is rotating. Similarly, for the qubit, for the polarization qubits, the qubit rises up and it is not lucrative. Of course, that's not what we desire. We want the qubit to be as low as possible and always below the threshold of 11% for particular to this protocol, which is BBM 92. So when you're entangled in the hybrid qubits, then irrespective of the rotation angle of one of the stages, the qubit remains within 6 to 9%. That's what we have seen. So I will skip some of these details and go directly to the fiber-based part. Last 5 minutes, 6 minutes or so. Yeah, okay. So in the fiber-based, we have different endeavors. So we have different setups. In the free space also we have different setups, but I was only focusing on one. So in the fiber-based setups also there we have a few of them, and we believe in doing everything all fiber integrated. Right, so this is a type 2 source, type 2 entangled photon source now. This is just a small characterization here. But right now we have actually seen entanglement in actually different kinds of states that we have seen out of this particular setup. And this is based on type 2 phase matching. Type 2 means the signal and the idler will always have orthogonal polarization. Type 1 and type 0, they have the same polarization. So you can actually, you can have different kinds of entanglement states based on these different kinds of phase matching. Those are again technicalities. So I'm just skipping one of these and coming to the main piece of work, which is where we have done QBER again, QKD and QBER. So this is again an all fiber integrated setup. It's an all fiber integrated broadband source of entangled photons at telecom C and L band, and it is based on type 0 SPTC. Again, type 0 SPTC, signal idler, both have the same polarization. So there are different kinds of entanglement states that you can think about: HH plus VV or HH minus VV. For example, let's say if you're talking about polarization entanglement. This is a setup that is on table. There's only one reference frame. Here we bank on polarization entanglement again. And this is just a small picture. And with this particular project, actually there's a project with the DST Quest, and this project is now over because we have demonstrated all that we promised. And this is a project that talked about multi-user QKD. So instead of a single RAM and a single Lakshman, you can think about multiple RAMs and multiple Lakshmans, and you can have communication between them. So for a bigger communication network, as we all know, for the scalability and everything, you need multi-user systems and not a one-to-one user only. Right? So this particular project talks about that. So there is an entangled photon source, but there are multiple RAMs and multiple Lakshmans between which you can have communication. And all of that is quantum communication. And the first step to show that is doing a QKD with this multi-user setup. So I'll just skip this particular slide. These are all characterizations of the source. The source, by the way, is extremely efficient, and it has a spectral brightness of about 10 to the power of 8 pairs per second per milliwatt per nanometer. So per nanometer of pump power with which we are shooting in, we are incidenting the photon, the source produces 10 to the power of 8 pairs, which is per second and per nanometer of bandwidth. So all these sources have a broadband, right? So it's per nanometer that we are trying to focus on. As you can see, this particular picture, this is an experimental picture. The blue line is a theoretical fit to it, and this shows the spectrum or the bandwidth of the photons that are emitted from this particular source. And it goes from so 1520, so about 1510 to 1560, 1580. So it's about 50 to 60 nanometers wide, right? So and it's extremely it's a very efficient source. And This is again, so this is actually the J side. If you recall, I talked about many things. So, but one of the things I talked about is that inverted ellipse for to show that whether the photons are correlated or not, the joint spectral intensity. So this is an extremely very fine ellipse that shows an inverted that shows that the signal and idler photons here are highly correlated, and they're correlated throughout this entire band. This entire band is 1520 to 1580. So about 60 nanometers range of photons, all of them, the signal idler, they are correlated to each other. Of course, with the conservation of energy, conservation of momentum, all of that. Now coming, so this was the basic characterization of the source, the properties of the source with all that. And then we wanted to entangle the photons. So we put them in a C-DAC interferometer like this. So this is more details about the setup. And what we have today is an array waveguide grating to portray this multi-user, picture in which the C band idler and the L band signal, for example, they are now channelized, and with the help of such array waveguide grating, and you have several signals and several idlers, and there is a multi-user kind of a setup here based on C-DAC. And then again, this is a characteristic of our entanglement. So this is for the broadband entanglement, where you take the entire C as one and the entire L as one. So there's one signal, one idler. They are very broadband, each of them. And initially, we just classify that broadband polarization entanglement. This is the entangled state, and these are the characteristics, the fidelity and visibility, all of those are pretty high. And then we wanted to do C entanglement in a single channel. Now we split that C band into several channels, and we split out the L band also in several channels. And then we take one channel of the C and one channel of the L, and we want to characterize the entanglement. So the number of photons, of course, in that channel has decreased, but we want to see if the quality of entanglement is good or not. And this we here is a slide to show you just one of these characteristics. We have actually characterized 16 such channel pairs, 14 such channel pairs. Right? So again, this is the entangled state between for that single channel. And this is a 2-photon interference experiment. So these are actually the signatures for doing any kind of entanglement experiment. And the CHSH bell parameter is more than 2 for sure. It's 2.33. And the fidelity of this broadband source is about 85. These numbers are a little old. This is much better now. Now we have more than 90% for the broadband entanglement. For the single channel entanglement, initially we just tested for 3 channel pairs, and we got fidelities very high, concurrence is also high, and high S parameters. And these 3 channels were somewhere close to the degeneracy point of 1550 nanometer. So these are channels around the 1550 nanometer. But in principle, you can actually utilize this entire bandwidth of 60 nanometers, and you can do many channels. It could have many channel pairs, means many user pairs. So multi-user, it can go up to easily 30 pairs of users. So this is something that's published. If you all are interested, you can go back to these references. Anyway, our website is there in IIT Delhi. So the quantum photonics group, if you Google by name, you will get all the details of all these publications. So recently, actually, we have done, so utilizing the source, we want to just see, because everything is based on fiber integration. We want to just see whether long distance transmission is possible or not. So we utilize different fiber spools, and these are fiber spools which are, so we tested different kinds. We tested 10 kilometer, 20 kilometer, 50 kilometer. Now we have also done 100 kilometers. And just to see whether the entanglement, whether the QBER, all of those things remain intact or not, even after propagation of 100 kilometers. Right? And this is the multi-user entanglement-based QKD network up to 100 kilometers using all fiber integrated WDM-based field deployable telecom band tunable entangled photon source. So this is one of the patents that we have also applied, and the paper is under review currently. And this is the fidelity of the entanglement that we see across these single channels, and we have characterized 14 channel pairs, as I mentioned. these are some of the numbers that we obtained as a function of the different fiber lengths. For example, if Ram and Lakshman each have 50-kilometer fiber spools, right? So this is the coincidence rate. This is, you can see it is like sort of the raw key rate, okay? And it's 24 per second. The numbers look very small because we have detectors, single photon detectors. So these are raw key rates, which is after what the detectors have given us, the numbers, right? But these detectors are only 10% efficient. Right? So if we have SNSPD detectors which are 95% efficient or more, these numbers would go up to kbps. So this is just an artificial thing. The source is much, much stronger. The source is very bright, but the detectors are not that efficient. It's only 10% efficiency, and that's why these numbers look small. So SNSPD detectors would give us about kbps, about 7 kbps or so. So these are the fidelity and the concurrence, and this is the QBER. As you can see, the QBER is much below the threshold of 11%, and so this is a fantastic source based on multi-user QKD. And so both have 50 kilometers, and that's the fidelity that we obtain. Then at Alice's side, we have a small 2-meter fiber, but at Bob's side, you have a 50-kilometer fiber. Then this is the fidelity, and this is the rate that we obtain. And then at Bob's side, we have a 100-kilometer fiber. So these fibers actually, of course, so when photons are propagating through a fiber, they get attenuated because of the fiber dispersion. And so it was also important to do study polarization mode dispersion of these fibers, because we are doing polarization entanglement. So H and V actually travel with different speeds inside a fiber, inside a medium, and all of that. And so all those things had to be tested. We saw that, and with the use of PM fibers, of course, this protocol doesn't work, and nobody uses actually PM fibers. The way to go is with single mode fibers, which are non-polarization maintaining, because you're trying to do polarization entanglement based QKD, and so on. So, right. So, yeah, I think I would stop there. No time to talk about silicon photonics. That's another regime where we work based on that. So everything all integrated, but this is all kind 3. This is also a direction where we are working, and not recently, 2 years back actually, we have shown our design techniques to actually generate entangled photons directly from such silicon, integrated silicon on insulator platform. Right, and now we are actually starting our experiments also, because we have silicon nanowave guide chips, and we are trying to see if we can generate photons out of them, pair photons out of them, and the way to go is to also generate entangled photons out of them. Questions?
First of all, I thanks for this is a great talk. So I have a question that you said that sorry. Okay, so can you just explain more about how entanglement increases the efficiency of algorithms?
Entanglement increases, so that is really about quantum computation. So that would be a technical question actually. Yeah, maybe Amit would be able to answer that better, because I actually the speed of certain algorithm, I would say, right? Or certain algorithms which can be cracked by entanglement, maybe made more. Yeah, I don't have. I don't want to say something that's not technically sound.
So you have studied the entanglement for the photonic-based qubits. Yeah. So there, if you identify the entanglement, sudden death, and birth, have you observed during your experiment or observation? Entanglement, sudden death, like entanglement is
there,
but it is missing at some point, and again suddenly it is taking rise in the entanglement. It's like I have gone through some research papers. There I have seen the work, like they are talking about entanglement, sudden death, and birth patterns observed in the experiments. Have you studied these things in your?
No, actually we have not studied, and we have seen our setups once they are entangled. So our entangled photon sources, there are multiple now we have in the lab, both fiber-based as well as free space. And particularly for this aspect, actually we study it over hours. So we have studied it for 8 hours, sometimes throughout the night, and we take measurements, and once they are entangled, they remain entangled. unless there's some disturbance. Maybe, I mean, I don't know if anybody else can comment on that, but particularly we have not actually looked out at entanglement sudden death. Maybe, yeah, Nandita, they want to say something? Okay, yeah. So the sudden death thing, I don't know, I have to, look at it. But we actually don't want our systems to die. We want the entanglement to remain intact, and that's why we have also done. So I went through the technical slides pretty fast. One of those slides actually had a real-time measurement. So for 6 hours, for 8 hours, we just kept it, and we just measured it in between. And we saw the fidelity was always above 90%. So, and we want it like that. So when we are doing a quantum communication, we want the entanglement to be intact. And we would do anything so that they are alive. And there's no sudden death.
Yeah, actually some research is saying that during the experiments, it is happening, like entanglement sudden
Have
death
to read more about it.
there. And again, the entanglement birth is also there at certain stages. Why even concurrence is study of concurrence is also saying these points. So that's why I
Okay. Good to know. I'll check that out. Yeah.
So, ma'am, please.
Thank you for the presentation. So, Dr. Joy, being an experimentalist, I wanted to, you can tell me what was your thought process in selecting a BBM92 QKD protocol, not an ECRT91?
ECRT91, at every step when you're doing the QKD, I think you have to measure. One of the steps is to measure the S parameter and then go ahead with the QKD. Right? So for BBM92, I think that step is it's saved. Right? For BBM92, you of course you have to prove and verify that this is an entangled photon source, and then you can go ahead with the QKD. That is one thing, and BBM92 is a little easier also. The
next question is, you had mentioned about polarization hybrid.
And I think, sorry, coming back now that I'm thinking, the ECRT91 also asks you to do it in those 3 mutually unbiased bases. If you're doing polarization entanglement, for example, right? So I think you have to choose your basis. So for BBM92, we choose the HBDA. Now we don't need the circular basis, right? But for ECRT, I think you also have to show for the third one.
So it's easy for implementation.
Yeah, for implementation, yeah, people do it as BBM. But if BBM92 has been done on setup, right? Then ECRT91 is also doable, of course, with some more thoughts and some more planning.
And when you spoke about hybrid entanglement, then you use the polarization and orbital angular momentum.
Yes.
So when you're deriving the secret key or the secure key, are you using either one of them or a particular?
No, both of them.
Using both of them.
So the secret key or the encoding information is not just in terms. Can I go back to that slide? Do I have a few minutes? Yeah. So this slide, actually, I didn't have enough time to explain. What we are encoding is through these logical encoding. Yeah, logical qubits. So this L and R, they are, so the 0. So this is, this capital and capital R, let's say the right circular, left circular polarization, right? And this small r and small l, this is the orbital angular momentum with opposite handedness, right? So you have, let's say a right circular polarization has half H cross, and you have a particular way, right? And the L equal to 1, is a handedness in the opposite way. And we try to interconnect, we try to combine them of opposite handedness. So let's say the right-handed one and the L equal to 1. Similarly, the left-handed one and the L equal to -1. Okay, so that way we do it, and this handedness, so whenever there is a rotation of the photons, right? So this is encoding in the total angular momentum property. You can imagine the polarization of the photon, whatever polarization, that is the spin angular momentum, right? So right and left circular polarization have a spin angular momentum which is equal to half H cross. Similarly, the orbital angular momentum can have ±1. Right. So, and based on that, plus minus half. So those are the technicalities. but they are like opposite. If you can combine them in an opposite-handedness manner, right? Then this whatever is the rotation, that the spin part gets affected, but the orbital angular momentum part gets affected in the opposite manner, right? So they compensate each other in a way, such that when you try to encode in the logical bit and you try to also decipher information, encryption and decryption in the logical qubit, then everything remains unaffected. That's how, as a function of the rotation angle, we were rotating the stage actually, but we took this information, and after so this hybrid system is there, and then irrespective of the rotation angle, I mean, one gets affected, the other does not get affected.
And you mentioned that the fidelity is about 5 to 6%.
The QBER.
QBER is 5 to 6%.
Fidelity is very high.
Very 90.
Yeah.
So,
the polarization entanglement also, fidelity was very high to begin with. But the moment we started rotating the stage of Ram, for example, because this is entangled photons, right? Lakshman is in one stage and Ram is in the other stage, and you're trying to rotate the stage of Ram. Then the polarization entanglement, whatever fidelity, QBER, everything started falling down.
What is the trade-off you have observed in terms of maybe
when we go from polarization to hybrid?
Yeah, from polarization compared to hybrid, the throughput, the security rate, or the generation rate remains the same, or?
So the hybrid one is resilient to any kind of rotation. The polarization one is not. The polarization entanglement, and based on that, the QKD, that the parameters start decreasing. Okay, as a function of that rotation. But what we understand, one thing, if you can ask me that if there is any cons to this. So the number of photons, the polarization entangled source, of course, is a little brighter compared to the hybrid entangled source, because it also has to go through these orbital angular momentum manipulators, which we use as part of the setup, right? In order to have this logical encoding. We do the encryption and decryption in terms of this logical encoding, which is the total angular momentum of the photons. Okay. All right. Yeah. Maybe we can talk more about this. Yeah, if you're interested. Yeah.
Have you characterized noise like free space versus?
That's a very good question. Yeah, because whenever we talk about free space propagation, and particularly orbital angular momentum, right? So there we know that there is atmospheric turbulence, right? And there's also noise, right? There's photon loss and all of that. So we have run our simulations, and we have now of course, we have to use one thing we understand is we have to use better detectors with very high efficiency. We have to use probably better alignment techniques if you want to go to long distances, and you also have to incorporate or take the effect of atmospheric turbulence. So better to do these experiments where turbulence is low. So particularly OM part of the photons also get affected too. So we have our simulations now. So for not very long distances, the OM is okay, but I don't have the numbers right now or those slides. We have done our simulations, and we also have a small chamber with which we try to see it. And we can also see it through spatial light modulators. So you can mimic atmospheric turbulence and see, how long your photons are capable of, communicating in free space, and so and so. So of course, all these noise have to be taken into account when you're doing a real space thing. For the moment, the demonstration, the free space part demonstration is within lab, and we are planning to have it outside very soon.
Do you have some mitigations associated with that, like the information?
Yeah, it has to be. Yeah, it has to be. So of course, one of the main things is to make your source as bright as possible, so that even if there is some turbulence, even if there is some decoherence, some distortion within your channel, channel losses, there could be different kinds, photon loss. Then also you're remained with, so some keys or some photons remain intact, right? So to start with, so you also have to crank up the photon number for such a source.
And one last question, a very general question. When we talk about sending an entangled photon from a ground station to a satellite, so what are the constraints? There's a lot of distance to cover.
There's a lot of distance to cover, but the atmospheric turbulence is actually in a small narrow belt. So if you're going up or going down, you're going through this. better probably to do downscale, what I have learned now. But anyway, nevertheless, whether you're going up or going the communication from top to below, so you have to just cross that boundary of the turbulent layer. And after that, actually, it's not so bad. So that's a narrow layer around, so in the atmosphere.
So you have a carrier signal that kind of depends
Yes,
on the
yes,
penciling.
sure. There's a beacon laser, there's a carrier signal, and yeah, all those things are there. I mean, one has to.
That is tweaked to kind of cross those layers.
Sure. In order to guide your actual photon beam, right? That is necessary. Yeah, all those things are necessary. So, yeah. More questions? Yeah.
Well, while going through that layer that you're talking about, and do you think what the man just asked that may happen?
Entanglement there?
Yes.
I really have to,
But,
go back and check this out. Yeah,
I haven't experienced.
So right now we do it in the lab, and we also do it. We are planning to do it. So we have done some small bits of experiments outside the lab, but we have really not gone up to space. Yeah, so that we don't know. But I mean, we can study about it before doing the actual experiment. So I have to really understand this sudden death and all. If you ask me, I would not like a sudden death, right? But if it's actually happening and what is the reason behind it? Like something, some noise, some turbulence, some loss, I can imagine, right? And the loss is so heavy that it has killed, ultimately any signal, any entangled signal that is there, that I can understand. But apart from that, what is this sudden death and what could be the reason for that? If it is not source driven, then I don't understand that. So right now, it's not clear to me. I have to go back and check.
So my guess is like you have another photon getting entangled and that's getting passed on.
No, so it may be because of noise.
No.
Photons don't interact so easily, right? They don't interact so easily, and that's the beauty. That's why we call them so robust. Decoherence is something I understand, right? Then
Entanglement, sudden death, maybe different context or different application area, maybe black body radiation.
yeah, that's different. Yeah.
It's not
So for
application.
communication, actually, we don't. Yeah.
It's decoherence.
Decoherence is something that I can understand, but then I don't know why it's called sudden death. Gradual death due to decoherence is something I understand. Okay, so my ignorance, I have to go back and check this out. Yeah. In the lab, actually, it's a tabletop setup. So all these QKD experiments, this one, and also this is 10 by 15 tips. So there are two huge tables, and we have them. So and this is a rotational stage that we can turn as a function of that. And then everything is connected. So you actually so this is actually connected through a fiber. This is all in free space. So we can very easily actually increase this distance. It's nothing. By reflection of mirrors, you can actually have 10, 20 meters within the lab. But right now we haven't done that reflection of mirrors. It's just that there will be some photon losses and nothing else. It's very easy to do. More questions? Yeah.
First of all, thank you for the presentation. So next thing is in your multi-partite communication.
Multi-user.
Multi-user, sorry. So,
Partite.
So were you creating a multi-partite entanglement?
No, that's what I'm saying. When you say multi-partite, so it's not multi-partite. Multi-partite would be a big entangled state, and we are doing bipartite entanglement. Be clear about this. There's no confusion. Bipartite entanglement. So the entangled photons are always two together that they are entangled, not multiple photons are entangled, right? But we are doing a multi-user QKD. So there are bipartite multi-user. And that's why, so there's, let's say, round 1 talks to Lakshman 1, round 2 talks to Lakshman 2, round 3 talks to Lakshman 3, and so on. And this is around the degeneracy point. The degeneracy point is at 1550, but the photons are very broadband, right? So they are about 60 nanometers wide. So around 1550, you can have narrow channels. So let's say 1551 and 1549 could be 2 channels. 1556 and 46 could be 2 channels similar.
So is that going to be the spectrally or spectral? You showed the ellipse. I think it was,
Yeah.
it was correlated, spatially correlated. Yeah.
Spectrally correlated.
Okay, not spectral.
Spectrally correlated because the x and y axis of that particular plot is signal wavelength and Eitler wavelength of the photons.
So each frequency of photon frequency is sort of entangled.
Yeah.
Correlated.
Can I go back to that slide? Yeah. So that, by the way, that's another JSI. That's another JSI, but it's a different kind of source. And it's a smaller bandwidth source. Yeah, this one. Right? So here actually the degeneracy point is somewhere here, 1550. That's the strongest signal and Eitler we thought. But since it is so broadband and there is like a plateau for this band of photons, right? It's a beautiful source that way. So, and therefore all of all these lit points are actually coincidences. And around 1550, so this is let's say 1560, but it is 1540 for the Eitler. So they are all, I mean, of course, conservation of energy is there, right? So that's why it's an inverted ellipse and inverted at 45 degrees because it's, same polarization of photons and you don't degenerate photons.
Maybe I'll ask questions later. Thank you.
Yeah.
Later on.
But it's not seriously
Is that the reason? Is that the Make it close it.
Maybe it's still shared.
Thank you, Professor. Thank you, Professor Ghosh, for sharing your profound insights. Your expertise has truly deepened our understanding. To honor Professor Ghosh, I now invite Mr. Amit Srivastav, Scientist E at C-DAC, to join us on stage for felicitation. Ladies and gentlemen, we now have a lunch break. Please proceed to the 4th event. We look forward to seeing you back for the afternoon sessions commencing from 2 o'clock. Welcome back, everyone. I hope you all had a refreshing lunch break. As we continue with our program, we are excited to bring forth more distinguished guests who will share their insights on the advancement of quantum computing and related fields. Our next distinguished speaker is Professor Arindam Ghosh, an experimental condensed matter physicist and professor at IIC Bangalore. He is renowned for his pioneering research in quantum transport and low-dimensional systems, which have significantly advanced our understanding of quantum phenomenon in nanoscale materials. Professor Ghosh has received prestigious accolades for his contributions to physics, including the Shanti Swarup Bhatnagar Prize in 2012 and Infosys Prize for Physical Sciences in 2020. His groundbreaking work has been substantial implications for the development of advancement materials and technologies, solidifying his reputation as a leading figure in both Indian and global physics. Thank you, Professor Ghosh, for his significant contributions and for being here with us today. Let's welcome him on the stage for his session on emerging and future materials and device platforms for quantum computing and associated technologies. Thank you, sir.
I told that I'm here. Okay, but I'm sure you can hear me. So I'm going to first thank Amit, C-DAC, for inviting me here. It's very nice campus. The short time that I've spent here, and this is the first time that I came. So I'm Arindam Ghosh. I'm from the Indian Institute of Science. I'm going to be talking about on materials for quantum technologies. I'm not sure what happened in terms of introductions in the first half of this workshop, but I'll try and keep a low profile on the introductions, but try and say what's new in the materials that will lead to new hardware system for quantum computing, and very importantly, take quantum computing beyond quantum technologies, beyond quantum computing, and I'll show a little bit about what's happening in sensing, communications, and other systems. Okay, so I'm sure you have this, you have had it since morning. So quantum technologies, of course, come because of the second quantum revolution, probably since the 1980s, when we first started engineering our understanding of quantum mechanics. That was built over the last nearly 100 years. What we can do now is that we can engineer some of our basic understanding of quantum entanglement, superpositions, and measurement. And with these three, we can get new functionalities, which are simply impossible in classical devices. We can get devices with extremely high sensitivity and speed. So these are the three major directions that quantum technology is aspiring to achieve in the next decades. Superposition, I'm sure I don't have to say anything about it. Because of the quantum, the superposition, our Hilbert space is significantly enhanced, and this leads to certain exponential speed ups in certain number of applications. Then measurement, when you measure a quantum system, it collapses into a particular state, and again, that's one of the key features of quantum physics. And entanglement. Now, at this point of time, I'll digress a little bit and show you, okay, quantum entanglement is something that is at the core of quantum computing. But how do you see quantum entanglement? It's actually very difficult. So, and it's not an easy concept to visualize because you cannot do so. So I'm going to give you an example. I deliberately took this example from quantum sensing domain. So for example, you have an apple and you want to measure the size of this apple. Okay? Now what you can do is that you can take a scale and you measure the apple. Fine, very good. In order to make this sensitivity or the accuracy of the apple size better, you can make many measurements. You can make second scale, you can make third scale, and as you keep on adding scales, at some point of time, a classical average of the size will definitely be more accurate. So what you do is that you get a standard quantum limit, which is essentially the error in the determining the size of the apple is given by the length that you measure in a particular with a particular scale and over the average of it, and then square and take a square root to get the standard deviation, and you get a number which varies with 1 over square root of n, where n is the number of times you have made the measurements. Now assume a situation where these scales are quantum mechanically entangled. Right, so let me just check. Yeah, so if these scales are quantum mechanically entangled, then we have a different measure, which is called the Heisenberg limit of the error, in which the number of, or the error in the measurements go as 1 over n rather than 1 over root n. Now imagine a situation in which you have got very large n, say photons, 10 to the power of 6 photons, in which case now the accuracy of making these measurements will be about 1,000 times better than a standard classical measurement. So this is the core concept of quantum sensing that people use, where the quantum entanglement helps us doing measurements in a much better and more accurate manner, which immediately gets applied not only in one field, but across many fields like biology, like medical medicine, diagnosis, and so on. So this is one of the main reasons why quantum technologies are being looked at as a potent technology of the future. Well, if you want to do quantum computing or communications or metrology or sensing, materials come at the center. You need to build your own material for doing quantum technologies in a more reasonable way. What can quantum technology give us? I'm guessing that this has already been flashed by your previous speakers in some way. Of course, quantum technologies have got very large number of domains in which it's supposed to get applied, not just in quantum computing. For example, you have got ultra precise clocks, simulators, which can lead to new drug designs, for example. Sensors, I just gave you an example. Example of sensors is oil and gas exploration to look for oil underground, or you can have plate tectonics, movements of continental plates in a very accurate way, because that changes the acceleration due to gravity by a very small number. And measuring small changes in the acceleration due to gravity, you actually can predict various geological phenomena. And in addition to that, even astrophysics or cosmology, in which you want to detect the gravitational waves, LIGO is already using quantum technologies to measure to detect gravitational waves from black hole mergers and various others. So that's a sensing compartment of quantum technologies. Medical imaging, for example, nuclear magnetic resonance. We know NMR machines are large and you have to go inside a huge magnet to get your brain imaged or various other parts. But if we can have a sensitive detector of signal, we can actually do NMR or those kind of imagings in a much simpler and cost-effective way. So this is also one of the major directions in medical imaging for quantum technologies. Quantum communications, of course, quantum key distribution for hack-proof communication protocols. And last but certainly not the least, the quantum computing, which machine learning or artificial intelligence and several other directions are becoming more and more important these days. Okay, that's overall. Quickly, the qubit, everybody knows by now, so I'm not going to spend time at all. A quantum two-state system in a cavity, that's a generic form of a qubit. Typically, this James Cummins Hamiltonian, where this is the state of the qubit, and this is the coupling, and you change this. Using this, you can change the state of the qubit. If we look at the main qubit today, this is the superconducting transport qubit. Those of you who have not seen a superconducting quantum processor, it essentially has this kind of a structure. This is the cavity, which is aluminium usually. And then this is Josephson junctions inside the aluminium cavity, which is addressed by using microwave radiation. However, and this is where I should start going beyond a particular system, while IBM has certainly laid out a wonderful roadmap for the futures to come on how to increase the number of qubits in quantum processor, there are competing technologies, and we must be aware of what the competing technologies are, because one of the key aspects of or unique aspect of quantum technologies and computing, including computing, is that there is no winner yet. Yes, the semiconducting processors have a head start, but that doesn't mean 5 years to 10 years down the line, that's the one which that technologically will become most viable, something that will have millions of logical qubits. That aspect is still not clear. As a result, if you look at the stress that's happening globally today, this is quantum superconducting qubits. You have, these are the companies which are putting their money on in superconducting bits, IBM, Rigetti, QSim, there are several. We have good gate fidelities, but requires gradually cooling. Their coherence time is still short. So there are both positives and negatives in all the technologies that we have today. For example, the next one is semiconducting quantum processors. Again, there are, you can see the number of companies which are developing semiconducting processors, from Intel to silicon quantum computing, quantum motion, Dirac, several. Advantage of silicon quantum computing or semiconductor quantum computing is that you can use the processing facility that is there in these computers. So that's a huge advantage of miniaturization as well as fabrications. Trap time is probably one of the forerunners as well, actually. So you can see IonQ, you can see Quantinuum, several companies already there looking at trap time based superconductor or quantum processors. Neutral atoms, for example, long coherence times is a major advantage, but of course it needs ultra high vacuum. So again, there are difficulties and advantages in each quantum platform. Finally, photonics. I think photonics has a massive advantage of being all room temperature. That's a huge advantage that you do not have to cool things down. Of course, the single photon detector requires cooling down, but look at the number of companies, the PsiQuantum, Xanadu, Fox, Quakes. There are several companies now in photonic quantum processing as well. If you think these are done, and each of these technologies require hardware development, new materials, and new devices. These are not all either. For example, there are NMR and the vacancy centers, nitrogen vacancies, qubits based on nitrogen vacancies, for example. In addition to that, quantum computing topological qubits, in which Microsoft has given a lot of emphasis to, but it's not going too far at this stage, making qubits using topological materials, where the qubits are intrinsically protected against error, which is why the overhead to make from physical to the logical qubits are actually much smaller. So that's one of the main directions in which material growth is taking place. So what do we need? We need new semiconductors for quantum technologies. And semiconductors are not just for making qubits. For example, silicon germanium is one direction in which you require semiconductors. But you also require quantum dots for single photon emitters and detectors, which is immediately required for photonic quantum processing as well as quantum communication, as well as sensing purposes. Then you need photonic integrated circuits. You need peripheral electronics. The semiconductor devices must be created for quantum technologies. superconductors, and this is something which is very interesting. You wanted to know, so why do we need new superconductors? We need new superconductors because, for example, we need for new architectures of Josephson junctions, how to clean new type of Josephson junctions which are resistant to errors. We need for imaging, superconducting single photon detectors is one of the most commonly used single photon detectors today. We need superconductors which can resist dephasing. In addition to that, high temperature superconductors are essential if you want to increase the operational temperature to closer to room temperature, or at least liquid nitrogen temperatures. I'll give you an example. This is one of the latest developments. So when superconducting quantum processors were getting created, first generations used aluminium. Then they tried with niobium, for example. And these are superconductors in which the typical T1, the bit flip coherence time was about 70 to 80 microseconds. Our aluminium is about 90 microseconds, and so on and so forth. Recently, just about 3 years ago, it turns out that tantalum probably is a much better superconductor where the bit flip coherence time, or T1 time scale, is more than 3 times larger than the older ones, which is aluminium and aluminum. So again, you see, researching quantum technologies with new superconductors is a crucial step if you want to get better devices tomorrow. Advantage, why this is increasing? So we need research on what causes dephasing, what causes the error in superconducting devices. For example, the oxide that forms on the superconductor. For example, aluminium oxide forms on aluminium, tantalum oxide forms on tantalum. It turns out that the tantalum oxide has got much lesser number of traps, which causes dephasing, and that's the reason why it's better. So again, material research is the key. If you want to, this is 300 microsecond is the bit flip T1 time, which now actually looks like most of the superconducting fabrication companies are going in this direction now. Okay, so there are many different materials. This was a paper that we wrote a couple of years ago, in which what kind of material base will be required for next generation of quantum technologies. New semiconductors, new doping schemes of semiconductors. See, semiconductor, we know what kind of semiconductor would say is silicon, very good. But in order to make silicon work, we have to put dopants so that it conducts electricity. For quantum technologies, the doping scheme must be different. For example, this is the Australian group in New South Wales University. They have started doping silicon in single dopant manner, in which each dopant is a qubit, or a small cluster of dopants, about 2 or 3 phosphorus atoms inside silicon forms a qubit. Advantage, you are creating single electron quantum dots, which can function as a quantum dot well up to liquid nitrogen temperature, 70 Kelvin, 100 Kelvin temperature range. Materials, I'm going to go a little bit more detail in this. Topological materials, which are error resilient materials, and novel superconductors. These are major areas. I'm going to show a little bit about this one. Two-dimensional materials is materials like graphite, for example. Graphite has got a layered structure. Large layer of individual layers are called graphene, which got the Nobel Prize about 10 years ago, 20 years ago. Sorry, 10, 14 years ago. Graphite's advantage is that it has the different layers are very weakly coupled to each other, comparison to covalent bonded or ionic bonded materials. And that's why you can take it out. You can take one layer out. Up to you how you can do this. There are ways in which one layer can be taken out, and you can make devices based on those. There are many such materials now. Graphene, these are graphene usually are semi-metal, but there are semiconductors and ferromagnets, etc., superconductors also. So today materials are actually very important for quantum technologies. You can make extremely high quality electronics. You can make novel superconductors. You can make topological materials, communication for photonics, and you can make single photon detectors for computing and sensing, as well as magnetic sensing. So this is a very important material. Many people are working on it. I'll give you one example in which people have made a qubit using two-dimensional materials, which is using bilayer graphene. But quickly, you see bilayer graphene, there are two layers of graphene, is essentially like a semiconductor. It's a semiconductor with a small band gap. Okay. If I apply electric field, I can actually open a band gap. This is the band gap on the bilayer graphene. Like this, you apply a large electric field, the band gap increases. Now, using this concept, you can make wonderful double quantum dots on a qubit. Double quantum dot is a qubit because you can keep the electron either here or here. So this is a two-state system. So this has now become an interesting direction. Why? Because there are several advantages over silicon as a semiconducting qubit. For example, you can make bipolar quantum. You can make both electron and hole type quantum dots. You can make spin qubit as well as valley qubit. There are additional degrees of freedom that you can use. There's extremely large spin T1 time. In case of silicon or silicon germanium, the spin silicon T1 time is in the order of microseconds. Whereas in graphene, you can get it up to 50 milliseconds of T1 time, which is fantastic. Imagine in the case of superconducting qubits, spin T1 time is just about 100 to 300 microseconds now. Relaxation time is more than 500 milliseconds. So there are plenty of very interesting advantages. As a result, these days there's a steady progress, and from 2021, when the first qubit was demonstrated, we now have a significant amount of additional work. Now, if I look at the overall direction, how this field is going, take a look at this. This work is being done by Professor Chalni in IISc. She is making this graphene-based qubits now. If you look at the silicon-based or the semiconducting qubit development, starting from the mid-90s to where it is today, this is the development happening in 2D material-based qubit development. The latest in this is the spin detection scheme. You can see the spin detection scheme for the spin qubits for silicon was done in 2005, and in the case of graphene, it was done here recently. The progress is significantly faster than the semiconductor-based qubits here. If you think that you have learned unconventional qubits, you'll be surprised with the next one. The next one is the making qubits on the surface of liquid helium. Now, you might say that, oh, why should I do liquid helium? Isn't it cold? Actually, it turns out that superconducting qubits require millikelvin temperature ranges to operate and give you the results. This qubit is actually much warmer. It can be done at 4 Kelvin or even at 2 Kelvin within that. So actually, by making qubit on top of helium is one of the most interesting ways of making qubit. Why? Because if you helium, or for that matter, neon and many of the inert gases, they have a trapping potential of electrons on the surface. So if you inject electron, if you charge the surface of these liquid, electrons essentially self-organize and form a triangular lattice. And those lattices, each electron is like a qubit. It's a spin resonance. Each electron can spin up and spin down like a semiconductor qubit. So now you can have qubits on top of silicon or liquid helium, and this was a proposal way back in 1999, and it's a very clean system, and you can make millions of qubits. This is straight away. You don't have to worry. Electrons are self-organized. You can make millions of qubits. They're identical because there's just a single electron. The only difficulty that was there before was that you couldn't read out the spin. That was the only difficulty that was holding these people up. Turns out that they solved this problem now. In 2022, the first electron spin resonance measurements on the electrons self-organized on helium has been done. This is on neon, I'm sorry, not helium, neon, it was observed. As a result, as you can see, immediately after that, now we have a company. This EOSQ essentially is trying to make a full-fledged scalable quantum computer with electrons self-organized on liquid helium surface. Right now, this has been happening in IISc as well. The idea there is that using instead of single electron, you make electron bubbles. These guys can actually have T1 time of 10 to the power of 5 seconds. Extremely large coherence times can be observed. Okay, I'll quickly say about a little bit of my work here, about a couple of slides or so. I work on noise in many of these quantum devices, in which I look at noise in quantum hardware and see how the decoherence in these hardware is connected to the level of noise and how the trap distribution affects the noise, the decoherence properties and the noise properties. Usually we do this using low frequency 1/f noise measurements. The reason is, suppose I've got a aluminum oxide Josephson junction. There are disorders or defects in the aluminum oxide that couples to the superconducting state and then makes the superconducting state wander around the point that you want it to stabilize. So we look at how noise affects the state of the quantum state. Okay, I'm going to. How much time do I have? I've got about 5 more minutes.
Yeah.
Okay. Good. So this is what I do. I do 1/f noise measurements to understand how it's connected to dephasing of the quantum state. It turns out that 1/f noise is directly connected to the T2 time of or how the quantum information gets dissipated to the rest of the universe. T2 time and T1 time. T2 time is essentially the T2 time plus the dephasing time. So you don't want dephasing time to be too large, because in that case you lose the quantum information very, very quickly. So we would like to make sure that there are materials, identify materials where the T2 time is very, very long. One of the perfect examples is doped silicon. I gave you the example, the silicon quantum dot, by making clusters of phosphorus atoms. And we found that these are the systems in which the T2 time is extremely long, simply because they don't connect very well to the local trap distribution because of single crystal environment of silicon around the phosphorus atoms. And this is one of the longest spin decoherence time that has been reported. If you take many materials, this was one of our work a couple of years ago, we found that if I look at the noise magnitude of these materials, large number of semiconductors, carbon-based materials, topological materials, semiconductors, and we found that the noise value is large, the coherence time is short. Space-breaking length or space-breaking time are directly proportional to each other. So you can see that as the noise becomes large, the coherence time shortens, again showing that it's directly connected to the decoherence taking place by the traps. Okay, I'm going to flip this. I'm going to go straight to where we are with the quantum technology, quantum computing in the next 2 years. So you might have already seen this, so I'm not going to take too much of time. The major stakeholders are here, from life sciences to advanced industries, finances, and so on and so forth. There are much better people to talk to you about this than me. The ecosystem of quantum technologies per se, I will give you a comparative view between computing, sensing, and communication. For example, there is a certain amount. These are about a year-old predictions. So we know that majority of quantum technology ecosystem is going to be governed by the quantum computing. Quantum communications and sensing are probably going to add, and depends upon the market size. Probably one has to look at where it goes. We have right now about potential economic impact of nearly about $1 trillion in the next decade or so. This is the projection. There are 180 universities right now with quantum technology research groups. We require this to enhance in India. India is just at the starting point today. In addition to the scientific progress, if you look at the number of papers published and the patents, it's actually very, very large, very staggeringly high, actually. In 2022 alone, There are 44,000 papers was published in quantum technology area. As a country, I think we are significantly small in that front. We know that India has recently started the quantum mission, and there are other departments like MIT had already started it some time back. But we don't have a fault-tolerant computer today. So what's the way forward? So before a fault-tolerant quantum computer is available, quantum computing is likely to provide speed-ups on few types of problems which have got demonstrated advantage. For example, here are a few examples for those who are thinking of getting into this area, and simulation problems for sure. Then hybrid AI/ML problems, which uses the quantum algorithms, and optimization problems, probably some things that we can do at a shorter time scale. Of course, finally, we need to build probably a hybrid quantum system with noisy qubits and high-performance computing coming together. Cryptographic problems in particular, the quantum algorithms essentially probably is a short-term view that we are talking about. So this will be my last slide. What are the computing-related technologies that the world is looking at right now? And I'll also give you the companies that are doing this. So right now, there are three areas in quantum computing-related technologies are progressing. If it's in classical computing, I'll give you what I mean by that. Analog quantum computing and the digital gate-based quantum computing. That's the right. In which, if you look at classical computing part, there are two areas in which essentially are getting covered. It's quantum inspired and quantum emulators. If you take a look at essentially quantum emulators are running quantum computing codes on classical computers. It's about that. And even that, look at the number of companies that are engaging their activities in that direction. If you take a look at analog quantum computing, essentially quantum annealers and simulators, you can see D-Wave had been there for quite a while. And in addition to that, now Pascal and Quera are also providing optimization problems and quantum physics simulations using on a classical plan. The holy grail is, of course, the last one. That is essentially the digital-based quantum computing. There are two areas, of course, and one is NISQ. That's essentially the noisy intermediate scale computers, which is what the superconducting qubits, the atomic qubits, the other photonic other qubits, which are in physical qubits provide us. And you can see the number of companies there. There are a huge number of companies which have come up. None of them are Indian companies, which is something that I think as a country we should seriously think about how we can get ourselves one of them in that list. The fault-tolerant quantum computing is primarily optical, essentially looking at measurement-based quantum computation, which are in certain ways are universal quantum computing, and Xanadu as well as Phi Quantum and now Alice and Bob has come in, are providing that kind of probably. Alice and Bob probably are doing a little different work. They are not really working on photonics, but they're using cat states for quantum computing, which essentially is an exponentially suppressed quantum error correction. So this is more or less where we are in terms of our quantum computing related infrastructure. We require new quantum hardware platforms to come up, and which is why not only existing technologies needs to be incrementally improved, but new hardware technologies. With that, I will thank you for your attention. Yeah, you can just ask. I'm sure I can hear you. I think we need the. That's okay.
So you mentioned a new compound, that a new molecule we can use for thallium,
Tantalum.
right? So how do we access it? I'm just thinking about, like, if we want one of the companies to be in that list,
right?
We need to understand about supply chain.
Of course. So tantalum is a material that can be evaporated like niobium, for example. So usually tantalum can be either sputtered or electron beam deposited. Right now, even if you look at the aluminium, there's a dedicated foundry system for aluminium deposition for those junctions. One can do exactly the same for tantalum. I know that there are fab facilities within India which is capable of depositing tantalum. IIT Bombay, IISc, there are several. I think there are other places also. But I don't think the technology of deposition is very difficult. So if there is a way in which we can deposit a wafer scale tantalum film, actually we are ready to go ahead with the qubit formation. Yeah.
In today's earlier messages, they mentioned that IC Bangalore now has a 5 qubit quantum computer.
Yes.
DIF has 6 qubits, IC Bangalore has 4 qubit.
4 qubits.
Yeah.
So can you mention and show us this a package for a superconducting qubit? So what's contained inside that? Is it a chip that is fabricated? Is it just a deposition that you mentioned?
What's inside that is essentially the Josephson junction. So you have the Josephson junction is thin film deposited. It's a shallow deposition system, which is they're usually on sapphire substrates, right? And then it is connected to the input and output of microwave. I can go to this picture again if you wish, and the whole thing is inside a cavity, which is a superconducting cavity. And this one is this one. Right. So this is a superconducting cavity, which couples to the Josephson junction and allows you to change this. This one is aluminium.
So is it like a shield?
It's a shield. You can call it a shield. It's a housing. The size of the housing is determined by the wavelength of the electromagnetic radiation, which is in the order of a few gigahertz. A few gigahertz has a wavelength of a few millimeters. And that's why this size is about a few millimeters.
Thank you.
Yeah.
So, is there a natural limit to how far you can go with T1 since you're working on that area?
I mean, no, there are different systems which have got T1s, orders of magnitude different. You go to ions or atoms. Atoms have seconds of T1s. You go to now even the helium people saying that they can go to T1s of seconds. So larger than seconds, could be hundreds of seconds. Superconductors and semiconductors are systems in which the qubit is very strongly coupled to the lattice. Wherever you have a lattice, it's a problem. And that is why the T1 times comes down. So there is no fundamental limit as far as I know, T1. There are, actually you don't want, there are systems where T1 time probably is age of the universe. You don't want that. You want to flip them at some point.
And one question. So which one is your favorite out of all the technologies?
Photonics.
Yes.
Photonics. I think the photonics advantage you have is that there is a chance you will get everything to room temperature. And if you have got everything to room temperature, now why I stress on the word everything is because the only that is not, low temperature part is a single photon detector. Although everybody says that, okay, I've got photonics at room temperature, but at the end of the day, the single photon detector is superconducting detector. So you have to solve that. But there is a strong chance of that getting solved, which with efficiency of 80% or above, 85% efficiency, single photon detector, number resolving at room temperature, I think is an easier solvable problem than getting superconducting detectors of 10 millikelvin, making it a million logical qubit. So that's why I think in the shorter run, unless there's a paradigm shift in superconductivity or that architecture, which might be possible. I'm actually quite I would say quite excited with the CAT states. Now they are doing this, these companies now, and you never know. But I'm putting my money on photonics.
So whenever the topic of fault-tolerant computers come up, there is always topological computers in the picture.
Yeah.
So what are the hardware challenges that we are facing to build a topological quantum computer? Because currently they are theory.
Right. So now topological quantum computers were originally suggested to make fault-tolerant qubits. Qubits which do not easily couple to the environment, or they are agnostic, or they don't get disturbed by local fluctuations, right? And local electromagnetic fluctuations flip the qubits. So for that, the topological qubits were created. And topological qubits depend on certain very exotic braiding principles. Anion braiding, right? Problem is the anion braiding is property of certain excitations which have not been discovered by us yet. So for example, we need a Majorana for nodes, or Majorana mode. We don't have a clear Majorana mode yet. I mean, the Majorana modes were discovered or claimed to be discovered. People went gung-ho, yes, we have it, but turned out the data was fudged. So turns out that we need proper Majorana modes to be established, then your rating becomes. Now, I think there are ways to sort out, and I really like the idea of projecting 0 and 1 to the full Schrodinger states, in which if you take the idea of cat states, essentially take 0 and 1, which are at the same place, but take them apart. So the local fluctuation that can flip one state to 0 is no longer being able to do so because they're physically separated. Is also the same concept as topological qubit, because they are non-local. So the moment you create non-local excitations, you are moving into topological qubits, which is actually a very good concept, but hopefully someday.
So I have a small question related to the prediction of very small changes of G that you spoke about. So given the very high sensitivity of these quantum sensors in detecting these gravitational anomalies, let us say,
right.
So how do you see these quantum computer enhancing the real-time processing and prediction of these changes in G?
Right. I think we have to separate the two problems. I mean, first of all, the measurement of G very accurately, usually the nano G measurement, that is essentially 1 part in a billion, is what is the projected and intended accuracy. Now, that's a pure hardware problem, of course, but there will be a lot of noise. And of course, the computing as well as machine learning softwares can enhance that or to isolate the noise. But the core idea here is usually to make using atomic sensors or gravimeters, in which a trajectory of atoms, a small change in the trajectory of atoms can be used to identify what the change in the local gravity wave function, local gravitational constant is. The only reason is that mass of the atom is so large that any change in the trajectory by small change in G changes the trajectory of the atoms, and the interference pattern of two atoms interfering with each other changes. So that's the idea of measuring very, very accurately the G, the gravitational constant. But again, once the interference pattern is there, you can use computing tools to isolate the noise and get them. So that's where it comes. I don't think quantum computing per se will be able to help measuring the G changes very quickly. Okay, no, thank you.
Thank you so much, Professor Ghosh, for sharing such profound insights and an informative session. To honor Professor Arindam Ghosh, I would like to invite Mr. Samrit Mehdi, Scientist E at C-DAC, to join us on stage for felicitation.
He's went outside.
Okay, I'm extremely sorry. I would now like to invite Mr. Amrit Saxena, sir, in order to felicitate. Of course, sir. Our next distinguished speaker is Dr. Sandhu Sardar, sir, who joined DRDO as a scientist in 2010 and currently serves as the director of DRDO Young Scientist Laboratory for Quantum Technologies. This laboratory was established with a mandate to advance research and development in quantum technologies in India, in alignment with the vision of Honorable Prime Minister Shri Narendra Modi. Dr. Sardar has received several prestigious awards throughout his career, including the Technology Group Award from Anurag DRDO in 2012, the Research Excellence Award from IIT Hyderabad in 2018, and the Appreciation in Research Award from IIT Hyderabad in 2019 during his PhD studies. He also received a Commendation Award in 2024 from the Secretary DRND and Chairman of DRDO. Notably, Dr. Sardar was a Vishweshwarya Fellowship during his PhD. His contributions to the field are extensive, having published numerous papers in international journals and presented at various conferences. Thank you, Dr. Sardar, for your significant contributions and for being here with us today. Let's welcome him to the stage for his session on Journey of Quantum Computing National Initiatives. Sandhu, sir.
Yeah, good afternoon, everyone. So first of all, I thank C-DAC for inviting me here and giving me an opportunity to give a presentation. In our lab, DYSL QT, we are working on various aspects like quantum sensing, QRNG communications, and quantum computing. So here, my talk, in my talk, I will briefly touch upon the importance of quantum computing, then give a very brief overview of global scenario at present, and then journey of India. I will focus mainly the activity of our group in collaboration with TFR Mumbai. And being a post-lunch session, I have purposefully avoided the mathematics part, and I will give a brief overview. The idea is to give a flavor instead of going into the deep of these technologies. So within this small time. So I will start with this slide. So as we know, cyber security is a very real threat. Every now and then there are various critical news about cyber breach, these things. So all these things happens due to vulnerability in the systems. So if we rank these vulnerabilities, the most important vulnerability is fundamentally vulnerable cryptography. Now, the classical cryptography technique, those are basically depending on the computational complexity aspect. So now the projection is that with the advent of quantum computer, so this can easily break the prime factorization problem, and that may lead to a disaster in the classical cybersecurity aspect. In fact, in some survey, it was compared with nuclear threat to cybersecurity as well. Now that may lead to various aspects which can be called as an act of war itself, like power grid shutdown, transportation grid lock, banking sector fall off. Then in the battlefield also, if the security is leaked, then that itself will be a very disaster for any nation. satellite could deorbit, so hacking of satellites. So all these have very, very finite probability with the powerful advent of quantum computer. But at the same time, quantum technology gives a solution also to these aspects, at least partly to some extent, and that is quantum safe cryptography. So from there, actually, the new vertical comes quantum communication. So we had various previous presentations also on quantum communications. So mainly key distribution, quantum random number generators, and post-quantum cryptography. So these three are the most prominent approach for prominent aspects of quantum safe cryptography. So, this is how actually our quantum computing, quantum communication is. So this is just one aspect of application of quantum computing in an offensive manner. So there are various other use cases also. I will not go into the details. It can be BFSI, aerospace, life science. So there are various aspects or various applications. I think in the subsequent presentations also it will be covered. Now for these we need powerful quantum computers. So how powerful a quantum computer should be to use to address these aspects in a practical sense. So for that there is a survey. So in this survey they have told that we need basically hundreds of thousands of qubit based quantum computer to address various practical problem statements. So basically we are very far ahead, but it's a good way. We have started the journey. The journey started long back in 1980s when the quantum Turing machine was first proposed. And then Richard Feynman, he himself told that no one understands quantum mechanics. But then what best we can do, we can make use of these exotic properties to achieve technological edge or marvels. So he himself was promoted the idea of making a quantum computer. So he told that the nature is quantum mechanical, and if you want to model the nature for our benefits, then the computer also has to be quantum computer. So he promoted it in a big way, and then various other people, they have made various quantum algorithms for to demonstrate what are the advantages or what are the edge we can have. So this I think was briefly covered with by Amit Saxena sir also. So there are various flavors how to implement it. So they have given the advantages. Now comes how we can implement a quantum computer. Quantum computer means it's basically a collection of qubits in different manner, in different architectures. And there are various modes of implement, how to implement physically. Gosar also, he has explained various aspects of it. So I will just summarize like NMR based, traptan based, neutral atom based, solid state based, so photonic based and topological. So there are various other aspects also in the previous presentation we have already seen. So now to make a quantum computer, there is some rules that has to be followed to control the quantum computers. So those are governed by De Vincenzo criteria. And there are various security or performance measures of a quantum computer, like how many number of qubits, qubit lifetime, gate fidelity. So there are some performance parameters that we have to check when we are developing or implementing a quantum computer. So I'll not go into the details of each of it. And currently, there are various major players in quantum technology, quantum computing globally. So we have shown only three major big players, China and IBM. But very recently, there are various startups have come up. And in fact, some of the companies, they are offering quantum computing as a service also. And at the same time, they are offering procurement of quantum processing unit so that we can buy the quantum processing unit and then we can build a quantum computer around it. And some of them are offering a full-fledged quantum computer also, but the number of qubits what they are offering, those are very less. So those are basically for get an hands-on flavor of a quantum computer. Most of them are superconducting circuit based, but there are various other. This list is non-exhaustive. But here we cannot be dependent on these foreign sources because there are lots of there are lacks of visibility. At the same time, export control and monopoly risk is also coming up. That I will be explaining at a later presentation. But before that, I would like to highlight that there is a long way to go. So currently, the hardware research for implementing a quantum computer and to have an application advantage in practical scenario, there is a huge gap between it. So if the performance we can, so if the performance of a quantum computer we can show it in the x-axis. So first milestone maybe cannot be simulated by a classical computer, followed by demonstrable advantage against classical computers, economic advantage for a specific problem, and finally, being defense, another objective will be to have advantage for DoD relevant applications. So in algorithm level, there are various explorations. In hardware implementation level, like NIST era, fault tolerant, those are also we have seen some details in the previous presentation. So there is a gap between it, and internationally also there's a huge push to bridge this gap. So for that, we need to address some of the challenges here, like quantum integrated circuits to allow scaling and reduce the swap-C operations. So basically, if we see the current, let us take an example of superconducting circuit-based quantum computing. So here, if you see the number of interconnections and the kind of complexity of the systems, those are huge, even for hundreds or thousands of qubits. And those will be very, very much enhanced when you go for tens of thousands of qubits. So we need some alternate approaches like FPGA-based approach or IC-based approach for control and readout. And at the same time, how to enhance the other support systems for quantum computers. Fault tolerance. So currently the quantum computers are noisy, which is called a NIST era. But how to enhance the fault tolerance performance or noise reduction, that is an active area of research. And then again, application advantage. So basically this bridging this gap is a major concern. And for that, the research on hardware implementations, those has to be fast forward. And we don't know which one will be the winner of different flavors of implementations. There's a survey by US Office of Undersecretary of Defense and Research and Engineering. So for various quantum technologies, not only for computing, but for communication as well as for sensing. So what is the military readiness of this technology versus what is the potential military impact? So those they have plotted in this graph. So we have to take it with a pinch of salt, but we can get some idea. So let us focus only on quantum computing. So here if we see, if we have a small noisy quantum computers, so this currently the readiness is it's in lab demonstrations level. So there are various startups who are working on it, various government agencies, various industries. But they have a very low impact on the military. Whereas if we can, if we are able to achieve large error-corrected quantum computers, then we may have a very big impact in military, but the readiness level is very low. So this is just to give an idea of where we stand currently. But at the same time, there is a survey by ASPI for different technologies. So what are the top 5 countries and what are the technology monopoly risks? So it may seem a little premature to evaluate what are the monopoly risks, etc. But as per their survey, quantum computing and quantum communication sensors, so everywhere, US and China, they are almost in the top, followed by Germany and UK. There are other countries also working in the similar directions. And here, if we see focusing on quantum computing, the monopoly risk here, as per their assessment, it is very high. So one of the factor what is actually contributing to it is coming in the next slide. Very recently, I'm sure you have seen in the news also that there are various export controls. So those are being imposed on quantum computing. So not only for the quantum computer related export control, but export control on various components, subsystems of the quantum computers also. So though it may be a little early, but I consider it is been more difficult or more dangerous. Because currently we are many countries, those are in R&D stage. So if there are some export controls at this stage, then that may be very, very dangerous. And this is just the tip of the iceberg. So basically, there is a international organization is there, Westerner arrangement. So there, it's a multilateral export control regime, which have 42 countries are party of it, including India, USA, and many others. So there, basically, they deliberate about these topics. So what are the technologies which should be controlled by the member states? And their quantum technology is one of the sections that they have incorporated very recently, I think around 2019. So there the export controls are mainly being discussed on quantum computing and very recently on quantum communications also. So this may be very challenging in the subsequent days if it is increased, these controls are increased. So this will give just to give a very brief idea about the recent global scenario. So I will mainly focus on Indian advancements and mostly in our work. But before that, to give a very good idea about where actually India stand globally. So this is just to give an idea that so I have listed out different approaches of implementing a quantum computer. So what is the international status and where we stand in India at present and what is our immediate targets? So for superconducting qubits, we know IBM, they have gone up to 1121 qubits and that is the highest currently at present. Whereas in India, our group along with TIFR Mumbai and TCS for cloud access, so there we are able to achieve up to 6 qubit quantum computers. So there are various optimizations that has to be done. But the first level complete system is ready. I'll be explaining the details. And at present, under National Quantum Mission, the immediate target is to go up to 24 in the next 2.5 years. Similarly, for other approaches also, I have just listed out a very brief good overview of where we stand and where it is globally. At the same time, works are going on quantum simulators where C-DAC along with ISC, IIT Roorkee are working, and there is a activity from C-DAC on hybrid quantum computing. So now I will focus on our group activity jointly with TIFR. So here our objective, we started our activity in 2020 and our objective was to make a full-fledged quantum computer using superconducting circuits. What does it mean? So basically a quantum computer, the heart is our qubits, set of qubits, which we call quantum processing unit. So this will be a set of qubits interconnected with each other. Then to make it a quantum computer, we need to initialize those qubits. We need to have some control over the qubits, how actually those qubits should interact with each other, have to interact with each other to make up specific problems. And then how to measure the final output. So these three will be the major subsystems. And then finally, this is the computer. So we need an access to be used by a user. So here, this is actually one actual snapshot of our complete systems. So our idea is not only to make the computer, but our objective is twofold. So one is that to make a quantum computer using quartz-based systems, which is available. And at the same time, we are parallelly exploring how we can indigenize some of the parts. So one such part is definitely the quantum processing unit. So these anyway in both the approaches, it is being developed by TIFR Mumbai in their fabrication facility. Another is our control electronics part. So this part, we are approaching two methods. One is using the existing methods available globally using the quartz components. At the same time, we are trying to make FPGA-based solutions which actually will be replacing all these things. So currently, we have made these systems, and then this single FPGA board can control and measure simultaneously 8 qubits at a time. And we have tested it in simulation using loopback mode as well as with actual environment as well. And what we found out that this will not only give us some technological visibility and reduce the form factor, but it will reduce the cost also significantly. So some very rough calculation what we have done, the cost factor will be around 22. between the two different approaches. So these two approaches both we have tested, both with actual qubit as well as with in loopback mode. And TCS is involved in this activity to make this user interface for cloud access. So this complete system, we have this few months back, we have made a complete demonstrations. Now, there are various scopes of optimizations as well as some automation is required. And after that, we are planning to, so this is the final system. So this complete system is available. And by this December 2024, we are planning to launch this quantum computer over cloud for general public use, so that students and other people, they can get a hands-on the actual quantum computer made in India. Yes. So this cryogenic setup will be the this one. So where we will have quantum processing units and other related components, attenuators, multipliers, etc. Then we will having automated calibration softwares, control measurement electronics, and then on top of that we will have a software layer which will actually talk to the actual hardware and make the microwave pulses for the operations. And the user need not bother about all these things. So so they will have this user interface, they will make a login, and then they can do gate level operations. So there will be two different approaches are there. It can be a drop-down box-based graphical user interface, as well as they can directly code in Python also. So this is the individual qubit that is fabricated, and this is the exact architecture what we are using for the 6-qubit quantum computers. So this is the open box part, open fridge part, and these are complete systems. So right now optimizations and various automations are going on. So hopefully by December end we will launch it for public in India. So this recently came in the news also. And so this is our immediate plan. So we'll be launching in December, and then we have to maintain it also so that people will be continuing using it as a complete system over cloud. So further also discussions are going on how exactly we can do it. And the next very important part will be how to scale up to larger quantum processing unit. So under the National Quantum Missions, we are in discussions how we can, this joint team of DRDO and DIFR Mumbai, how they can jointly work together for this larger version of the QPU. So that is going on. At the same time, we are planning whether we can make a dedicated fabrication facility for not only for quantum computing, but the same facility can be useful for other quantum particles also. So I think as time is little less, I will go a little faster. So these are some of the other explorations going on. So as I was saying, the quantum processing unit for our activity also, this was developed in the TIFR facility itself. But for increasing the number of qubits up to hundreds or more, that facility may not be sufficient. We have to think of some other sophisticated facilities for QPU at a later stage. This is the work going on in IISc Bangalore. So Dr. Vibhor Singh and Balanita Suri, they are the PI, main PI of this activity. So they are also working on various other different aspects, architectures and of quantum computing. So they have made up to 4 transformative qubit-based quantum computer and tested the performance. Another activity that DRDO has promoted through their ERIPR project is super semiconducting quantum dot-based quantum computer. So for that one, project was given to IIT Bombay, and currently the PI is Dr. Mahapatra. So he has initiated fabrication of an array of 8 quantum dot-based qubits, and the performance characterizations, so those things are going on. The recipe is almost final. At the same time, we are trying to not only the quantum control electronics for the quantum computer, but various components also are trying to indigenize as part of our quantum computing efforts, like the RF mixers or HEMT low noise amplifiers. So for quantum computing, they need to have some specific parameters. Those we are trying to make within India and then test it in our facility what we are already available as part of our quantum computing initiatives. And for that, we have one facility in Hyderabad called GATEC. So we are getting a very great help from GATEC to work on various aspects of this indigenization of the components as well. The QSim part that is already covered by C-DAC about their efforts on the QSim. It's a software simulators that also people can access online. So it's C-DAC ISC collaborations. For atomic qubits, there are various institutes available. So I will not go into the details. And for photonic qubits, which is a very promising technology, so there also the major work is going on in IISc, IIT Madras, and RRI. The current target is that by 2026 they want to go with they want to implement 20 qubit photonic quantum computer on chip, and by 2028 it should go up to 50 or 100 using chip or our bulk optics. HPC quantum integration, these are already discussed, and C-DAC is taking a lead in these directions. And these are some of the technologies, some of the institutes, and the PI name I have just listed out on quantum algorithms. So maybe in the subsequent presentations also it will be discussed in a great details about what are the activities going on in these institutions. And currently with the advent of National Quantum Mission, quantum computing is vertical in it. And here, very recently, there was an announcement that the thematic hub for quantum computing will be in IISc, and there will be various other institutes involved. So work is going on in a positive direction in it. So now, very briefly, just I will list out what is needed, what I feel for readiness for rapid progress. So I'll not go into the details. I will just highlight it. So one thing, as I was mentioning earlier, is dedicated fabrication facilities. This is very, very important. And without that, we will be forever dependent with outside. Another is facility and expertise for various material research as well as fabrication processes. Growth of silicon germanium heterostructure. This is very, very important for quantum dot-based quantum computing. Electronics and microwave engineers. So basically quantum computing and for that matter, quantum technology, those are multidisciplinary approach. So we need expertise from electronics, RFs, computer science, physics, and various other fields. Integration in the HPC, already it has been discussed. Dedicated personnel, so this is very, very important. And then evaluation, funding, and procurement procedure. Those has to be very, very fast. And some of the challenges and suggestions from my side. So one is optimization of application processes to make reliable large-scale chips. As I was mentioning, those chip-based control electronics for quantum computing is the future. It is unclear at this stage if targeting large number of qubits without error correction is useful. So for that, we have to explore both these things, and strong R&D is required in all these directions. Which qubit will be the winner? We don't know. Key expertise predominantly in academia. So basically, government labs and industries, those also handled in a very, very strong way so that we can have a sustainable development in these directions. So in this, I will conclude my presentations. So with the note that there are lots of promises, lots of things to catch up, exciting times. So from DRDO side also, we are putting our best to proceed towards Atmanirbharata. So let us hope for the best. And with the National Quantum Mission, we have high hopes on it. So for my presentations, I would like to acknowledge these are the academicians and Dr. Nath from C-DAC Pune. So I have taken many materials from their presentations as well. So thank you for your questions. Any questions from anyone?
Thank you, sir, for your significant contributions and for such valuable insights for the session. To honor Dr. Santu Sardar sir, I now invite Mr. Samrit Mehdi sir, Scientist E at C-DAC, to join us on the stage for felicitation. Our next distinguished speaker will be joining us online. It is Mr. Amit Srivastava sir, Scientist E at RCI-DITO. He holds a master's degree from IIT Delhi and a bachelor's from the IET Jhansi, and is currently pursuing a PhD in quantum technologies at the IIT Pune. With over 7 years of quantum cryptography and quantum sensing, Mr. Srivastava has led India's first optical fiber-based quantum key distribution project, achieving 100 kilometers of secure communication in 2021. He has received the Technology Group Award, National Science Day Award, and an Innovation Award from NVIDIA. Previously, he worked in scientific data computing for 15 years, developing defense applications. Thank you, Mr. Srivastava, for your valuable contributions. Sir, we would like to continue your session on quantum entanglement, a resource for information processing.
Hello.
Mute.
Am I audible?
Because this
Hello. Hello? Hello? Am I audible?
Yes, sir.
Yes, sir. Yes, sir. Can I start or is still echo problem is there? Yeah, so thank you for the organizer for inviting me and presenting me this talk here. So the title of the talk is Quantum Entanglement, a Resource for Information Processing. As we know that quantum entanglement is the most non-classical manifestation of quantum formalism. And first, it was recognized by Einstein, Podolsky, and Rosen and Schrödinger together. But that was a negative sense that Einstein was not convinced with this idea, and he said it is not a complete theory. And later, after 70 years, the Bell experimentally he proved that it works and it is real as in the form of the energy also. Okay, so and what I will be presenting here, the information processing, like how you can use this concept for doing the computing, also for the communication and sensing. So my talk would be covered in following subsections. So for the sake of completeness, I will be giving some introduction about the quantum technology. I think it is has already been covered by some other previous speakers. Then I will talk about what quantum entanglement is, what is the motivation, and how do we measure it, how do we quantify it, and there are many numerous applications. Out of that, I would like to classify in quantum computing, communication, and sensing category. So as we know that we are in the second revolution of quantum technology. So first was when that transistors, lasers, and all were invented, and these rules were framed in around 1930. Okay, but though the mechanism was there inherently, it was there inside, but we were not able to control it. So in the second revolution, what we are trying to manipulate and then trying to use this as per our wish to either to compute and communicate and also the sense. So here you can see that we have quantum computers, and then this is for telecommunication and for sensing. So this is like a quantum gravimeter, which can measure the value of gravity up to the 8th or 9th decimal. So some of the unique properties of quantum physics are Hello. Yeah, oh, sorry. Yeah, sorry for the interruption. So I'm just displaying here some of the unique properties with respect to quantum technology. So as we know, the first is quantization, so which comes from the name itself, the quantum. And the second one is a wave particle duality. So whatever quantum state we have, they work both as a wave and as well as particle also. And these states, we can put it in superposition, so they can have the values simultaneous. Then comes the entanglement, which I would be explaining in detail in this presentation. And the next one is indetermination, which is basically Heisenberg uncertainty, that some of the commutative properties cannot be measured very precisely. The next is a measurement property in which we cannot identify this alpha beta exactly. The only we can know by projecting, either we can have a projective measurement or POVM, which is the generalized version of the projective measurement to estimate these values alpha and beta. And these measurement changes the state, so that is also unique. And then we have a tunnel effect, in which these quantum state then bypass some of the higher energy level, which is not possible classically. So this concept is heavily used in the quantum computers like D-Wave, quantum annealing and all, and the non-cloning, that we cannot clone make a copy of a quantum state. So since this specifically I will be talking about entanglement, so this is one motivation here. So all of us, we know that the PET scan. So how it works is we inject the radioactive tracer into the patient body, and wherever some pathology is there, that radioactive elements can get deposited, and then when it decays, it emits the positron, and then this positron interact with electron, it produces two photons which are entangled, and then those two photons are detected by the detectors which are placed around the patient. So these two photons are entangled, but we know that there are a lot of noise in the emission of this from the emission to the detection of the photons, and then these PET images are very noisy. That is why we need to combine with CT. So can we do it better? So if we use properly since these two photons are entangled, and if we use this entanglement property at this point of time, we are just doing the detection. We are not classifying whether still they are entangled or not. So there is some research is going on, which they are calling as entanglement enhanced medical imaging, and they hope that they will have a very fine PET images equal to the CT, and we will not to have the register with the other medical modality. So this is one of the example. Another example which I thought I'll present it here is a bomb test experiment, just to motivate you what all quantum principles can do, which is not possible classically. So you assume this is a thought experiment. You assume there is a bomb which is represented here as a TNT bomb, which has got a photo detectors, and the task is to you have to find out whether bomb is faulty or working. But the issue is that bomb has got if you shine light, it will explode. So how we can test whether the bomb is faulty or not faulty? So there is classically it is impossible to detect, but if you use a quantum principles, it is possible to detect basically the concept is interference here. So we create a superposition by sending a single photon. So either it takes the upper path or lower path. So when the bomb is faulty, always D2 will click with 100% of the probability. But when bomb is good, there are 25% of the probability that D1 will detect, D1 will click. So this clicks gives the answer that the bomb is in good condition. And this is a basically So the concept is the photon has not traveled this lower path in which bomb was placed, but still we are able to conclude that bomb is working. So this is a counterfactual protocols, and there are a lot of methods are based on these protocols. One of them is counterfactual quantum key distribution. So as I told, there are numerous applications of quantum entanglement. So some of them I just listed here, like that is very much aligned to the quantum communication. Then we can develop the self-test random number generation. We can teleport the quantum state. We can develop the quantum repeaters. We can use a super dense encoding in which we are sending only single qubit and can transfer 2 classical qubit. We can do many precise sensing. We can do metrology and computing. So the concept is has got really totally counterintuitive and non-classical, and based on this, the 2022 Nobel Prize was given to the 3 physicists, and the task was that for experiments with entangled photon, establishing the violation of Bell inequalities. So we can, by using this itself, we can realize the importance of this concept. So before that, I'll just explain what is pure and mixed state in this, because it would be used subsequently slides. So generally, whenever we do the theory, we use like present as a single vector in a Hilbert space, so which is a pure state. But actually, when we do implementation and on the lab, we never get a pure state, because always environment keeps on measuring the state, so it becomes a mixed state. So you can, I think, understand the anything inside the Bloch spheres become the mixed state. And if it is a maximally mixed state, I think the quantum property will be lost and it would be at the center. So the definition of quantum entanglement is like the state. It is the combined global state of composite systems in which the individual systems lose its identity. So the combined composite state, which is cannot be represented as a product state. It is then it is an entangled state. This is valid for the pure state, but for the mixed state, since we have to represent, we cannot use the psi or phi for the pure state. So we have to have a density matrix for that. So as per the definition, the which should not be a separable state. So like we cannot be entangled. For the entanglement, we need to prove that we cannot represent as a complex combination of the density matrix. So there are some well-known entangled states like Bell state, GSG states, W state, cluster state, and the measurement-based quantum computing, the concepts totally is based on the cluster state, in which initially we have a end-to-end connectivity or entanglement with the states, and then we do measurement one by one, and then like we can compute any logic. So there are different types like discrete variables entanglement. We can use some of the degree of freedom like polarization and orbital angular momentum, and also in continuous domain we can use Gaussian state and squeeze state. These also can be entangled. We also have a concept of hybrid entanglement, in which we can entangle single photon with a coherent state, which is not a quantum state. Also hyperentanglement, at the same time we can entangle more than one degree of freedom. So the next question comes, suppose we have been given some state, how to find out at how much entangled it is. So for the pure state, for bipartite system, it is easy, but if you go for multipartite, it becomes more complex and it becomes almost impossible if you consider the mixed state. So there are some of the measures. The first one is like Bell inequality. So we compute this S value, and if it is and we say that if it is higher than 2, then we classify it as entangled, else it is not entangled. Then some of the other properties are like entropy of the entanglement, okay, entanglement of formation, relative entropy, and also the using density matrix, we have to calculate the partial transpose of the density matrix. And if we have to see if there is no negative eigenvalues, then the state is separable and it is not entangled. But this is again, it's an NP complete problem, and it becomes very difficult to evaluate. How to suppose we have been given some state which are not maximally entangled, can we enhance that entanglement? So that is not always true. So there are concepts like free entanglement in which we can enhance, or we can do the entanglement distillation and purification, but there are some bound entanglement in which that is not possible. Coming to some other unique property, there is a monogamy of entanglement in which if A and B are maximally entangled, then there is no way to Charlie to get entangled. So means Charlie cannot have any information. So this concept is heavily used in QKD, where we have to do the secure communication. So we have to just prove that Alice and Bob are maximally entanglement, and the proof is done. But some of the limitations of entanglements are, as I mentioned, that it is a very complex structure, and it is very fragile, because environment keep on monitoring the state and then get entangled with the state, and then we end up with mixed state. And the limitations are, to get the entanglement, we need to have both the state at the same place. If too far, states cannot be entangled. So coming to the like example in quantum computing, how the entanglement helps, I'll just present few examples here. So this is just to make you understand that how the quantum and classical differentiate. So in classical, we have two types of algorithms, deterministic and probabilistic. So in the probability, since cannot be negative, we cannot suppress any state. Unlike that in quantum, since it is a probability amplitude, so some of the unwanted state get cancelled out, and then we get the required output. And this is how we classify the algorithms. So here if we see, there are many algorithms, and if we see the universal set, so which consists of C0 and Hadamard and T-gate. So as we know that we can create a, if we use a Hadamard and C0 in sequence, we get entangled state. So there is very difficult to find out any algorithms in which entanglement is not there. So the interpretation is, if we have, since we are doing computing in invert space, so we have a very large space to keep track of that. If we connect the entanglement, and that will help us in navigating the state and getting the required state as an output. So there is a paper I mentioned as a reference on the role of entanglement in quantum computational speedup. Though it is a debatable concept, but there is a thought that if we don't have entanglement, so whatever we do can be simulated classically. So as I mentioned here, in the computing, the simplest way is to put Hadamard and C0. So, and this you get a maximally entangled state. So here, and then what is generalized way of getting entanglement here is any unitary transformation. If you put a Hadamard, that superposition state, and then the psi is not a eigen state of that uniform, the transformations, then you end up with an entanglement. So since as 1 by root 2, 0, 1, and the tensor product psi, if you apply this transformation, you end up with phi. And now we cannot take anything common, so it is not separable and become entangled. there is a very famous phase kickback mechanism in which this psi becomes the psi becomes the eigenstate of the u. In that case, we can represent with E I theta psi, and then it becomes, though it becomes separable, but the understanding is that the information is transferred, and then at the end it becomes again non-entangled. So this concept is heavily used in many algorithms. So what is happening here? We have put a transformation S in which rotates by pi by 2, but that rotation is happening in the control unit, not at the target. So basically the interpretation is it kicks back the phase, and this is the same concept is used in global algorithm in which we have to design some oracle, and oracle just kick back the phase of what exactly value we are searching, and how to get this phase. It is not an easy way to get this element of the opposite phase, because it is again still equal probable. So then we need to do the amplification and get the amplitude, higher amplitude for particular this element. So this concept is used in most of the algorithms. Like the phase estimation, we do it n times the phase kickback, and then we do the QFT to find the period, and the same concept is used in the shore. So we say that most of the algorithms, the entanglement is used, and so the entanglement basically needs connectivity. So if we, though there are some other characteristics to find out like how powerful the quantum computer is, like number of qubits, the qubit fidelity, the gate errors and all. And one of the important parameter is the connectivity, because that gives if we have a more connectivity, then we can entangle the qubits, and then it becomes more powerful. So as we know that the superconducting, the connectivity is limited by the neighboring qubits, and then we have that this IonQ in which using the ion traps and this neutral atoms, since these are the traps, so they can be moved, and we get the entangled, and then place it again. So in using this mechanism, we have many to many connectivity, and they are much better and more powerful than the limited connectivity quantum computer. So coming to some more applications. So as we know that like the analog computing, the term was coined long back, but so far we don't have analog computers. Why? Because we were not able to control the error. Unlike that, in quantum computers, we have a quantum error correction which can control these errors, and that is why it makes it possible that we would be having in future very powerful quantum computers. So all this comes because we are able to have the entanglement in the case of quantum computer, unlike the analog classical computers. So, and the entanglement again come to the rescue. The entanglement is a necessary and sufficient condition for having the quantum error correction. If I come to the communication, so as I know that there are many degrees of freedom to do the entanglement, and that if we have more than 1 degree, we can call it as a hyper entanglement. And in the case of computing, we use H and C naught. In the case of the photonic optical things, we use SPDC to create entangled photons. So this is I am just showing in my lab in which we have created an entangled photon, and we calculate that CHSS inequality, which is around 2.3, and some other properties are listed here. And we also do the quantum tomography to get the density matrix, and then that helps to quantify how much entangled it is. So this is some more details about how do we do the Bell inequality and get this S value. The next concept comes about the quantum repeater. So again, as we know, we cannot the quantum entanglement we cannot preserve for longer duration or longer range. So what we do here, we divide it into segments and apply the entanglement purification and the entanglement swapping. So these two concepts, we get very far points maximally entangled, and then we do subsequently the transfer of the keys or any qubit state or rest of the thing. Also, the teleportation is also a very unique feature in which we cannot like copy the qubits, but we can transport. And since we are not physically transporting the qubits, so there is no loss because in the channel. So, and the concept is again we have to use the entangled pair which are pre-shared, and then we project these two qubit which we need to teleport and the entangled qubit into the ballistic basis, and which gives the 4 values, and these 4 values are transferred using 2 classical bits, and then we apply at the receiver and get the qubit. So there is no loss of this qubit. We get intact, the state is intact because it is not transferring, but magically it is getting teleported. So there are some of the experimentation which has been done, and the China has teleported the qubit state from the satellite to ground. But yeah, in India, we don't find any lab which has teleported the qubit. So I think we need to put some efforts in this direction. Even the same concept, the reverse concept is a super dense coding in which we are using an entangled pair, and we are sending the only 1 qubit and transferring the 2 classical bit. So yeah, in the sensing case, so as we know that these qubit states are very fragile, the same principle is used to measure the phenomena here, and like we can get a very precise measurement using these qubit quantum state. So there are 3 classes. The first one is if we just use just prepare a quantum state and do the measurement. If we use a coherence, that is called second class 2. And if we use a entangled state, then that gives the most precise measurements. And in the case of unentangled state, the precision is limited by 1 over root n, where n is a variance. So here, in the case of entanglement, it gives 1 by n, and then we get a better precision. So this is all like what all we can measure here. It is like magnetic, gravity, acceleration, and gravitational wave and all. So at RCI, we are putting some effort and working in quantum sensing direction, this field, and we are trying to measure gravity, magnetic field, and other parameters. So this is pictorially I have represented how entanglement helps in getting better precise measurement. And also there is a concept called quantum radar, in which as we know that we cannot detect the stealth targets. So presently in classical regime, what we send some radiomagnetic wave. What if we send entangled radiomagnetic waves? So the concept here in this case, we will have one copy to compare, and this correlation is high. So we hope that we can do much more better than the classical. These are some of the values in which it is projected that this concept can even track all stealth targets. The same entanglement, there is a concept called ghost imaging, in which we can do imaging by sending the photon, keeping one pair with the sensors and sending the other photon to the target. And coming to the QRNG, as I mentioned, that the So far, we don't have a self-certifiable QRNG. Since we have only statistical test to measure, but they are necessary but not a sufficient condition. So how do we prove that whatever we are generating is really random? So again, if we use entanglement, and these are some of the classification, I think I'll skip because of the time. And basically the concept here is, if we do this low fold detection and we like create an entangled state, and that since that is already random, that state is random, and we generate this random number using these entangled state, we can claim that it is a really random. So this is some of the activity at DRDO. Like we had a quantum roadmap in which we have listed out some of the activities in which direction to work. So like there is a communication, and in computing, I think Dr. Sandhu has already presented his work, what they have been doing, and also sensing and other activities. So this is the just to summarize what I have presented. So quantum entanglement is like the most non-classical manifestation, and it has got numerous applications. Yeah, thank you. I think I can take up some questions if time permits. Yeah. 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 So the phase actually we are doing is up to number of like we need to get a precise measurement of the angle. Okay. So we do multiple times, and then each time if we apply this phase kickback, it increases the precision. Okay. And then at the end we do the QFT. Okay. So which tells the period. So the as many times as we do apply this phase kickback, we get higher and higher precise angle, yeah, measurement. I hope I was audible.
Hi. Good afternoon to all. Yes, so hope I am audible to all of you. Sorry for my delay due to some other meetings going on, and I hope I can start my presentation now. Am I audible to all of you? Because I couldn't hear anyone from the stage. Huh? Yeah. So now something is coming. So shall I start my presentation? I just want a response from your end. Yeah. Shall I start my presentation? I can start, right? Okay. Fine. Okay. Yeah, hello. So let me start my presentation. Just wait. Yeah. So screen now. Gosh. So I hope my presentation is visible. Okay, and title of my presentation is quantum circuit partitioning. Okay, optimizing the quantum processing elements (QPEs) for the NISQ era. So the motivation of this particular lecture is that okay, how to accommodate the execution of the quantum algorithms, which involves okay, that means a good quantum algorithm which solves a problem, right? It involves a good number of quantum gates and qubits. And we know that presently in the NISQ era, we have a fewer quantum resources. So how we can implement this water and the circuit partitioning techniques, which have just been developed, I think, for a few years, not a very old concept. It has only emerged for a few years, and we'll discuss some of the techniques which are now used for this in my lecture. And also I will discuss that what is our research in this domain of utilizing this circuit partitioning techniques and trying to implement the quantum circuits in the present NISQ quantum systems. Okay, I thank the C-DAC and Symbiosis for organizing this workshop, and it would have been lovely to be there with all of you physically. But again, due to some pressing commitments, I have to go online. Okay, so the outline of my lecture will be like this. So I will first introduce the concept of circuit cutting. I don't know how many of you already know this concept. And then I will introduce some of our works like IQER, FRAC-QC, QR zone, and NOTADS. And then I will conclude with some of the possible research directions. So let's see the quantum computer. Yeah, we know that in the NISQ era, that is the noisy intermediate state quantum computers, where we have less number of qubits, we cannot implement the fault-tolerant quantum computing due to the limitations in the number of qubits. We have to use the qubits available mostly for our for encoding our data, and we don't have the qubits to encode our errors. Okay, and that's the problem in the present okay quantum era, right? NISQ era. And but quantum computing shows a huge promise, and we have to come up with some sort of okay midway or adoption of some strategies so that we can also visualize the solutions what a quantum computer can give for a sizable amount of the problem, for a sizable input size of the problem, right? So how to handle that Okay, that's the entire story what I will present today. Now, what I show two figures, one on the left and one on the right. Okay, let's start with the right figure, which is more common to us. Okay, this is a quantum circuit. Okay, on the right we have a circuit to execute, which comes from a given quantum algorithm, and this may be one instance of the algorithm, and we complete a particular circuit for that, for instance of an algorithm, and we have a good number of gates, right, good number of qubits, okay, to work with and to implement this algorithm. But whereas when you go to the left, we have a hardware, right, and this hardware is limited in number of qubits, and the way the qubits can be connected, or the qubits are being set up in the placement. Okay, so we see that maximally we have okay, two connected qubits, two adjacent qubits, right, all over. Okay, we don't have 3 adjacent qubits or 4 adjacent qubits in my topology. But still we have to implement entire circuit which has larger number of qubits in its logical gates. Okay, to implement here. If physical gates also, we have to we don't have okay, much more qubits rather than 2 qubits at a particular connected by an edge. Okay, and there are also few number of qubits for that. Okay, so what we can do, we can actually consider that, hey, we have an NISQ, we have several this type of machines available, but each machines are restricted in terms of their qubit size and the connectivity between the qubits. So if we assume that, hey, I can get a number of multiple machines of this kind, but each machine is a restricted size and qubit number, right, and qubit connectivity. Okay, that's the problem we are discussing today. Okay, and to handle this problem, what we have to do, we have to try to figure out that how this large circuit can be mapped to this scanty resource, but maybe a number of this scanty resource can help us in a process of distributed quantum computing, in a process that we can, okay, fragment the larger quantum circuit into small fragments, and can take this to each of these independent smaller quantum resources and execute them, and then we have some sort of way to reunite them and can generate the outcome. Okay, so that process we will be discussing now. Okay, so this is what is exactly, right. So this is called a circuit cutting, right. It is a physically like scissoring your circuit, right, across the gates or across the qubits, right, and trying to do smaller computations in each of the physical resources, physical quantum resources, and then in some process we are trying to gather the entire processing result. So it is something that it is something that circuit cutting, circuit partitioning, and then we are knitting the results. Okay, so it is okay, cutting, generating partitions, and then knitting the results coming out of the partitions. Now, if we look into this this paper, which is already there, right, which is published a year ago. Okay, Brent Hopper et al. Right, it's an archive paper. I think we have to search whether they have a formal journal publications, a conference somewhere. But this is a very good directions they have given in this paper, where they have said that okay, there are there are very fundamentally there are 2 ways we can cut a quantum circuit. Okay, one is cut by the gate. Okay, where if you see the top figure where we have the gate cut, right, what we do in the gate cut is that we have a circuit which is shown in the, let me use pointer, yeah. Okay, so this is a circuit which is the original circuit, right, and some way we actually partition the circuit across this this particular gate. Okay, this particular gate. So the Hadamard C0 and the second C0, across the second C0 we partition. So what happens? Okay, it happens something like that. That obviously obviously the first two qubits, which are having the Hadamard and the CNOT, are there. There is something we define as Fi1, okay, right? And again, for the partition, this is the partition 0, the top one, right? And then the blue color is the partition 1. And the partition 1, what we have something as Fi2, and then the third CNOT comes. Now the topic of discussion is that it seems that we have tried to partition this gate, CNOT gate, between the qubit, maybe if I take it's qubit 0, 1, 2. So between the qubit 1 and 2, the CNOT gate has been fragmented into some sort of operations, okay, which are this Fi1 and Fi2. Now, how this can be conceptualized, okay? So this is conceptualized by some sort of technique where we can try to compute classically. We can do it classically also, right? Or we can have a sort of quantum communication setup so that once we know that this is a CNOT function, we know CNOT function. What's a CNOT function? So CNOT function means that if I look this as a 1, right? This will be set. This will be inverted, okay? Right? And if it is 0, it will not be inverted, okay? So state will not be inverted. So what I can do, that means I can try to know what is this particular qubit, right? And accordingly, I can actually set this, okay? Set this particular qubit value, right? Or I can have a logic where I say that, hey, if I have a 1 here, right? If I have a 1 here, then you place a NOT operation here, okay? Something like that, right? I try to measure that what is this qubit, and I do this because ultimately maybe the result may be something we are expecting in the partition 1 or any other qubit. That means I can already get the result here, okay? So there are multiple ways this can be done, but this is the scheme. This can be quantum teleportation also in some of the cases where we can teleport the state here to here, and we can build another qubit line here, and we can construct a CNOT gate to actually work it out, okay? So something like that we can do. There are several processes there to do that, okay? And there is another. I will come to more details on this when we go to the next paper called QSim on this particular work. And then there is another thing which is called that is fragment across the wear, okay? Wear cut. Okay, so wear cut, what it means is that, hey, this is the circuit, and then what I do on this particular wear, right? The wear number, maybe it is the 0 qubit 0, this is a qubit 1. So across the qubit 1, we just separate it out. So what it means that okay, this particular both of the partitions are having, okay, 2 qubit here. Okay, the same gate operations are preserved, but here we have an extra where we have to generate here, okay, to pass this information to here, and this can be done by teleportation, right? Or we can do it by measuring and setting up this particular qubit here once again, because ultimately, as per the circuit, this qubit is acted upon on this particular point, okay? So there are this paper in the way defines various quantum and quantum classical processes, okay, by which we can actually cut the circuit across the gates and across the wires, and we can actually execute the circuit in 2 different quantum systems, because the partitions will be working on 2 different quantum systems separately, okay? Okay, but this doesn't tell us much about the unification of the results and how the results will be computed. Okay, that means on the approximation, results will be estimated on each of the qubits in a separate way. Okay, now the next more step towards this particular way of circuit cutting was actually proposed by a paper called QSim, which was also, I think, in late 2023 or maybe early 2024. Okay, where this okay, this problem was being more emphasized. Okay, so the problem of the circuit cutting has three things to be done. Okay, one is that, hey, what is the good location to get cut? Okay, obviously, I think the previous speaker spoke about entanglement, and that is one of the key issue that we should make a cut in those particular lines which has a minimum impact, okay, for the entangle gets or the entangled qubits. Okay, the entangling gets or the entangled qubits. Okay, so if we can avoid breaking entanglement, it's the best. Okay, that's the obviously a thumb rule, but still we have to okay, so the cost of circuit cutting, we have a formal notion of the cost of a circuit cutting, which obviously incorporates the entanglement into consideration, right? It also incorporates the number of wires getting cut in this particular okay, partitioning, right? And there are some other properties are there. Okay, so obviously finding the cut location and how many cuts you have to do, it depends on how many gets you have in the circuit, how many qubits you have in the circuit, and what are the actual physical resources where you can execute them. Okay, so obviously there should be a balance between the physical resources and the number of cuts you generate. Okay, so that once you cut the circuits, it becomes pretty easy, okay, to execute those partial circuits or those cut circuits into each of these physical quantum machines. Okay, the next challenge is obviously, these are all the problems in respect to the cut, and I will go into a little bit into when I discuss the research challenges at the last on this particular issues. The second is that quantum processing, what we need to do, because you need to do some extra processing. You cannot say that there is no free lunch, right? You cannot tell that, hey, I am doing circuit, I'm cutting the circuit and I am distributing it to multiple quantum processing elements, QPEs, right? And it is just done very simple way. No, it's not like that, right? You have to do some extra quantum processing, maybe quantum classical processing you need to do, and that also has some sort of process which you need to think, which you need to plan for a given circuit. Okay, and then obviously the classical post processing, that is once you go to the measurement and once you go to the density of states or the probabilistic measurement, right? How you generate the distribution across the multiple qubits, which was there in a single circuit, and then the multiple qubits they are distributed in various circuits, and how we again regenerate the distribution. Okay, because quantum result is nothing but a state distribution. Okay, when you measure it, once you measure it, okay, it becomes a distribution. So how to regenerate the distribution across multiple circuits and create a single distribution, that is the quantum post-processing. Okay, so let's look into the steps. What do we do? Okay, so what I show in the figure here is that in the figure here is that it means okay, we have a very example quantum circuit which involves two unitary transformation, each of 2 qubits. One is on the upper half of the circuit, and another one is the lower half of the circuit, right? And then we do a cut in the second line of the circuit. Okay, now what actually does in the second line of the circuit is that what we have to do here is that we have to either do some measurement on this particular qubit where I get cut. Okay, right? And we have to reinitialize the state in this particular qubit line, okay, for the get U23, right? And if we can measure it properly and reinitialize this properly, then probably the outcome what you're expecting in all the qubits line, okay, of the partitioned circuit and that of the circuit non-partitioned will be same or will be very close. Okay, and then we have achieved our target. Okay, if we can do that, then we have achieved our target. Okay, so so this is the thing what is to be done with a little bit, with a lot of importance in the circuit cutting, that how we can find out the state in this particular line, and then how we can initialize the state in this particular qubit line. Okay. So this is a little bit of that means that mathematics which we have to just take care that how we do it. Okay, so let us try to find that we have a state psi, right, and we have that we have an identity operation that is on n qubits. It's an n qubit operation. It's an n qubit state psi, right, and we generate the same psi. So psi equals to I operator psi. There's no problem. Okay. And now this I we can represent by this particular notation, the Bra and K notation of a particular operator B, right? And this is same which is as I. Okay. If we do the this product, the inner product of this, it will generate the I. Okay. Right. And so this is what is a line. Okay, a qubit line, right, which connects between two gates, right? We can visualize this as an I operation, because this is we can consider that there's there's no change in the state, but that is actually an I operation. Okay, it's identity operation, right? And this identity operation we can actually decompose. So what we show here is that, hey, this is the entire computation what we are doing on this 3-qubit quantum circuit. Okay, so we can tell that, hey, I initialize the 3-qubit quantum circuit with 0, 0, 0. Okay, first I operate between U12 between 1 and 2, and then I operate V23 between 2 and 3. Okay, so now what I do, so now this particular line is coming after we operate the U12. So I just try to expand this in a way that, hey, this particular circuit is nothing but this expression. Okay, operate on U12, and then this particular I is decomposed into something like this. Okay, some operation B. Okay, and then we separate it out, and then we try to say that, hey, this part of the circuit, okay, which operates on 2 and 3, 2 and 3 goes here, right, and this part of the circuit which operates on 1 and 2 goes here. Okay, so what happens is that your psi 1, 2 here is some operation like this, right? And your psi 2, 3 is some operation like this, okay, right? And then this particular psi, what you try to generate at the outcome at the end is nothing but the tensor product of this operation and this operation. Okay, this psi 1, 2, right, and psi 2, 3. So this is the so what it actually guides you is that there is a way by which we can partition the where, right, and we can define it as some sort of quantum operator formulation, right, and then we can define the sub states in the fragment quantum circuits, and this can be again united, okay, with a tensor operation, okay, to actually find the entire psi state of the circuit. Okay, now if we want to go into the greater details of this is the operation. So here I show two partitions, and this can be extend with n partitions, right? If we do n partitions, we have to do a tensor product of n subcircuits, and we have to generate the outcome at the ultimate outcome of the psi states. Okay, now this is the formulation what I show here. Again, this is the same thing. So if I have a single qubit connectivity between the single qubit line, which actually we can tell that, hey, U is the part of a partition 1 and V is a part of a partition 2, right? So how we can move this, right? How we can do certain measurements at U and then reinitialize this at the V, right? So this is the way how we try to understand what is the state operating at U, and we can do a measurement across all the bases, okay, I, X, Y, and Z, okay, all these bases. And if we take a trace across all these bases, right, if we take a trace across all these bases, and there is a mathematical, I think this is the way you can generate a trace across all the bases, which is called a tomography, right? And then based on the tomography, you can try to find out that, okay, what is this phi state, what is this, okay, this particular state, okay. Now based on this particular state, you can initialize, based on the measurement, what you can do here, you can initialize this particular state as any one of the state, 0, 1, plus minus 1 and plus minus I. Okay, so this is a coordinated okay, that means work you have to do. Okay, so you have to first measure this state, right? Based on this, you have to initialize this particular state, which actually starts with the next with the partition where you have cut the qubit where, okay, right? And these are the details mathematics. I'm not getting into this. There's a very beautiful paper called QC, right? You can go through that, and they show that how there are different ways you can do different type of circuit. There are multiple cuts you can do, and you can again you can actually reinitialize the eigen vector, right, of the cut qubit. Okay. So that means if anyone tell me how much time I am left with, okay, right? If anyone can tell me, it will be great, so I can know that how much I can continue for this. Okay. So summary is something like this. Your measurement 5 minutes. Okay, good. Okay, so I have to finish fast. Okay, so this is a summary that X, Y, Z are the basis, and based on the basis of measurements, you can do do this computation, right, and try to find out the probability of the, if there are multiple qubits, each qubit can be having a value 0, can having a value 1, or can having a value 0 plus minus 1. So this is the this actually is a 0 plus minus 1 superposed input. Okay, or it can be a plus I or minus I, something like that. Okay, so plus I. Okay, so based on that, you can initialize each of the qubits of this particular circuit. Okay, so I will just skip it a bit. Okay, this is already being. I will tell you that what are the works we are doing very quickly. Maybe I have 5 minutes, so I will just finish within 1 minute each of the work. So this is the work which is called this IQUR, which is the reduction in terms of error reduction, quantum error reduction. So what we did, if we try to look into this work, okay, this was published in SEM JETC, I think a couple of years ago. Okay, so the work what we did here is that we actually try to look into the circuit parameters, which is the feature space of the circuit, and try to decide that where I will cut the circuit, because if you don't cut the circuit, what happens is that that means your error gets more and more, because your that means you cannot have the qubits to accommodate the circuit. So you have to cut the circuit at some point of time, right? And but when you try to cut the circuit, right, it will be governed by an error threshold. Okay, so we look into the quantum hardware. We have all the pre-measurements of different types of circuit feature space and their errors in the IBM quantum hardware, right? And we listed those errors, and we use a machine learning approach to find what will be a good cut for the circuit to reduce the error. This is the first work. I'm skipping it a bit, right? Yeah. Next work was a QC, where we tried to go not go into the machine learning approach, but the machine learning approach requires a lot of exhaustive search in the feature space, right, and try to find out the mapping between the feature space criteria, parameters of a quantum circuit, and the physical parameters of the quantum machines, right? So then we focus a little bit different work. So what we try to do, we try to form a sort of weighted graph, sort of stuff, right? And we try to look into the balance factor of the graphs of the circuits, right? And try to use a sort of genetic algorithm sort of technique, okay? I think it is some, this is some sort of objective function we try to propose, objective function of this cut, okay? That is involving the features of the circuit, okay, right? And we develop some sort of cost model based on the physical cost of the circuits, right? And try to use a sort of different types of optimizers, okay, to find the optimum parameters in the search space, which will converge to a particular cut in the particular circuit, okay? So we use different types of optimizers like quantum annular, genetic algorithm, right? And then it was a graph partitioning problem, but the difference was that the graph partitioning problem was actually defined on a double the graph has the cost parameter in the node also, and the cost parameter in the edge also. So there's a qubit cut cost and there's a get cut cost, so both were being combined in the graph, right? And that was the specialty of this particular algorithm. And we tried to compare with different types of algorithms, and we tried to find out that how we can go with different types of quantum circuits, okay, right? And then we propose a real simulator, right? This real simulator was incorporating all our cut QC problems, all our quantum cut algorithms. We actually distributed a quantum circuit into multiple quantum machines, multiple virtual quantum machines, and a compiler for that. Okay, we require a compiler, right, which will follow the things what we have already developed, right? And we'll partition the circuit and we'll place it place to the different resources. And this parallel compiler was also being done. I think this was also a research paper what we did. Okay, and this was called QR zone, right? And the last work which was some of the members of our group, which is a combined group of Indian Statistical Institute led by Professor Shushmita Shurkule and Calcutta University led by me. Okay, right, and we actually did some sort of more work on this particular work, where we tried to define this as a sort of noise and time aware distributed scheduler. So we tried to extend this. We tried to use a formal ILP, because these are basically offline. We can decide there's no online. There's not much online component in the execution of the quantum circuit at this point of time. So we had defined a sort of ILP where we took all the temporal requirement is also there, and that error requirement is also, that noise is also there, right? And we tried to make a more extensive cost function, okay? Extensive cost function. And I think this so now there are two knobs in your user end. We know that error and time are the knobs we give to the user. Okay, so the user tells that, okay, that means in my distribution how much error I can go with, and how fast I want to converge my circuit. So this, based on these two inputs, okay, the objective function, okay, that means optimizes the circuit cuts, right, and tries to fragment out this the circuits, and it worked, and it worked well, right? And we had lot of this experimentation we have done, okay, right? And there is some sort of score is there to validate. That's called Mapomatic score, which is given by IBM, I think, okay, IBM hardware, which actually tells that what is the mapping of a given circuit with a given quantum hardware. Okay, so if the mathematics score is high, it means that the circuit will run in this particular hardware. Okay, so we validated this particular work with the mathematics code, and we found that most of our scheduling algorithm gave a good mathematics code for most of the quantum machines, for most of the partitions we generate out of the circuits. Okay, so this is all. I'm again trying to a little bit a lot of that was how we estimate the objective function, right? As it is an ILP solver, okay, we have to find a suboptimal solution. Okay, yeah, it's optimal or suboptimal solution of in the sort space with this particular ILP, right? Okay, so these are some of the results. Okay, right, and at the last, I think there are there are certain sort of we still didn't actually we still actually worked on the mapping of the qubit hardware in terms of the qubit resource, in terms of the error, right, and in terms of the timing of the hardware resource. But there are some inherent placement parameters or placement properties of the different hardwares. We didn't work on that still. So that will be more close to the hardware, more close to the technology mapping of the circuits. And people are now using very efficiently. We have seen some of the works from other groups where they're using this techniques of teleportation, techniques of dynamic quantum circuits, where they're partitioning not offline, but they're partitioning online. Okay, that means okay, considering that the resources can it can be high or low in the runtime. So how we can do it in the runtime, how the scheduler can do the things in the runtime, those are some of the things we need to work on and need to move on in this particular research. Okay, yeah, I think I will. Yeah, shadow tomography is one of the things that instead of measuring all the qubits and trying to measure the entire thing, we can use a sort of machine learning, or we can go for partial tomography of some of the partial knowledge of the quantum of some of the circuit cuts, and then we can go ahead. So some of the things which are coming up in this domain also are very interesting. Okay, there are a lot of things are there okay, to work out in this particular domain. This we have just started for the last, I think, 2-3 years, but I think this is a good domain, and I expect that the researchers will join and will try to contribute in this domain much more, right? And in terms of HPC and quantum handshaking, I think this is also one of the best domain, because you require an HPC to run the scheduler to decide this scheduling algorithm, right? And then place this quantum operations selectively into this NISQ QPs. Okay, this is the entire motivation of this research. Thank you. I am done. I can now go for questions, if any. Yes. Yeah, Akshay, any questions? Sure. Yeah, so how to take this? Yeah, please go ahead. True. Yeah, so HPC will be utilized for the offline simulation, sir. Okay, it will be for the offline simulation. So we so for a given problem, suppose I have a given problem and have a large quantum circuit, and we have a certain set of quantum resources, right? We have to figure out a solution for circuit cutting. Okay, so I think machine learning is one of the quickest way, but I think there are other optimization functions also, where we can actually use offline the entire strategy, plan the entire strategy, and then push it in the real time into this quantum hardware. Okay, so that is one of the way we can use this HPCs. Okay, to do the offline solution of the circuit cutting for large circuits. Yeah. Okay, thank you. Bye. So taking off, huh? I'm taking off. Yeah, sure.
Gupta sir, who got the Bombay in 2014. Following his doctoral studies, he joined IBM Research in Bangalore, where he has been working since. Dr. Das Gupta has contributed to diverse range of fields, including power system dynamics, renewable integration, data science applications in agriculture, and carbon footprint estimation in cloud data centers. For the past 3 years, he has been associated with IBM Quantum, focusing on applications that can provide quantum utility. Thank you, Dr. Das Gupta, sir, for your valuable contributions and for being with us today. Let's welcome him on the stage for his session on IBM Quantum.
So good evening, everybody. So I'd like to thank C-DAC, SIT, Amit, Vishu for inviting me here. I had a very pleasant stay. So today my topic of my presentation is, although it's IBM Quantum, I've written IBM Quantum, but the focus would be on QCSE. QCSE stands for Quantum Centric Supercomputing. Okay, so IBM has a goal of reaching QCSE by the year 2033. So, but we are making progress on that direction as we speak. Okay, so before I talk about QCSE in specifics, I would like to take you through the roadmap that we have. So I think you have seen this roadmap over the course of our of the various talks that you have come across today. So so initially we started in 2016 with 5 qubits, and that was the first time we had a a system on the cloud, and people were able to access them 5 qubit, although 5 qubit, but it was there in the cloud, and people were we kind of democratized usage of quantum computing right from 2016, right? And then the initial focus was on building larger and larger systems, like systems having more number of qubits. So it started with 5, and the target was by 2023 we would have 1,000 qubits. And our systems are like the machines are named after cities, and the processors are named after birds. Okay, so you can see the eagle, and the eagle had like 100 qubits, and then you had I guess the heron, like the heron processors now have around 133 qubits. So the one thing you must remember is it's one thing to have lots of qubits packed into one quantum processing unit, QPU, right? And it's another thing to have high quality results, right? So what we found out was like the Condor that we had, right? The IBM Condor had 1,000 qubits, but it was not kind of it was not meant for utility, especially because you had lots of errors there. Right? So what we decided was like instead have smaller number of qubits packed into a processor, but they should become modular so that you can connect them together to form a larger system. So you see, although you have that Heron processors here, but they are meant to be interconnected with several other Heron processors to form a larger system. Right? So we are right now in 2023. So I would move to kind of take you from 2024 to 2033. So the focus is mainly on how many gates you can run, right? So qubit depth is a concern for us. So right now we are at 5K, like 5,002 qubit gates. So if you look at Heron, right, like 124. So the plan is to, the next set of processors will be called Flamingo, which will be like, around 6K and then maybe move to 7K and then 10K with Flamingo itself, but 100 million with Starling and 1 billion with Blue Jay. Right? Oh, sure. Yeah. So you have Heron here at 5K and Blue Jay here at 1 million. So that is a 2033 goal, right? So along with increasing depths, like having larger number of gets to process and having higher number of qubits, one thing we should notice, like the error has to go down, like the qubit gate errors, the T1 coherence time, that should increase. But more importantly, we need, the target is to have error corrected qubits by 2029. Okay? And the associated, the software side as well, like having serverless, having circuit cutting knitting. I think Professor Amlan was talking about circuit knitting cutting. So all should come in. So we also need AI services like the transpiler. So transpiler is basically when you map your let's say you have written some code, right, and you have some qubits and you want to map them to the actual hardware, the qubits of the hardware. So that is a graph theoretic problem, and it's not classically hard problem. Right? So there you would need some high performance computing as well. So this transpiler service, and you're also looking at something called using our generative AI to do Qiskit code assistant. So where researchers and scientists need not write the code manually. They would just say, write me a code for some chemical simulation, and the code you get it, right? So that is also in the process. So we have our own generative AI. So we are using it. We call it Granite. So we are using it to work on all those things. But the target is 233, where we need to have quantum-centric supercomputing, where we believe that very complex workloads, right? Very complex work, like for example, solving a molecular simulation or some say healthcare problems like drug discovery or whatever, right? So that requires quantum alone won't be able to solve it, and I'll show you why. So in some later slides. So we will need classical resources. Like even in 2033, we are not going to do work with quantum alone. So we will still need, machine learning, AI, and high performance computing to work with quantum to give us good results. Right? So that is the target. For that, we would need seamless connectivity between classical resources and quantum resources. So this is the kind of architecture. Like this is a very broad level architecture where you see you have GPUs, CPUs, and QPUs working together. So QPUs will have some classical units also inside, like the runtime cluster. So so this is the dilution chamber. The QPU will be here, and here are some classical resources will be here, where you basically parameterize circuits, and so basically you have the circuit cutting and knitting that the previous speaker was talking about. That would be done here, right? And if you're calculating, let's say, expectation and processing the sampled results, so that also requires some classical resources. So that would be done here in the runtime cluster. And besides that, you would also need CPU and GPU for doing some other part of the work, right? Other part of the the bigger work, right? So this is the overall picture. So delivering impactful quantum computing requires the interplay of quantum and classical resources. So quantum alone won't be able to do it. So that's why we are talking about quantum-centric supercomputing. So I would like to show you one video here. So this is how the plan is, right? So you have a user, he writes some, there's a cloud, there's a intelligent orchestration. The orchestration is the circuit cutting knitting part, you can say. Okay, so let's say you have started a job, right? You write a code, just send it over, right? So let's say these are unitary gates. It goes to the cloud server here, right? And here, what will happen? You have the orchestration where maybe circuit cutting, the knitting, entanglement, forging, all those things, and that will require some cloud, classical resources, and also the transpilation part that I was talking about. So once that is there, what will happen is the circuit has been parameterized, the circuit has been divided, decomposed into multiple circuits. Then it will go to the, it will be, let's say, divided into multiple circuits, let's say, one big circuit. Then it will go to quantum runtime as a service. And then it will go to the quantum data center. And the data center has the dilution chambers as well as some, some classical components. So the results have come out, let's say, from the dilution chambers in terms of bit strings. It will go to the runtime service again. So where the expectation values of the parameterized circuits will be, evaluated, and the final results will come out in the form of a quasi-distribution, quasi-probability distribution. Right? So I hope this was clear. So essentially, what we'll have is we'll have some classical HPC Also, we will have some AI infrastructure, and we will have some, quantum. So the term you must have heard of, like quantum AI. So this is essentially what quantum AI should be, right? So you have AI infrastructure, classical HPC, and quantum all working together to give you some solving very tough problems. Right? Now, so we have already some tie-ups, right? So with University of Chicago and University of Tokyo, where we plan to have a 100,000 qubit quantum-centric supercomputer by 2033, and IBM is already investing so many $1 million. And like University of Tokyo is specializes in applications, and University of Chicago also has some expertise in middleware, kind of orchestration and all those parts. Right? So this is one, this is one collaboration that we are looking like we have a lot of hopes on, and hopefully by 2033 we would have some very large system working together. Okay, so let's see, like how HPC and quantum could work together. So mainly HPC plus quantum workloads can have three different ways of working. Like one is HPC for quantum. You have some quantum task where HPC could come in. You have, let's say, quantum in HPC, where you have a bigger HPC problem where quantum could play a smaller part, and quantum about HPC. So right now we are at quantum about HPC. See, HPC for quantum and quantum in HPC would require very tight integration of quantum resources. Like quantum and HPC resources should reside side by side. Okay? And all the job has to be done within the coherence time. So if you remember the last question I asked Professor Amlan was, like all those circuit cutting and all, will you be able to do it within the coherence time? So probably the answer is no right now, but it has to be done in some time. Like, so when you have very big circuits and when you want to, let's say, have circuit cutting knitting kind of operation on the fly, right? So you will need to have very tight integration between quantum and HPC resources, and on premises, they should reside side by side. And similarly in quantum in HPC, so we have some very big problem in HPC, and you want certain components of the work to be done by the quantum resources. So quantum resources for acceleration, let's say, and that also needs on-premise integration. And right now we are at this stage, quantum about HPC, where they are not tightly coupled, but HPC does some pre and post processing tasks, and quantum will do like the main. I mean, they are kind of decoupled right now. So quantum will do the job, send the result to HPC, and HPC will do something and then again send it back to quantum. So the classic thing is VQV right now, what we have. Right? So I mean, you could go through this paper here. They have described all these things very nicely in this paper. So the perspective paper, where quantum centric supercomputing for material science was discussed. So I'll give you the basic layout of VQA, right? And this is kind of getting outdated already. So I'll talk about another method that is being currently used for as this quantum about HPC, right? So you know VQE, right? Many of you have probably seen this picture, right? So you have you have a quantum part, you have a classical part, right? And what happens is, like, you have this ansatz. So basically you create your circuit, right? You have a particular problem where you encode. The encoding could be like, if it's a chemistry problem, it could be like occupation number basis in second quantization. If it's some machine learning problem, it could be some amplitude encoding, phase encoding. And then you have an ansatz. So essentially the job is to, you have a Hamiltonian H and you want to find the lowest eigenvalue of this Hamiltonian. So what you do is you start off with a good reference point, which is kind of close to this lowest eigenstate, let's say, and then you have an ansatz that is supposed to take you further closer to the lowest eigenstate of this Hamiltonian, right? And then what you do is measure, and this measurement value is then passed on to a classical optimizer. The classical optimizer then updates your parameter and sends it back to your ansatz here, which is parameterized with this with this theta here. So this is how the cycle goes on, and there's a time when the classical optimizer is satisfied and says that, okay, I'm good with the results that I have. Now give me the final result. So like the parameters have been optimized to the classical optimizer's satisfaction. Then there are several ways to design this ansatz. You have domain inspired. The chemistry, some chemistry problems have domain inspired ansatz. They are hardware efficient, like ones where the circuit depth is less, but nonetheless they are quite efficient. And of course you have QA, which is like a time evolution kind of an optimizer. Also you have gradient based, non-gradient based kind of optimizers. So this is something that you already know of, right? But there are some problems. I'll tell you why with this kind of an approach. Right? So first of all, this was the paper, the recent paper, which is a collaboration between IBM researchers and Riken University. They took up this problem of finding the ground state of this molecule Fe4S4, okay, iron sulfide. So, the number of qubits used for the simulation of this molecule was 77. And this molecule is so large with this kind of qubits, right? You would have like 67 lakhs or 6.7 million polystring operators. The Hamiltonian that I was talking about can be broken down into these many polystring operators, right? And the precision required, if you were to reach within chemical accuracy is 10 to the power minus 10. And if you use VQE kind of algorithms, right? So if you are to reach within that certain level of accuracy, you will need 10 to the power 20 kind of iterations, right? Like circuit runs. And if you go by this is a reasonable kind of an approximation, 10 microseconds per circuit, you will need 3 million years to solve this problem with the VQB that you have, which is kind of impractical. But with the approach that they have taken, like where quantum and classical was used, not the VQE approach, I'll show what it is. So you can solve it within 2 hours. And they have used around 3,500 2-qubit gates and 10,000 gates overall. They were able to solve it in 2 hours. So there is a, this is a, what is it? NISQ. So IBM now stops, doesn't use the word what is it? An intermediate scale quantum. So let's say it's called pre-fault tolerant and post-fault tolerant. Let's say so. This is a pre-fault tolerant kind of a algorithm VQV. So, but the post-fault tolerant, the fault tolerant kind of let's say algorithms would still require days. So if you use some error mitigation, error correction like surface error correction, even that would require days to solve. But with QCSE, you can solve it within 2 hours. So I'll just, okay, so this is the paper I was mentioning, this chemistry beyond exact simulations on a quantum-centric supercomputer. This was a work by Riken University and IBM. So where Riken University used their supercomputer, the Fugaku supercomputer, and IBM used the Heron processor. So this is the approach, right? So what you have is, you have the same, setup where you have a reference state and where you have an ansatz, and you just sample. Okay, you don't directly find the expectation, you just sample. And this sample, let's say call it X, right? You create a distribution of this bit strings, right? And using this bit strings, what you do is you create a subspace, right? And this is commonly used in chemistry, actually, this kind of a method. So let's call this a projection subspace, right? So what you do is you then kind of, project your Hamiltonian to this projected subspace, right? So you say that these are good bit strings that I am getting, and my final answer is going to be a linear combination of these bit strings that I am getting, right? So my answer is going to lie as somewhere within the, as a linear combination of this bit strings. So if I create a subspace using these bit strings and then project my Hamiltonian into that subspace, right, and then diagonalize, then probably it would be, I'll get the correct result. So what is happening is, classically, you can't diagonalize a very big matrix, right? Very big Hamiltonian. So quantum, what it does is gives you some samples, and you have kind of reduced the size of your Hamiltonian, and then the classical kind of goes and diagonalizes. Okay, so this is the main approach. So essentially, some equations, maybe I'll just run through quickly. So some optimization problems. So essentially, once you solve it, right, so what you get is, this kind of a problem where your HP cap is a projected Hamiltonian, right? And your parameters that your, let's say this UI is your bit strings, and your lambda min. So which is kind of yeah. So I'll just give you an example. Instead of writing the equations, maybe I'll just give you how it is done, right? So let's say your bit string, let's say your ansatz, your quantum circuit churns out this bit string. Okay, so forget the alpha, beta. These are in chemical, in chemistry, you have this alpha electrons and beta electrons. You have probably studied in your +2, the arrow pointing up and arrow pointing down. So the alpha and beta electrons. So let's say these are your bit strings. Okay, so there are chances that your bit strings will be wrong. Okay, some incorrect samples. So see with those occupation number basis, what happens is like the number of ones gives you the number of electrons in the system. So this has to be conserved. You cannot, like for example, if there are 2 electrons, you cannot have 4 ones. Okay, so it has to be 2 ones. So you have to correct this sample. So this is called configuration recovery. So there's a big chapter on that in that paper. So maybe you can go through that paper. So first of all, you have to correct those bit samples, bit strings. So your quantum hardware will churn out some samples, but you have to correct them. And once you have correct them, you have to, let's say those are denoted by U's, let's say U1, U2 to UN, right? And then what you do is, let's say you have a Hamiltonian which is of the order of 2 to the power m cross 2 to the power n, m being your number of qubits, right? So your Hamiltonian is huge, 2 cross m cross 2 cross n, right? So, but then you have collected only n samples, which will be, let's say, is very, very less than 2 to the power n. So once you have projected this Hamiltonian H cap into HP cap, right? Look at how it has been done, right? So this is the pra and the H and the ket here. So this is, if you can reduce the size of your H, right, to an HP, which is like of the order of n cross n, which is much, much less than 2 to the power n, then it's kind of easy for the classical system to kind of diagonalize. But like in this case, like they collected millions of samples and get this subspace and then to diagonalize still required a supercomputer. So they use the Fugaku supercomputer, for in that case. And this is the paper actually. So so you have this IBM Heron processors using 133 qubits. They use 77 qubits, so many gates, so many 2-qubit gates, and the Fugaku had this many nodes and so many cores. And this is the paper, and you could see they worked on iron Fe4S4. They also worked on some other molecules. This is like the bond breaking they showed for nitrogen molecule, right? And they clearly showed that it works kind of better than the CCSD, the classical CCSD approach. Of course, the best classical method is HCI, like heat map configuration interaction. They were not able to reach there, but they were better than other classical methods in some sense. So you have already reached some level of utility, right, using quantum computers and supercomputers like working together, right? So yeah, that's about it. So I hope it was informative, and I'm open to questions and answers. Yeah.
The Rayleigh-Ritz method is only applicable for particular quantum algorithm, or it is
applicable to any optimization problem. You have a Hamiltonian, you want to project it to some subspace, but you have to remember that your certain properties are not violated. Like in this case, the chemistry problem, the property was the number of ones have to be conserved, like because they represent the number of electrons, which is kind of fixed for this molecule. Right? But in your problem or some other problem, that could be something else. So you have to take care of that.
Already on the HHL algorithm, this is a Rayleigh-Ritz method is applicable, but I haven't seen it is applicable over other quantum algorithms, like the variational quantum algorithm or QAOA. That's also be not used.
QAOA is very hard because QAOA, see, if your Hamiltonian is big, right, you do e to the power IST, it will never end, right? It's a huge circuit. But here it's an ansatz, right? So which is kind of let's say
dummy variable.
Yeah, you're not doing the QA. QA is a totally different approach. Here it's more of a good short depth kind of an answer. So here they use something called LUCJ. So cluster Jastro they call it. Okay, LUCJ. So that kind of an answer is not very deep. It's excitation preserving in the sense that the number of ones are preserved. Right, you have some Gibbons rotation kind of an operation, like a unitary operation, so that the number of ones are preserved, and then they get the bit strings. But if you are doing the QA approach, then it's very difficult because e to the power IHT will be very big, right? And you also have non-commuting terms, so then you'll have to kind of keep running the circuits again and again, like multiple circuits. I mean.
So another question that in the big data and the classical data, so we are thinking about the Hadoop and management of all the data. So can we think the similar kind of process in this one?
I'll have to look at the problem. But if you have a problem to matrix to diagonalize, if you can distill down your problem to that, this approach can be taken. Okay.
There's a flight to catch. I'm sorry.
Maybe we can take offline questions.
Yeah.
There's no offline questions. Yeah, please.
So in one of your slides, you showed the generational change of quantum computers that IBM is offering, right? And also you pointed out after a particular time you're scaling to distributed quantum nodes.
Yes.
Is that like a dual layer qubit? That was one type of question. The other one was, are you taking any architectural changes in that?
Yes, that's a good question. So normally, so see, the target is to have error corrected qubits by 2029. So that would require certain form of coupling between qubits. So you have this. So IBM, like we have decided to use this LDPC-based error correcting codes. Okay, so we call it a gross code. So there would require coupling between qubits, and this coupling will happen not only within qubits in the processor, but when you have multiple processors, and this coupling will happen like between qubits in different processors. So you have the C couplers, L couplers, M couplers. You'll see, probably would have seen some pictures. I don't know. So all these couplers would be necessary. So those are the architectural changes that would be needed to kind of have error corrected qubits. Right?
When you scale to 1 billion, is there another change or?
So I cannot tell right now because it's an ongoing process. So right now we are targeting Flamingo maybe year by year. We'll take it slowly, right? I mean, but the hope is by 2033, 2029 we will have error corrected qubits. By 2033 we will have 1 billion. We'll be able to simulate 1 billion two qubit gates.
In the other slide, in this diagram, your communication between CPUs and GPUs, I think you're doing a little part of that today. So how are you connecting your QPUs? Is it a classical way?
Yeah, so right now we don't have a pipeline. So I was discussing with Amit. So right now it's not a pipeline, but one thing to remember is, so it's still a feedback kind of a loop in the sense that if you remember, like this bit strings were corrected, right? Bit strings were corrected, right? So this correction requires some information from some previous iterations from the classical results. So there will be some feedback from the classical, but that is kind of offline. Like we are not doing it kind of within the T1 or something like that. It's all offline, right? So you have the results, go to the classical, fetch the data, use it, refine it, again run the circuit.
This would be not like a GPU plus CPU.
Right, so they would have had a pipeline. I mean, in the sense that maybe they would have written a code that could do it, right? Like automated, but still like not a perfect kind of a pipeline where the quantum results directly goes to the classical. Like they would have to write a code to fetch it from some place and then give it to the classical, something like that.
And can we do GANs with the same technique? Two GANs.
QGANs.
Same technique. Because it's
okay.
Also...
Okay, so QGAN. So let me remember what GAN is. Like graph generative neural. Okay. So ANSAs are like one form of neural networks only, and there also you have some loss function you want to kind of minimize, right? So you can map that to this kind of a problem. Okay.
Thanks.
Thank you so much, sir, for such an informative session. To honor Dr. Kalyan Dasgupta, sir, I would like to call Dr. Ayesha Mullah ma'am to join us on stage for the felicitation. Our next distinguished speaker is Dr. Vidya Niranjan ma'am, a leading scientist and academic researcher excelling in computational biology. She is currently serving as professor and head of the department at RV College of Engineering, Bangalore, with over 30 years of extensive research experience. Dr. Niranjan has made significant contributions in big data, automation in genome analysis, drug discovery, and tool and database development. She has published 155 research articles with a notable H index of 19 and has secured research funding worth 4.34 crores from various government agencies and pharmaceutical companies. Currently, Dr. Niranjan is part of the NVIDIA Inception program from AI drug-based discovery and is working on a project related to quantum computing and protein folding funded by the Ministry of Electronics and Information Technology in collaboration with Amazon AWS. Thank you, ma'am, for your presence here and for your significant contributions. Let's welcome her on stage for this session for advancing drug discovery and genomics via quantum amalgamation. Thank you, ma'am.
Good evening, everyone. I know I'm the last speaker of this entire symposium, but I definitely is going to give you a different direction or different change in whatever that was done the whole day. Okay, and they're going to change the game. I'm not going to talk about more on computational side or algorithm side. Rather, I'm going to tell what are the roadblocks we have while doing life science projects and where classical mechanics is failing terribly because we definitely going to do that because we have the validated results in biology or life sciences and we have prediction. Sometimes prediction goes very well and that's why we tell that classical mechanics works, and where it is not working, then we are now going to tell you that quantum is the only method for us to start with it. So it's going to be much lighter than all the previous presentations. And I'm just going to give you a little bit introduction on so this is our panel of advisors. Dr. Amit Saxena is also our advisor. And from agriculture side, we have Suresh, who is from UAS Bangalore, Vice Chancellor. And we have Dr. Jitendra Kumar, Managing Director, who is also in the panel of advisors. These are some of the collaborations we have. So why I'm showcasing all this is we have a lot of experience in doing a lot of projects, service projects from many companies, or where we found out during implementation that some of the things are terribly failing. And that's why we told that we have a lot of experience in terms of pharmaceutical company as well as other company. And this is bringing us to use quantum as one of the tool now. So this is our total funding we have in the Center of Excellence Computational Genomics. And so I have around 2 decades in industry in the capacity of group leader. And the last decade I shifted towards academics and I set up my own lab there. The one thing where we do in academics, we work like a startup. If you come and see my lab there, it will be like a startup culture. So we have to, being a private college, we have to earn our own fundings and we need to work. So that is making more aggressive in nature. So this is our team. So I have 8 full-time PhD students who are working with me, with many interns also there. And one thing I have to tell, we have a very good computer science engineering department we have. So there are a lot of students come and work on this quantum computing. So this is one of the advantage we have to adapt. Usually if you see the biologists usually changing to the different technology is being a major challenge for them. So that was not a big thing for us because we are adapting to the technology very fast. So all these things, what I am telling, there is a purpose for it. Why did we shift to quantum? So these are the infrastructures we have. So we have started with HPC and then we have GPUs. We have 800 server in our college, and we are also getting from IonQ generously fundings to do quantum computing also. So these are the infrastructures we have to do our life science projects. And these are the other resources we have. And this is the ecosystem we have developed the lab to adapt to the new technology. And this is one thing which I want to tell you, where the lab is successful in publishing many papers, having many PhD students and a lot of projects, is how do we adapt to the technology? So initially we started with HPC. CPUs, big servers, where it took 3 months for us to do all the genome analysis or drug screening. Then we shifted towards GPU, and then we started working with GPUs, and then we used all AI/ML data analysis, and then we started doing kits. Now we are still finding a lot of problems with these things, and so we now shifted towards the quantum computing. So this is where I am going to start with the presentation. So these are the challenges in the life sciences, which I am going to throw to the quantum experts here. One is very important is the biological networks and systems. So here, when you consider as a systems biology, there's a huge challenge in the computational side with available resources of either GPUs or CPUs or hybrids, whatever we have, because of the maximum cliff problem, which helps identifying highly connected clusters. So when you consider as an organs or tissue, and when you want to connect it, it is a huge problem we are having. Still, there is a lot of scope in systems biology by using quantum computing. And another is de novo assembly. As you all know, the genome, I don't know how many people here can understand biology. The genome, whenever we do sequencing of the genome, to assemble is a major problem we have. And using normal HPC clusters, it's very difficult, and we are not getting a good. But I think now we have started working with NP hard graph problems, like Hamiltonian path problem, and we have started working with it, and we are finding some improvement in the genome assembly. And then another is quantum approximation optimization algorithm, or variation quantum algorithm, which provide new methods for solving optimization problem, which is more efficient than classical things. So this is one of the area where quantum computing can make a big difference. And the other thing with these three, these three are still, we are not having a hold on it. Anybody interested in these problems, we are open for collaboration, but we have started with protein folding. That is, classical approaches are computationally expensive for large proteins, because when Kalyan told that only 77 qubits for proteins, we need much more than that, because any protein will have at least 300 amino acids. Where do we go for 300? It's very difficult for us to have such resources. So that's a major problem. I'll tell you how did we solve it also in the next slides. And the molecular docking region. So in the morning, told there is no drug for COVID. Okay, it's only repurposing of drug. That is because the idea regions which cannot be solved by classical problems. This is in what is idea region? I'll tell you. Whenever the host, the viral comes to the host, these regions will not be stable. It will go on change. Whatever drug you prepare and give it, it has a very good mechanism that it is not stable and the drug is not effective. And that is why COVID, there is no drug. These idea regions are very, very important. For the next outbreak, at least quantum should mature enough to solve this idea problem and have the better drug for it. And also the faster identification of potential drug candidates, because whenever the outbreak is there, you have only 1 month to have this thing to give it back. So AI/ML is very important in that particular scenario, where we have worked on many papers on it and try to have the drug faster. So if you see that there's a huge problem right from genomics level, if you consider the health, there's a lot of areas where quantum computing can become definitely a better solution than classical mechanics. So this is first project we got from MIT, where we were sort of exposed to quantum computing, because we know that we have got only a few credits, but what we did is we started with using NVIDIA simulators and find out whether we have some answer for it, and then we shifted towards this quantum computing. So this is the first project we got, where comparative analysis of quantum computing. So here in this project, we benchmark between the classical mechanics and quantum mechanics, and we found out what are the gray area we had, how this quantum mechanics is giving a upper hand for us. So these are the two important papers we had. So the project is, so this is what is idea. This is one of very important problem that biology is facing about this idea in drug discovery. So this idea is a major challenge, as I've already told. So what happened? We are now getting into quantum computing. We had only one as a more of biotechnology expertise. We had only the papers to check and start working on it. So some of the papers told that VQ is better for peptide. But what happens in amino, if we go for such proteins, we have 300 qubits. So we need to still more do research and how to minimize that and how to get it. So what we have done is this configuration of protein folding. We did optimization here. We had only A and B and 2 planes. And we started, we just started with like this, where 2 points defining the position of each amino acid on a tetrahedral plane. So this is one of the minimization we have done. Because from A1 to A2, whenever there is 2 amino acids to have stable, what are the different ways that it can come there? So in that way we have started, and then what we have done is we have started calculating the Hamiltonian. So to have this stability between 2 peptides, these are very important. One is geometrical constraints we have took, and we took the chirality constraints and the interaction energy in terms of MJ interaction nearest neighbors. So these are the 3 things which we have used to understand that how exactly this particular idea regions can be solved. So for that, we had 20,426 human proteins. So we just scanned the whole protein database, human protein database, and we found out that 20,426 were selected, which do have this type of idea region. So then what happened? We found out that if we did an extensive analysis, so this is what is hybrid. So initially what we did is we found out that DHQKSEP, these are all amino acids. So these combinations are always present in this idea region. So instead of taking 300 amino acids and start analyzing that, we took only this 7 peptide. Because this is very important for us. If we solve this particular region of idea, we can solve the complete protein analysis we can do. So this is what we have done. So a selection of protein sequences, because of the constraint that we don't have 300 qubits, we did an analysis and we found out this is one of the peptide which will be very useful for us, and to identify that is important. So for that, we did 2 more things. We took only VQ because initially all the publication told VQ is the best way to solve this problem. So we did conditional value address, that is CVAR, to average over the tail of distribution. So whenever we are putting this into iteration, it comes to the tail and then stops there. That is in quantum computing. But still, this tail also has to be disintegrated and further analyzed for the stability of the protein. And then compared to conventional VQ, CVAR VQ provides a drastic speed up and optimization. So at the very initial level, we only had a choice of VQ, and optimizing it with CVAR is something which we started working to understand the protein folding. So because we should find out how exactly this idea region fold itself, so that appropriate drug can be discovered further, screened, and it can be discovered further. So here, if you see, we already know that in the classical mechanics, whenever we do simulations of this structure, so what we do is, depending upon its interaction, van der Waals interaction force and everything, we try to find out how exactly this protein can take up its shape. So we know that in classical mechanics, all the papers say that you should do a simulation for 100 nanoseconds, which is very expensive. Computationally, it is very expensive. We had a clue that while doing that, why do we do? Because when we get the plot, we know that sometimes it becomes stable, again it disintegrates, again it. So now we know that any protein cannot be taken as a structure as a whole. At different point of time, there is a change. So now we need to shift towards a probability of what is the structure at different instant of time. So that is what we have done here. If you see, when we see that classical as well as the quantum, we found out that 51% of the peptides, initially we were doing very extensive to understand what exactly the stability of that, but later we found out that 51% of the peptides reach minimum ground energy state at 50 nanoseconds. So whatever we are doing in the classical mechanics, considering that 100 nanosecond is not correct. Whereas the quantum gave us that at different 10 nanoseconds, what is the ground energy, and every, what is that it is not same like what we have done in classical mechanics. So this gave us a clear indication that the probability at 50 nanoseconds, the energy is what we need to take it for the stability of the protein, rather than taking in the classical mechanics the whole 100 nanoseconds. So this is something which we found out that the simulations should be done, and we need to cluster it. We need to find out the real region because we don't have qubits, and then we need to start for the drug screening. So here, if you see, we started Monte Carlo, which is nothing but the classical mechanics approach. We also worked on stochastic model, where it is a probabilistic. So we found out that if you see that DSP-KHQE, which is a very idea regions, which is not stable at all for any drug screening, we found out that at different nanoseconds, it has got a different conformation. So now we need to optimize this conformation for the drug screening rather than straightly find, which is going to have a negative impact on the drug screening. And this also, this is a probabilistic method taking care of many things, though it is, we found out it is much better than the probabilistic method. But if you see VQ-based solutions, what we have done, we found out that MD simulation or structured alphabet, that is probabilistic method, and VQ methods. If you see, VQ has got, we had a clue that the quantum computing is giving much more accurate results on the structure of the protein for moving towards the drug discovery. So this is what we have done, and this is the error rate. But one thing is, we found out that the error rate is very high. So one of our trainee who came from IIIT Allahabad, he told that why don't we start with all these Clifford gates, we can use it with T gates. If you change towards the T gates, the error can be minimized. So this was one of the breakthrough. This is how we develop our quantum computing. So we found out that if you see that the error minimization is very less with the T gates. We have not done at the algorithm level. We have done using our data. The T gates can have reduced the errors. We have to use T gates rather than other Clifford gates, so that we get a better reduced minimized gate. So if you see, this is one thing, and this has also been we had published in IEEE conference. And this quantum utility of folding of, then we took one of a very specific protein, ubiquitin C, which is very, very important. And we thought that why don't we do a benchmark, how it works with molecular dynamic simulation, which is classical mechanics. And we also used TN1 of quantum simulators, that is in NVIDIA. And then we used ARIA1 QPU, and we just did the benchmark. We found out that rather than using simulators in NVIDIA, though NVIDIA's told that the hybrid model may work better, but for us only the QPU worked better, and we had a better results of finding the exact structure of this idea. And this is also under, we have a review. This paper has also been under peer review. Some, they have asked for some error corrections, and we are working on it. So this is for next. So this is one very important, is to understand what is the structure of the protein, which is very important for the drug discovery, especially when there is a viral human interactions, how these particular proteins do not have a stable structure, which cannot be identified using the classical methods, and how the quantum mechanics helped us to understand the structure for better drug design. Next is we also want to find out the density function theory profiles. So what happens is the ground state energy for molecules with higher bond orders and with aromatic rings is very difficult for us to understand what is the density function there, because the density function is very important if you consider a protein or a molecule, so that it will give you a very accurate method of giving you a drug. So, and then differences is energy for various isomeric states. So one of the project when we took from our consultancy from Hindustan Liver, they told that these two isomers, what you predict that there is no toxicity, one is having toxicity and another do not have toxicity. They clearly verified with the wet lab and told that your prediction is wrong. So we were little offended and we found out why that is a problem, because in isomers, there will be a change in the bonds and the density function changes. So the classical mechanics do not capture these density functions for drug screening, whereas the quantum methods, while using this density function, we found out. Another is bond energy difference in various isomeric states leading in this HOMO as well as LEAS. So whenever we want to find out, it's not about the chemical formula. We cannot have it. It's about what is the isomer and how the density function is there before going for drug screening. So this is one thing which we have found out, and we have this is also accepted in IEEE conference, and it is under publications. So these are the tools we have used for that. And this is one thing very important we want to know is, till now only the single bond is being calculated. So if you see till oxygen, there is a literature telling that what is the theoretical value, what is its, how the density function. But we are the first one to start with double bond and triple bond. So at the ethyne and ethene, where you have double and triple bond, and it is very difficult for us with double and to understand the density function. We have already worked with it, and then we got error rate which is not much than whatever the linear bond is all about. So the conclusion is drawbacks. Hamiltonian time increases exponentially with increase in bond orders. If you see that ethyne and ethene, methanol, if you see, it's going to have. Still, we have attempted it, but we are not successful in finding the right things here. So we are open for here also. If someone can come help us to understand more about it, we are there. But this is a very important problem, especially if you consider aromatic compounds where the delocalization happens, and it is very important to apply the density function there in these aromatic compounds. So prediction of druggable properties, toxicity, brain barrier, all these things is whatever we have till now with classical mechanics is not it's not aligning with the wet lab experiments, that is validated experiments. So this is one thing which we want to do. And already we have done a very good tool of Proteo.net, a graph neural network based platform for talking score predictions, where we have used quantum AI/ML to understand how exactly it happens. Here, I think this Proteo.net is going to change because you can go through our tool where docking is no more needed. Here it gives a list of small molecules, gives a list of proteins, and it gives all possible combinations with the toxicity prediction, so that the drug discovery is going to be a very easy step for people. So this is one of the tools which we have done, and we have application for it. And quantum AI to predict protein ligand interactions, and quantum generative AI for molecules of desired properties. Once we do this drug, later we need to understand how exactly it is, what is the toxic, how it used, because now there are a lot of animal models has been done, but that can be also used as a prediction, and we can have only few tests with the mouse, so that the drug screening and discovery, which is a huge market, is going to reduce when we use these things. So this is what we are working on, and we are doing it in our pace to understand all these things. Thank you. I'm ready to take any questions, except very technical quantum computing where this is not my domain. It's only finding out what are the problem we have in drug screening or genomics and applying appropriate quantum techniques to solve it. Yeah. Yes.
Ma'am, so before you started using those T-gates, did you kind of use any other error mitigation technique and did it serve any purpose?
No, we haven't done. Actually, one of the expert in quantum, they told you can check. We have no clues, but it went down. So that since the results were good, we thought T-gates is really working on error mitigation.
Yeah, T-gates is what makes circuits really quantum. So I guess.
Maybe I have no clues about why it is, how it is, but I know it has worked.
Thank you so much, ma'am, for such a profound session. To honor Dr. Ma'am, I would like to invite Dr. Aniket Shah sir to join us on stage for felicitation. Ladies and gentlemen, as we wrap up today's session, let's take a moment to reflect on the wealth of knowledge and inspiration our speakers have shared. Their insights into quantum computing are truly shaping the future and guiding us towards the new frontiers. Thank you all for being part of this enlightening experience. We hope today's sessions have sparked new ideas and motivation. Let's continue to push the boundaries of innovation together. Have a great evening, and we look forward to seeing you tomorrow at the workshop commencing at 9:30 a.m. at DSA and MLT Lab, the Wing 5th Floor Department of AI/ML. Thank you so much. Yeah. So we are concluding the day one program. Thank you.
A very good round of applause to all the second year BPT students. They are and they are also the members of the quantum computing club, sir. Yes. So quantum computing club के ही students हैं who have volunteered for these students.
Very good. So quantum is growing in
Yes.
So बंद कर विशा ये सारा बंद कर
Yeah.